Hey everyone, my name is Vishwas and welcome to this brand new course where we're going to learn how to build AI applications with Next.js. Now, a few years ago, if you wanted to add AI features to your app, you would need a data science team, months of development, and probably a small fortune in infrastructure. Today, it's a completely different story. We're living in this incredible moment where AI has become accessible to every web developer. You can build AI-powered applications that write like humans, understand context, analyze images, have conversations, and make intelligent decisions. And the best part is you can do it all without a PhD in machine learning. But how do we go from traditional web development to building these intelligent features? Well, that's where the right tools make all the difference. For this course, I have chosen two powerful tools that work beautifully together. First, Next.js, the React framework that many of us already use and love. It gives us everything we need for modern web applications right out of the box. And second, the AI SDK from Vercel. It's a library that handles all the complex parts of AI integration so we can focus on building great AI features. Let me explain what the AI SDK actually brings to the table. It is organized into three main parts. First, we have AI SDK Core, and this is the foundation which gives us a unified API for generating text, structured objects, tool calls, and even building AI agents. All the background operations you'll need start here. The beautiful thing is that it works the same way regardless of which AI provider you're using. Second, we have AI SDK UI. This is a set of framework-agnostic hooks for quickly building chat and generative UI. Instead of managing message state, handling streaming updates, and dealing with all the complexity of real-time interfaces, you get hooks that just work. It's like having a UI expert on your team who has already solved all the hard problems. Finally, we have AI SDK RSC for React Server components. It's an alternative to AI SDK UI, but only for frameworks that support React Server components. Since this is experimental, we will focus on the core and UI parts in this course. Because the AI SDK is built by the same team that created Next.js, it integrates seamlessly with all the Next.js patterns we already know and use. Now that you understand the tools we'll be using, let's talk about who should take this course. If you're a Next.js developer who's been curious about AI but hasn't known where to start, this course is for you. Maybe you've seen all the AI demos online and wondered how to build something similar. Or perhaps you have tried working directly with APIs and found it overwhelming. This course is designed to guide you from a complete beginner to confidently building AI-powered apps with Next.js. I strongly encourage you to follow along and write the code yourself. However, all the code will be available on GitHub for you to reference, and a link to that is in the description box. Before we start building, let's make sure we are on the same page about prerequisites. You'll need to be comfortable with modern JavaScript, things like async await, array methods, destructuring, and other ES6+ features. You should know the React fundamentals, how components work, passing props, managing state, and especially hooks. We'll be using hooks extensively, including some custom ones from the AI SDK. You need to know Next.js, particularly the app router. You should understand how file-based routing works, how to create API routes, and the basics of server and client components. I have an extensive Next.js course on the channel, and I highly recommend you check it out. As for TypeScript, some experience will help, but don't worry if you're not an expert. I will explain the TypeScript-specific parts so you can learn as we go. All right, with this introduction in mind, let's proceed to setting up our development environment. Let's get our development environment ready. We'll go through 4 simple steps to get everything up and running. First up, we need to create our Next.js application. Open your terminal and run the command npx create next app at latest, followed by the project name. Let's call it Next.js AI app. You will see a few prompts, so here's what to select. TypeScript, yes. ESLint, yes. Tailwind CSS, yes. Source directory, yes. App router, yes. TurboPack, no, but please feel free to try it out. And customize import alias, no. This will take a few seconds to complete. Once it's done, you'll have a fresh Next.js app ready to go. With our app created, step 2 is installing the AI SDK dependencies. The AI SDK is modular, which means we install exactly what we need. First, navigate into the project folder. So cd Next.js AI app. Now let's install the dependencies. npm install AI at AI SDK / OpenAI at AI SDK / React and Zod. AI is the core SDK package and provides all the fundamental functions we need. AI SDK / OpenAI connects us to OpenAI's models. AI SDK / React contains React-specific hooks that we will use in our components. And finally, Zod helps us create type-safe schemas, which we will use later in this course. Now, if you're wondering, what if I want to use Anthropic or Google instead of OpenAI? Well, it's simple. You just install their packages too. I'll show you how to do that later in the course, but for now, let's focus on OpenAI. Step 3, we need an OpenAI API key. Head to platform.openai.com and create an account if you don't have one already. Then navigate to the API keys section and generate a new secret key. Now here's the reality. Using AI models costs money, and there is no getting around that. You will need to add billing to your OpenAI account. For this entire course, expect to spend about $10 or $20. And in my opinion, that's a bargain for learning skills that will be valuable for years to come. So go ahead, add your billing information, set up a payment method, and generate a new API key. For obvious reasons, I cannot show you my API key, so I'm going to create a new secret key behind the scenes. All right, now that you have your own API key, the fourth and final step is storing it securely. Let's create a .env.local file in the project root folder. .env.local. Open the file and add your OpenAI API key. So OpenAI API key is equal to, within quotes, your API key. Now Next.js automatically includes .env.local in the git ignore file, which is exactly what we want. Never commit API keys to version control, as you want your key to be safe and prevent others from using it. I'm going to add my API key off camera. All right, time to test and make sure everything works. Start the development server by running npm run dev. Open your browser and go to http localhost 3000, and you should see the Next.js welcome page. We have set up our project and we are ready to build. Next, we'll write our first piece of code and learn how to send messages to OpenAI and display the response. We'll start simple and gradually work our way up to more sophisticated features. Now that we have our project set up, let's build our first AI feature, generating text responses from AI. We'll tackle this in two parts. First, we'll create a route handler to communicate with OpenAI. Second, we'll create a UI to display the response. Let's start by creating a route handler. In the app folder, create a new folder and call it API. This is where all our API routes will live. Now, inside the API folder, create another folder called completion. This name will become part of our API endpoint. Finally, inside completion, create a new file called route.ts. This is where we will write our handler code. Start by defining an async post request handler. Export async function post. The function name must be post, as this tells which HTTP method this handler responds to. Next, let's add our imports at the top of the file. Import the generate text function from the core AI package and the OpenAI provider from AI SDK / OpenAI package. These work together to generate text using OpenAI's models. Inside the post function, let's make our first AI call. We'll call generate text with an object containing two properties. The first property is model. This specifies which language model to use. We'll use the GPT 4.1 Nano from OpenAI. So call OpenAI, passing in GPT-4.1-Nano. We will explore different models later on, but for now, know that GPT 4.1 Nano is a fast, efficient model perfect for generating text. Now the second property is prompt. This is the instruction we give to the model. For now, let's hardcode, explain what an LLM is in simple terms. The generateText function returns a promise that resolves to an object containing the generated text. Let's await the result and destructure the text property from the resulting object. Finally, let's return it as JSON. Return response.json object with key and value set to text. We have just created our first AI-powered API route. Time to test it. We'll use Thunder Client, a VS Code extension for testing APIs. Click on the extension, new request, change the method to post, and send a request to http localhost 3000/API/completion. The request should take a few seconds, and then you'll see the response from the AI. It's an object with the property text, and the value is the text generated from AI. This answer is in response to our prompt, explain what an LLM is in simple terms. So sure, an LLM or large language model is kind of a computer program, and you can read the rest. But it is quite clear our route handler is working as expected. 11 lines of code to interact with AI. How crazy is that? But now that we have our API, let's implement the UI. Our UI will accept user input and display the AI's response. So go back to the app folder and create a new folder called UI. Inside UI, create another folder called completion. And in here, create a new file called page.tsx. Now, this folder structure is not a Next.js convention. I just like organizing the UI folders to match our API structure. It makes the project easier to navigate. The file names, however, are not flexible. You have to call it page.tsx and route.ts. All right, let's build our UI component step by step. Start by creating the basic component structure. So export, default function, completion page. At the top, we'll add the use client directive, as this will be a client component that will make use of React state and handle interactivity. For the JSX, we'll start with a container div element. And within the container, we'll add a placeholder for our completion text. So display area for completion will go here. At the bottom of the container goes the form. Within the form, we'll add another div container with an input and a send button. For the input, we'll add a placeholder. How can I help you? For button, type is equal to submit. Now that we have the structure, we can use Tailwind classes to style all the elements. And I'll skip this part in the video, as styling components is not the focus of the course. You can see I've added Tailwind classes to all the elements, and you can copy these styles from the GitHub repo, but also feel free to style the UI to your liking. You can see this page in the browser by navigating to localhost 3000/UI/completion. You can see at the bottom of the screen, we have an input, how can I help you, with a send button and space for the completion text. Now let's go back to our editor and make the input interactive by adding state. At the top, import, use state from React, and create a state variable to track the input value. We'll call it prompt. The setter function setPrompt, and the initial value is an empty string. This is for the user input. On the input element, we can bind value to prompt, and on change, we can call setPrompt, passing in event.target.value. Perfect. Now our input is controlled by React state. Next, let's add the functionality to call our API route handler. We'll need more state variables and a submit handler. We'll create a variable called completion. The setter function setCompletion, and the initial value is an empty string. This is for the AI response. We'll also create isLoading, setIsLoading, with an initial value of false. This is our loading flag. Next, we define our submit handler. So const complete is the name of our function, and this is an async function. The function receives an event of type form event, and we begin by preventing the default behavior of form submission and reloading the page. Next, we call setIsLoading and pass in true. We'll also clear the input immediately for better UX. Next, we'll add a try block where we make our fetch request. So const response is equal to await fetch, and the endpoint is /API/completion. We'll also provide the options object. Method is post, headers, content type, application/JSON, and body JSON.stringify. We pass in the prompt. Once we get back the response, we convert it to JSON, so await response.json. We store it in data, and then we'll call setCompletion, passing in data.text. We'll add a finally block and set isLoading to false. Now let's connect this handler to our form and display the results. So form on submit is equal to complete, which is the function we've just defined. And then based on the loading flag, we will display the AI response. So if isLoading is true, we'll render a div tag with the text loading. Very simple. If isLoading is false, we check if the AI completion exists. If it does, we render a div tag with the completion as content. And if the completion doesn't exist yet, we simply render null. We will also disable the send button when isLoading is true. Finally, let's add proper error handling. We'll add a state variable to track errors and display them if they occur. So use state, we'll call this error, the setter function as setError, and initially the value will be null. The type is going to be either string or null, as we will populate the state variable with the error message when it occurs. So in the try block, if not response.ok, throw a new error, data.error, or something went wrong. Data.error will point to the error thrown from our API route. And if it doesn't exist, we fall back to something went wrong. And after the try block, we will add catch. We handle the error. We console log the error. And then we set the error. If error is instance of error, we set error.message. Otherwise, something went wrong, please try again. This right here is necessary to satisfy TypeScript. But now that we have an error variable and we are able to throw errors, let's update the JSX to show the errors. Within the div container, if there is an error, we render that error and we apply some Tailwind classes. Perfect. We've built our UI component progressively. We started with the basics JSX structure, added state to make the input interactive, implemented the API call functionality, and added proper error handling. This approach lets you see the component working at each stage and makes it easier to understand how the pieces fit together. Now, I strongly encourage you to type this code yourself. It really helps with learning. But if you need the completed code, check out the GitHub repo linked in the description. And now that we have our UI ready, we need to modify our route handler to accept the prompt from the request body instead of using a hard-coded prompt. We will also add error handling. So go back to route.ts and update the post handler function. We'll update the handler to accept a request parameter. So request of type request. From the request body, extract the user prompt. So await request.json. This returns a promise that resolves to the request body parsed as JSON. We will destructure the prompt property, so const prompt, and pass it directly to generate text. So prompt is the key and prompt is the value, and you can rely on ES6 shorthand syntax and specify just prompt. We'll then wrap this in a try-catch block to handle any errors. So try, catch, and if there is an error, console.error, error generating text, and we log the error, and we return response.json, error, failed to generate text. We also specify status 500. We can change console log to console error in page.tsx as well. All right, that was a lot of code, but now it's time to see it in action. Make sure your dev server is running. Navigate to /UI/completion and try asking, explain machine learning in one paragraph. Press enter. You should see the loading state. Then the AI response appears. Modify the model name to force an error. So nano123. Send a new request, hello, and you should see the error message, failed to generate text. There you go. We've built our very first AI-powered feature, text completion. Let me revert the model name and quickly summarize what we have done. First, we created a route handler to communicate with OpenAI's API. We made use of generate text from AI core package and OpenAI from AI SDK/OpenAI. For the UI, we created a clean form input and response display. We set up state variables. We accepted the prompt, made a fetch request passing in the prompt, and set the completion text. Based on the state variables, we display either the error, the loading text, or the completion. Text completion like this is perfect for Q&A features, content summarization, or any scenario where you need AI-generated text. Just remember, each API call costs money, so start with simple prompts while learning, and keep an eye on your OpenAI usage dashboard. All right, our text completion works great. Next, we'll learn how to improve this experience with streaming responses. Previously, we built AI-powered text completion where users can send a prompt, wait for the entire response, and then see it all at once. But here's the thing, AI models can be slow, especially when generating longer responses. Users might be staring at a loading spinner for 5, 10, even 20 seconds, which is not a great experience. This is where streaming comes in. Instead of waiting for the entire response, we can start showing text as soon as the AI starts generating it. It's like the difference between downloading a movie completely before watching it versus streaming it on YouTube or Netflix. With streaming, the user sees progress immediately, which makes the app feel much faster and more responsive. For this lesson, let's see how we can implement streaming to improve the user experience in our Next.js app. First, let's create our streaming API route. So go to the app folder and then API folder and create a new folder called stream. Inside this folder, create a route.ts file. The route handler code is very similar to the completion route handler code, but we will write this from scratch to make sure the concepts stick. Start by defining an async post request handler. So export async function post. The function name must be post, as this tells Next.js which HTTP method this handler responds to. Next, let's add our imports at the top of the file. Import a function called stream text from the core AI package and OpenAI from AI SDK/OpenAI. Stream text is a function designed specifically for streaming responses. Now, inside the post function, let's get the prompt from the request. So request of type request. And within the function body, we destructure prompt by awaiting request.json. Now let's call stream text with our model and prompt. So stream text, parentheses, object, property is model. We specify OpenAI, and our model is GPT 4.1 Nano. And in the next line, we specify prompt set to prompt. Of course, we can make use of ES6 shorthand and specify just prompt. We will store the return value in a constant called result. And it is very important we don't await stream text. Finally, we return the streaming response. So return result dot to UI message stream response. This method, to UI message stream response, creates an HTTP response that streams the data in a format that the UI can understand. Finally, let's wrap this in a try-catch block to handle any errors. So try, catch, we catch an error, console.error, error streaming text, and then we return a new response, failed to stream text. Status 500. Our streaming route is ready. You can see how similar this is to our previous route. The main differences are using stream text instead of generate text and returning to UI message stream response instead of JSON. Now for the exciting part. Let's build a UI component that can consume this streaming response. So in the UI folder, create a new folder called stream, and inside stream, create page.tsx. Let's start with the basic component structure. Use client directive, since this is going to be a client component. Export default function, stream page, with a simple div that says stream page. For the JSX, we will replicate the UI from our previous completion page. We'll start with a container div. We'll leave space for the streaming text to be displayed. So display area for streaming text will go here. At the bottom goes the form. So form, a flex div container with input and a send button. The input placeholder, how can I help? The last bit is to style these elements using Tailwind classes, and you can copy the styles from completion page.tsx. I also realized stream needs to be inside the UI folder. And here, stream needs to be inside the API folder. To save us the time, I have pasted classes for each element behind the scenes. You can see this UI in the browser by navigating to /UI/stream. The same layout as the completion component, but I've changed the placeholder to ask me anything to make it clear. The next step is to make the input interactive by adding state. The beauty of the AI SDK is that it provides a hook specifically for handling streaming completions. Let's import it. At the top, import, use completion from AI SDK/React. Now let's use this hook in our component. Use completion. This hook needs to know which API endpoint to call. So we pass in an object with the API property set to /API/stream. This is the path of our route handler. This hook returns an object with everything we need to handle the streaming response. First, let's get the input value and the onChange handler. So input and handle input change. Let's bind these to our input field. Value is equal to input. OnChange is equal to handle input change. Next, let's get the form submission handler. So after handle input change, the structure handle submit. Bind it to onSubmit on the form element. OnSubmit is equal to handle submit. Now for the most important part, the streaming completion. Let's get it once again from the hook. It's called completion. The completion value automatically updates as new chunks arrive from the server. Let's display it above the form. So if the completion exists, render it in a div. The magic here is that we don't need to manually handle the stream or update state. The hook does it all for us. Next, let's add loading state. The useCompletion hook provides isLoading property. Destructure it and use it to disable the button while loading. So disabled is equal to isLoading. Let's also add a loading indicator that shows when we are waiting for the first chunk. So isLoading, and there is no completion. Render loading text. Next, let's add error handling. The hook provides an error object. Destructure it. We can use this to display errors when they occur. So error, and if it exists, we display error.message. We'll also apply some Tailwind classes. Text red 500 and margin bottom 4. All right, time to test this in the browser. Navigate to /UI/stream and enter a prompt. What is an LLM? When you submit, you should see the loading text appear and the response stream in real time. This is a great improvement over the previous example, where the user had to wait for the entire response before seeing any text. Now, as of this recording, there is a bug where the input is not cleared after you submit a prompt. This is a known issue and should be fixed soon, but here's a workaround for now. From use completion, destructure the set input function. In the onSubmit handler, call it with an empty string. So this is going to be a function where we prevent default behavior, call set input with an empty string, and then call handle submit, passing in the event. Back in the browser, enter a prompt, what is machine learning, press enter, and you should see the input cleared and the response stream in real time. Let me show you one more feature related to streaming. For really long responses, users might want to stop the generation. The use completion hook gives us a stop function, which we can use to abort the current API request. So destructure the stop function from the hook and update the submit button to show a stop button when the stream is in progress. So curly braces for some JavaScript. Is loading. We render a stop button. OnClick is equal to stop. And we're going to add some Tailwind classes. Again, styling is not the focus of this course, so please feel free to style the buttons as you like. Now, if it is not loading, we render the current send button. Save the file to format the ternary expression. Back in the browser, start a long prompt by entering explain machine learning in detail, and while it is streaming, click the stop button. This will halt the streaming response. We have successfully implemented streaming text generation. All right, let's quickly review what we have done. We created a streaming API route using stream text and two UI message stream response method. We built a UI with the use completion hook. We added all the features one by one: input handling, streaming display, loading state, error handling, and the stop functionality. The AI SDK handles all the complex streaming protocols, letting us focus on building great user experiences. If something's not working, the code is available on my GitHub repo, so please make sure to check that out. All right, for our next topic, we'll take a step back and learn about models and tokens, which are fundamental concepts to understand when working with AI. We've learned how to build AI-powered text completion and streaming features. In both cases, we've been using this line: model, OpenAI GPT 4.1 Nano. But what exactly is a model? Why this specific one? And how do you choose the right model for your own projects? Let's dive in and understand these foundational concepts. In simple terms, an AI model is a program that has been trained on a set of data to recognize patterns and make predictions without human intervention. Think of it like a really smart assistant who has read millions of books and can now help you write, analyze, or create based on all that knowledge. In the real world, AI models power everything from the autocomplete in your phone's keyboard to self-driving cars. Now let's break down the different types of models you will work with as an application developer. First up, we have text generation models, and these are your bread and butter. They process and generate human-like text, perfect for everything from writing and analysis to conversion and code. You'll also hear people call them LLMs, which stands for large language models. They're large because they were trained on absolutely massive amounts of text data. To give you some perspective here, GPT-4 was trained on hundreds of billions of words. That's more text than you could read in 1,000 lifetimes. But all that training is what allows these models to understand context, follow instructions, and generate human-like text. The big names here are GPT-4 from OpenAI, Claude from Anthropic, and Gemini from Google. For most of your AI features like chatbots, content generation, code assistants, these are what you'll use. Second, we have embedding models. Now, these are a bit different. Instead of generating text, they convert text into numbers, specifically vectors that capture the meaning of the text. Here's a simple way to think about it. Imagine if you could turn the meaning of a sentence into a set of coordinates on a map. Similar meanings would be close together on that map. That's essentially what embeddings do. You might not use these directly as often, but they're working behind the scenes in features like content recommendations. For example, you find Italian restaurants when you search for pasta places. Then we have image models. These either generate images from text description or analyze existing images. Popular ones include Midjourney and GPT image models from OpenAI and Flux from Black Forest Labs. These are perfect for generating product images, analyzing uploaded photos, or creating visual content on the fly. Finally, we have multimodal models, which are the Swiss Army knives of the AI world. These can handle multiple types of input and output. Feed them text, images, or sometimes even audio, and they will process it all. They're incredibly versatile, but come with higher costs. Models like GPT-4, Claude 4, and Gemini fall into this category. Now that we know the different types, let's talk about what makes each model unique. Understanding model characteristics will help you pick the right model for your use case. First, we have context window, which is how much information a model can process in a single conversation. Think of it as the model's working memory. Some models can hold only a few pages of text at once, while others can process entire books. If you're building a document analysis app, you will want a model with a large context window. But for simple Q&A or basic chat, a model with a smaller context window works just fine. Second, we have intelligence, which determines how well a model understands nuance, follows complex instructions, and generates high-quality output. Less capable models are great for straightforward tasks like answering FAQs, categorizing text, or following templates. But when you need creativity, complex problem solving, or understanding context and subtext, that's when you reach for the more capable models. Always match the model to your task complexity. Next, we have speed, which is all about response time. If users are waiting for a response, like in a chat interface, you need speed. Nobody wants to stare at a loading spinner. But if you're generating reports in the background, take your time and use a slower model with better quality. Finally, we have cost, which varies between models. The pattern is pretty predictable. Faster, smarter, larger context window models cost more. My tip for you is to use cheaper models during development. Now here is a simple framework to help you choose the right model for your use case. For real-time features like autocomplete or a simple chat interface, speed is king. Users expect instant responses, so pick a fast model even if it's not the smartest. For generating content, quality beats speed. Users will wait an extra second or two for better writing, so pick a more intelligent model. For analyzing documents, you need a large context window to fit everything. Don't try to squeeze a large PDF through a small model. You should always test and experiment with different models to find the right balance for your use case. Think of it like choosing between a sports car and a city car. Both get you where you need to go, but one is built for performance while the other is built for efficiency. So start cheap, monitor usage, upgrade, and optimize based on actual needs. Alright, now that we have learned about models, you might be wondering who creates and maintains these models. This is where providers come in. If models are cars, providers are the manufacturers. Companies like OpenAI, Anthropic, and Google are like the Ford, BMW, and Mercedes of the AI world. Each provider invests hundreds of millions in research, has their own approach, and offers different strengths. When choosing a provider, consider reliability, pricing, features, and privacy. Looking at our code, it should be clear now. OpenAI is our provider, and GPT 4.1 Nano is their model. Now, one of the great features about the AI SDK is that it makes it super easy to switch between different models and providers. Let me show you how to switch from OpenAI's GPT 4.1 Nano to Anthropic's Claude Sonnet 4. First, within the project folder, so Next.js AI app, install AI SDK's Anthropic package. So npm install @ai-sdk/Anthropic. Next, we need an API key. You can head to Anthropic's console, link in the description, create an account, and generate a key. Unfortunately, there is no free tier when it comes to AI models. But if you prefer not to pay for yet another provider, you can simply watch what I'm doing without having to create an account. You can use the learnings for when the time comes. So once you have created an account, add the key to your .env.local file. Now I'm going to do this off camera, but here's how you do it. You have your OpenAI API key already set, and you add another Anthropic API key. These will be in quotes. Remember, API keys are secret. Never commit them to Git. All right, I've just updated mine behind the scenes. Now for the fun part. In the route handler present in the stream folder, import Anthropic from AI SDK/Anthropic. Update the model to Anthropic, and the model is Claude Sonnet 4, and we have the particular date. Each provider has a different naming convention, so we have to follow that. But this is pretty much it. One line change is all it takes to switch between models and providers. Save the file, restart the dev server, so npm run dev, and head to the browser. Submit a new prompt, so tell me about Batman, and watch. We see the response streaming in, but this time it is from Anthropic's Claude model. The AI SDK's unified API means you can easily experiment with different models by just changing the provider and model name. This makes it easy to test different models during development, switch providers and models based on cost or performance needs, have fallback models if one provider is down, and upgrade to newer model versions as they are released. No need to learn different APIs or rewrite your application logic. The AI SDK handles all the implementation details behind the scenes. If you want to switch back, just change this line to model OpenAI GPT 4.1 Nano. It really is that simple. Before we wrap up, let me mention that OpenAI's GPT 4.1 Nano is perfect for learning. If you look at OpenAI's docs, you will see that GPT 4.1 Nano is the fastest, most cost-effective GPT 4.1 model. And if you navigate to the pricing page, you will see that GPT 4.1 Nano is a clear winner by just looking at the numbers. It costs 10 cents per million input tokens and 40 cents per million output tokens. But what exactly are tokens? Let's explore that next. So we've been using OpenAI's GPT 4.1 Nano model, and on the pricing page, we can see it costs 10 cents per million input tokens and 40 cents per million output tokens. But what exactly are tokens? This is something that confused me when I first started, so let's break it down together because understanding tokens is absolutely crucial for building cost-effective AI applications. In the context of AI models, particularly language models, a token is a basic unit of text that the model processes. They can be whole words, parts of words, individual characters, or even punctuation marks. What's interesting though is that depending on the context and the model you're using, the same word might be tokenized differently. Let me give you an example. The word hamburger, one model might split it into ham, bur, and gur, but another model might go with ham and burger. Same word, different breakdown. Let's look at a simple sentence. I love to eat pizza. When we tokenize this, it becomes I love to eat pizza and exclamation sign. That is 6 tokens in total. Instead of me just telling you, let me show this in action. Let's head over to OpenAI's tokenizer tool. So platform.openai.com/tokenizer. This tool is great for really understanding how text gets broken down. Once you're here, click on the Show Example button. It fills the text area with some sample sentences. If I scroll down, you can see what the tokenizer is doing. It's breaking down the text and showing us several things. Up at the top, we've got our token count and character count. 53 tokens to 52 characters. But the really cool part is down here where it uses different colors to show us how the text is broken down into tokens. Each color represents an individual token. At the top, you will see a model selection control where you can change the model. Go ahead and click on GPT 3.5 and GPT 4. You will see how the tokenization changes. This is because different models learned to break down language in slightly different ways during training. You can see this model broke it down into 57 tokens. The first one was 53 tokens. As you can see, a token is simply a chunk of text with no specific length. As a rough rule of thumb, one token equals about 4 characters in English text. This isn't exact, but it is useful for quick estimates. Now you might be thinking, okay, tokens are interesting, but why should I care? Well, tokens aren't just technical trivia. They directly impact your application in 3 important ways. First, tokens determine how much text you can process at once. Every model has a maximum token limit, and if you hit that limit, you can't process any more text. Second, and this is the big one for most developers, tokens determine how much your API calls cost. Remember these pricing numbers we looked at earlier? All based on tokens. And third, tokens affect the quality of your results. If you send too many tokens, you might overwhelm the model with information. Too few, and the model might not have enough context to give you a good response. And this brings us to the topic of context window. We've already learned that every model has a context window which represents how much information a model can process in a single conversation. Well, let me tell you that context window is measured in tokens. Now, GPT 4.1 Nano, the model we are using, can handle up to 1 million tokens in a single conversation. That is absolutely massive. Let me put that in perspective for you. 1 million tokens is roughly 2,500 to 3,000 pages of text. That's equivalent to feeding the entire Lord of the Rings trilogy to the model at once. All of it in the model's memory, ready to reference. But, and this is important, there is a catch. When you hit that limit, older information starts getting pushed out to make room for new stuff. Imagine the model's memory as a whiteboard. As you keep writing, you eventually run out of space, so you have to erase the oldest nodes to add new one. That's why in tools like ChatGPT or Claude, it's smart to start a new conversation when things get too long. Next, let's talk about something that trips up a lot of developers: the difference between input and output tokens. Input tokens are everything you send to the model. Output tokens are everything the model generates in response. Now, why does this distinction matter? Well, there are 3 key reasons. First, different models have different limits for input versus output. Some models can accept huge inputs, but can only generate smaller outputs. Second, and this is where it hits your wallet, input and output tokens have different pricing. For example, GPT 4.1 Nano output tokens cost 4 times more than input tokens. Third, understanding this helps you optimize your API costs. You might structure your prompts differently once you know how the pricing works. Let's make this concrete with a real example. I'm going to show you exactly how much a typical API call costs. So we've got GPT 4.1 Nano's pricing: 10 cents per million input tokens, 40 cents per million output tokens. Let's say our input is "what is AI" in simple terms, and the model responds with this explanation. In this scenario, the input tokens are 7 and the output tokens are 84. With some quick math, here's how much it costs. That is about 3 thousandths of a cent. Seems tiny, right? But here's the thing. In production, when you're making thousands of requests per day, these costs add up fast. If you're making 100,000 requests daily with similar token counts, you're looking at $3.43 per day. That's around $100 per month. And this is for a relatively simple use case. But enough theory. Let's get back to our code and see how we can actually track token usage in our Next.js app using AI SDK. Let me open up the route handler file where we have our stream text function. Now, after the stream text call, but before we return the response, we're going to add some logging to our token usage. The result object that comes back from stream text has this usage property, which we can access. But here's the thing. Since we are streaming the response, the usage information is only available after the stream completes. So we need to handle this asynchronously. So result.usage.then, we specify a callback function, which gets access to the usage. And we're going to console log input tokens as usage.input tokens, output tokens as usage.output tokens, and total tokens usage.total tokens. Input tokens is the number of tokens we sent. Output tokens is the number of tokens the model generated. Total tokens is just the sum of both. Save the file, go back to your browser, and in the /UI/stream route, send a prompt. What is AI in simple terms? Now let's switch back to the terminal where our Next.js server is running. And after the response finishes streaming, you should see something like input tokens 14, output tokens 66, total tokens 80. Now the input tokens here is 14, but if we go to our tokenizer tool and we enter what is AI in simple terms, we can only see 7 tokens for our prompt. This is because the AI SDK automatically includes some system tokens for formatting and context. And this is normal, but just something to be aware of when you're calculating costs. So remember, tokens are the currency of AI. Every request costs token, and tokens cost money. Understanding which model to use and how to optimize your token usage is crucial for building cost-effective AI applications. All right, now that we understand tokens and can track them, we are ready to move on to something more interactive. In the next lesson, we'll explore how to implement chat functionality with the AI SDK. Previously, we learned how to send prompts to an AI and display the response. I can type a prompt, what is React, in the input field, click send, and we get the response back from our AI. Our implementation works great, but there's an important limitation you need to understand. AI models don't have memory. Let me refresh the page and show you what I mean. Watch what happens when I have a conversation. First, I'll ask, "Hi, I'm Vishwas. Who are you?" The AI responds nicely with a greeting. Perfect. Now let me ask a follow-up question. What is my name? You can see that it has no idea who I am, even though I just prompted a second ago. This happens because each prompt is treated as a completely independent request, kind of like browsing the web in incognito mode. The AI starts fresh every time with zero memory of your last message. To build a proper conversational experience, we need to maintain an ordered history of all messages and include that history with every new prompt. Now, you might think this would require complex state management and lots of code, but the AI SDK makes it super simple. Let's learn how by building a chatbot. We'll approach this in 2 parts. First, creating a route handler that maintains conversation history. Then, building a chat UI to display the conversation. Let's start by creating our chat API route. In the API folder, create a new folder called chat. Inside, create route.ts. Start by defining an async host request handler with a request parameter. So export async function host, and we specify the request parameter. Now, unlike our previous routes where we got a single prompt from the request body, here we need to get an array of messages. From the request body, so await request.json, we're going to destructure messages. Messages will be an array containing the entire conversation history. For TypeScript to understand what these messages are, let's import the UI message type. So at the top, import UI message from AI. And within the function body, we specify messages is of type UI message array. The UI message type represents messages that come from our UI. Now we need to stream a response. So let's import stream text from AI and OpenAI from AI SDK / OpenAI. Within the function body, invoke the stream text function with an object with the model set to OpenAI, GPT 4.1 Nano, and messages to messages. We will store the return value in a constant called result. But you should know that the messages from our UI may contain extra information that we need to render the UI. For example, a timestamp for when the message was sent, or the duration it took to generate the response. However, the AI model is not interested in such information and only needs the core message content, considering token input constraints and costs. To address this, the AI SDK provides a helper function. From the AI package, import convert to model messages. Now you can use it when passing messages to the stream text function. So convert to model messages or UI messages. This helper function strips away UI-specific metadata like timestamps and converts messages to the format the AI model expects. You can see the TypeScript is now happy. We will return the streaming response using toUI message stream response. Finally, let's wrap this in a try-catch block to handle any errors. Try block, catch error, we console.error, error, streaming chat completion, and then return new response, failed to stream chat completion, status 500. That is our chat route handler. The key difference from our previous routes is handling an array of messages instead of a single prompt. Now for the UI. In the UI folder, create a new folder called chat, and inside, create page.tsx. Let's start with the basic component structure similar to our previous routes. Use client directive at the top, export, default function, chat page. We'll start with a div container. We'll leave space for chat messages to be displayed, so messages will go here. And at the bottom goes the form. So form element with a div flex container. With an input, placeholder is equal to how can I help you? And a button element that says send. Type is equal to submit. I'm going to style this with Tailwind classes, and you can copy the code from my GitHub repo. We still have the div container, the form element, the div flex container within the form to place the input and the button side by side. The layout is identical to our previous routes. You can see this UI in the browser by navigating to /UI/chat. We have our input, how can I help you, and the send button. The next step is to make this form interactive. For chat functionality, we need to manage the input state ourselves. So at the top, import useState from React, and within the component, create a state variable called input, the setter function setInput, and the initial value is an empty string. Now let's bind these values to our input element. Value is equal to input, and onChange is equal to an arrow function where we get the event and we call setInput, passing in event.target.value. Next, we need the chat functionality. Now the AI SDK provides a hook specifically for chat. Let's import it. Import, use chat from AI SDK / React. Invoke it within the component. By default, the API endpoint is /API/chat, which is exactly what we have created. Of course, I will show you how to change the default endpoint very soon. But this useChat hook returns an object with everything we need to handle chat. Let's start with messages. What does a messages array look like? It's actually quite complex, so I'm going to show you a simplified version that represents a basic chat conversation. Messages is an array of type UI message. The UI message type has three properties: ID, role, and parts. ID is a unique string identifier for each message, which helps track and reference specific messages within the conversation. Role indicates who sent the message. The value is user when the human sends a message, or assistant when the AI responds. Parts is an array containing the actual content of the message. Each part is an object of type text UI part, which has a type and text property. Type is always set to text, indicating this part contains textual content. Text is a string that represents the actual text content of that part. Here is an example of a messages array to help you understand better. We are dealing with a simple chat conversation here. The user asks a question, so role is user, type is text, and the actual text is what is React. The AI responds with a simple answer, so the role is assistant. Type continues to be text, and text will refer to the response generated from AI. The user then asks a follow-up question, so role is user again. Type text, and the text is, can you give me an example? The AI responds with a more detailed answer, so role is assistant again. Type text, and the text here is a simple React component. For now, we are just handling text parts with type set to text and text property set to the text content, but there are other types of parts which we will cover later in the course. But now that you understand this basic structure, let's render the messages array in our UI. So right above the form, curly braces, and we loop through the messages array using the map method. So messages.map. We pass in a callback function. For each message, we render a div with the message ID as the key. So key is equal to message.id. And within the div, first we'll display the role for that message. If the role is user, so message.role is equal to user, we will display you. And if it's assistant, we'll display AI. Once we have the role, we loop through the parts array using the map method. So curly braces. And for each message, we map over parts. We pass in a callback function. Now remember, each part is an object, and at the moment, it has type and text properties. We will use a switch statement to handle the different part types. If the type is text, we display the text content. So back in our code, for each part, we add a switch statement. If part.type for case text, so if this is text content, we return a div tag rendering the text content. We'll also specify the key as message ID, so $curly braces, message.id, followed by index. For any other case, we return null. I will also add the tailoring classes for styling. So on the outer div, a margin bottom 4. On the role div, font semi-bold. And for the div that renders the part text content, whitespace pre-wrap. This might be difficult to wrap your head around, so let me explain the logic to render messages one more time. So messages is an array with ID, role, and parts. Parts itself is an array of objects. Each object has type set to text and text set to the actual content. So in our code, we start by looping over the messages array. For each message, we render the role, you or AI. And then for each message, we loop over the parts. If the part type is text, we render the text content. For everything else, we return null. This might seem a bit overkill at the moment, but trust me, it will make sense when we render other content types later in the course. Alright, our messages will now render in the UI, but we haven't wired up the form yet. So let's destructure the send message function from useChatHook. This allows us to send new messages to the AI. Let's create a submit handler, which will be called when the form is submitted. So const handle submit. We get hold of the event, which is of type react.formEvent, HTML form element. And within the function body, we will start by preventing the default form submission behavior. So e.preventDefault. Next, we'll call send message with a property text set to our input value. We will also reset the input field to an empty string. So set input, empty string. Now bind handle submit to the form element. So form on submit is equal to handle submit. All right, our next step is to handle the different states for a better experience. From the useChat hook, destructure the status property. The status tells us if we are ready, submitted, streaming, or error. Let's use this to show a loading indicator right below messages. We will rely on Tailwind CSS to show a spinning animation. So if status is equal to submitted or status is equal to streaming, we're going to render a loading spinner. I'm going to paste the code to save us some time. It is basically 3 div elements with Tailwind CSS classes. And while we're at it, let's also disable the button when we are not ready. So disabled status is not equal to ready. We've also added the necessary styles for disabled state. All right, next, let's add error handling. The hook provides an error object. Let's destructure it. In the JSX, display the error message at the top. So error, and if it exists, we render a div tag error.message. We'll also add some Tailwind CSS classes, text red 500 and margin bottom 4. Finally, let's add stop functionality for longer responses. So destructure the stop function and update the button to show different options. If status is equal to submitted or status is equal to streaming, we're going to render the stop button. If that is not the condition, we render our send button. Perfect. We've built our chat interface piece by piece. Time to test it out. Navigate to /UI/chat in the browser and test the conversation flow. Ask, "Hi, I'm Vishwas. Who are you?" Wait for the response. We see the loading indicator, and we also see the role. "Hi, I'm Vishwas. Who are you?" And the AI responds with, "Hello, Vishwas. I'm ChatGPT, an AI language model created by OpenAI." Now, continue the conversation by asking, "What is my name?" It responds, "Your name is Vishwas. How can I assist you today, Vishwas?" It remembers my name is Vishwas because it has the entire conversation history. Now, what about tokens in this scenario? Let's go back to our route handler and add token tracking to show how chat affects usage. So result.usage.then, very similar to what we did previously. We get hold of usage, and we're going to log to the console the message count, which is messages.length, input tokens, which is usage.input tokens, output tokens, which is usage.output tokens, and finally total tokens, which is usage.total tokens. Now watch the terminal as you chat. "Hi, I'm Vishwas. Who are you?" We get back a response, and you can see message count 1, input token 17, output tokens 43, total 60. I'm going to follow up. "What is my name?" We get back the response. We see message count 3, input tokens 72, output tokens 19, total 91. "Do you know React?" We get back a response. Message count 5, input tokens 103, output tokens 54, total tokens 157. You can see the input tokens grow with each message because we send the entire conversation history each time. And if the number of tokens grow, so does the cost. This is one of the reasons why apps like ChatGPT and Claude have new chat buttons to reset when conversations get too long. But there you have it. We have successfully implemented an AI-powered chat interface. That was a lot of code, so let me quickly walk you through the implementation one more time. We started with the route handler. We created a post route handler that extracts the messages from the request body, converts them to the model format, and streams the response. We also added token tracking to show how chat affects usage. For the UI, we created a client component. We added a form with an input and a send button. We also added a div to display the messages. We manage the input state ourselves and use the useChat hook for everything else. The messages is an array of objects with an ID, role, and parts array. We loop through the messages array and display the role and parts. The status flag helps us show a loading indicator and disable the submit button when not ready. We also added error handling and stop functionality for longer messages. I hope you now understand how to build a chat interface with the AI SDK in Next.js. We've been learning how to build AI-powered features with the AI SDK. But if you've been paying attention, you might have noticed something. Every feature we've added is fundamentally about improving user experience. And that's really what building AI applications is all about. How can we leverage powerful AI models to create better experiences for our users? So far, we've made two major improvements. First, we replaced basic text completion with streaming, so users get immediate feedback instead of staring at loading spinners. Then, we added chat with memory, so users can have natural conversations instead of typing isolated questions. Now, let me show you a third way to improve the user experience, which is by tailoring AI responses based on your specific application needs. And this brings us to the concept of prompt engineering. Prompt engineering is a practice of crafting instructions to get better, more appropriate outputs from AI models. It's not about changing the AI model itself. It's about guiding it to produce responses that fit your application perfectly. Think of it like this. You have a brilliant chef who can cook anything. But if you just say, make lunch, you'll get something random. However, if you say, prepare a Thai red curry and sticky rice for someone who likes mild heat, you'll get exactly what you need. Let me show you why this matters for user experience. In our chat interface, ask a question. What is a database? Have a look at the response. It's technically correct, but is it right for your users? If you're building a chat for computer science students, this might be perfect. But what if you're building for small business owners who just want to understand their options, or kids learning to code? This same generic response doesn't work for everyone. And that's where prompt engineering comes in. But it's not just about getting better responses. Good prompt engineering does three important things. First, it ensures responses match your user's needs and knowledge level. Second, it creates consistency, so similar questions get similar types of responses. And third, it can actually reduce costs by encouraging more concise responses that use fewer tokens. And the best part is that your users never see any of this. The AI just naturally responds in the right way for your application. One of the most fundamental prompt engineering techniques is to use system prompts. They are special instructions that shape how the AI behaves throughout an entire conversation. Remember when I showed you the message roles earlier? I mentioned messages have a role of either user or assistant. Well, there's actually a third role I didn't mention called system. System messages are like setting the rules of a board game before anyone plays. They set the context for the entire conversation, but the user never sees them. Let me show you how it works. Currently, we are passing an array of UI messages through convert to model messages and assigning it to the messages array on stream text. Instead, let's add a system message to guide the AI's behavior. So messages is going to be an array of objects. Our first object is going to be our system prompt. So role, system, and content is the clear instruction we provide to the AI. You are a helpful coding assistant. Keep responses under 3 sentences and focus on practical examples. After this system prompt, we spread convert to model messages are UI messages. This is the type of a system prompt. Role set to system and content set to the actual instruction. Please don't confuse with UI message type, which has the parts array that we use to render the UI. Now, about the system instruction itself, I want you to notice how specific the instruction is. Tell the AI three things. What it is, so it's a coding assistant. The length constraint, so under 3 sentences. And the focus area. Practical examples. Save the file, and now let's test the difference. Go back to the browser, and this time, let's ask, what is React? And look at that. Instead of a lengthy explanation, we get a concise answer with a code example. The response is tailored for developers who want quick practical information. Now, let's try another system prompt. You are a friendly teacher who explains concepts using simple analogies. Always relate concepts to everyday experiences. Back to the browser, refresh, type what is React, and you get back a different response. Imagine you're playing with Lego blocks. Each block is a small piece that can be combined with other blocks to build a larger structure like a house or a car. And I'm pretty sure they relate Lego blocks to components. Yep. So you can see that instead of technical jargon, you will get an analogy you can relate to. This is the power of system prompts. Same AI model, completely different communication style. Now there is a trade-off. The system prompts sent with every single request adding to your token count. More tokens means higher costs. So you need to balance between helpful instructions and efficiency. Sometimes telling the AI what to do isn't enough. You need to show it. This technique is called few-shot learning, and it's super powerful for getting responses in a specific format. Let me show you an example. This time, before the real conversation, we will add a few example messages. First is the system message, which sets the context. Role system, content, convert user questions about React into code examples. Then we show an example user question. So role user, content, how to toggle a Boolean. And then we show the exact format we want for the assistant response. So role assistant, content is the code snippet for toggling a Boolean value. Remember, these are model messages, and the type is different from UI messages. Save the file, go back to the browser, refresh, and now when you ask something like how to count clicks, watch what happens. The AI follows the example format and gives you just the code. No explanations, no extra text, just the code snippet you need. This is probably perfect if you're building a chat for developers who want quick code references. Now here are some best practices to keep in mind as you explore prompt engineering for your AI apps. First, start simple and iterate. Your first prompt won't be perfect, so test with real scenarios and refine based on results. Second, be specific but not overly restrictive. Give clear guidance while leaving room for the AI to handle unexpected questions. Third, consider your audience. A prompt that works for developers might confuse designers, so tailor your prompts to your actual users. Fourth, monitor costs. Every word in your system prompt adds tokens to every request. Find the balance between helpful and efficient. Fifth, test edge cases. What happens when users ask off-topic questions? Make sure your prompts handle these gracefully. Finally, document what works. When you find efficient prompts, save them for future projects. Prompt engineering is a vast topic, and there are many complex techniques you can use to get the best out of your AI models. I recommend both OpenAI's Prompt Engineering Guide as well as Anthropic's Prompt Engineering Guide as a good starting point. So far, we have been generating text responses from AI, and that is great for chat interfaces and content generation. But here's the thing, when you're building the front end of an application, you often need data in a specific format. Think about it. If you're building a recipe app, you don't want the AI to just write paragraphs about cooking. You need ingredients as an array, steps in order, cooking times as numbers. Or if you're building a task management app, you need tasks with specific properties like title, priority, and due date. You could try to parse the AI's text response and extract the data yourself, but that's messy and error-prone because what if the AI formats things differently each time? This is where structured data generation comes in. We can tell the AI exactly what shape we want the response in, and it will give us back proper objects and arrays that we can use directly in our code. Let me show you how this works by building a recipe generator. Users will enter a dish name and will get back a properly structured recipe with ingredients and steps. First, we need to define what structure we want. For this, we will use Zod, which is a TypeScript-first schema validation library. We have already installed it with the command npm install Zod. Now let's create our schema. In the API folder, create a new folder called structured data. Inside, create a new file called schema.ts. Start by importing Z from Zod. Now let's think about what a recipe needs. It should have a name, a list of ingredients, and cooking steps. Let's define that. We'll export a constant called recipe schema. This is going to be a Zod object, so z.object, with a recipe property that itself is an object, so z.object again. We will start with just the name, which is a string. So name is of type string. Next, let's add ingredients. The ingredients property is an array, z.array. Each item in the array is an object, so z.object, with name and amount, both strings. So name, z.string, amount, z.string. See how we are easily building this up because Zod lets us compose schemas from simple types. Finally, let's add the cooking steps. The steps is an array of strings, z.array, z.string. Each step is basically just text describing what to do. Perfect. We've used Zod to define exactly what shape we want our recipe data in. The AI will have to match this structure. Now the Zod schema, hopefully, is self-explanatory. If you want to understand more about Zod, please pause the video and refer to the documentation. If you are comfortable with this code, let's proceed. For our next step, let's create the route handler. In the same structured data folder, within the API folder, create a new file called route.ts. Start with the basic post handler structure. Export, async function, post, parameter, request of type request. Now we need to get the dish name from the request. So we're going to destructure dish by awaiting request.json. This will be whatever dish name the user types in. Now here is where it gets interesting. Instead of using generate text or stream text, we will use a new function called stream object. So at the top, import stream object from AI and OpenAI from AI SDK/OpenAI. Within the function body, call stream object with the model OpenAI, GPT 4.1 Nano, and a prompt asking for the recipe. Generate a recipe for the dish. But how does the AI know what structure we want? That is easy. We pass our schema to inform the AI of the expected output. So at the top, import the recipe schema from /schema and add it to the stream object call. Property is schema, and we set it to recipe schema. Now, the AI knows exactly what structure to return. Finally, let's return the streaming response. So const result is equal to stream object, return result dot to text stream response. This method converts the result to a streaming response the client can consume. Finally, let's add error handling. Try block, catch the error, console.error, error generating recipe, and then return new response, failed to generate recipe, with a status of 500. Our route handler for generating structured data is now complete. Now for the UI. In the UI folder, create a new folder called structured data, and inside, create page.tsx. Let's start with the basic component structure. So use client at the top, export default function, structured data page, and we return the JSX. The UI is very similar to our previous components, so I'm going to go over this fairly quick. First, import useState from React and create state for the dish name. Let's call this dish name, set dish name, and the initial value is an empty string. For the JSX, we'll start with a container div, and we'll leave space for structured data to be displayed. So structured data goes here. At the bottom goes our form. So form element, we add a div flex container to place the input and button side by side. Let's call this button generate, type is equal to submit, input placeholder is equal to enter a dish name. And since this is a Next.js plus AI course and not one on Tailwind CSS, behind the scenes, I'm going to add styling for all these elements. So div flex container, the form element, the inner div, which is a flex container to place the input and button side by side, all styled with Tailwind classes. You can see this UI in the browser by navigating to /UI/structured data. We have our input and the generate button. For our next step, let's bind the dish name state variable to the input. So value is equal to dish name, and on change, we get hold of the event and we call set dish name, passing in event.target.value. Now that we are managing the input state, the next step is to make the API call and get the structured data. And for this, the AI SDK conveniently provides a use object hook. Let's import it and use it in our component. Import experimental use object as use object from AI SDK/React. We import the hook with an alias because it is still experimental, but the hook works just fine. Within the component, call the hook with our API endpoint. So use object, you pass in an object with an API property set to /API/structured data. And we also need to set schema to recipe schema. The hook needs to know about our schema because it ensures type safety on the client side too. The hook returns a submit function with which we can send our API requests. Let's implement the submit handler. So const handle submit is equal to event of type React form event. We prevent the default form submission behavior. We call the submit function from use object hook, passing in dish set to dish name, and we clear the input. On the form element, we assign handle submit to on submit. So when you submit the form, the hook will make the API call to /API/structured data, passing in the value of the dish, and the API will return structured data as it streams in. Let's destructure that value from the hook. You get access to it as object, and this will contain our structured recipe data, which we can render in the UI. So first, let's display the recipe name. So object, if it exists and the recipe exists, we're going to render an h2 with object.recipe.name. I will style this with some Tailwind classes. You can see how TypeScript knows about the recipe structure thanks to our schema. Next, let's add ingredients. So right below the h2, curly braces for some JavaScript. So if object recipe ingredients exists, we return a div tag with an h3 that says ingredients, and then another div tag. Within this div tag, we map over the list of ingredients, so object.recipe.ingredients.map. We specify a callback function. We get access to the individual ingredient as well as the index, and we return a div element with key set to index, a paragraph rendering the ingredient name, and another paragraph rendering the amount. With some editing magic, I'm going to add Tailwind classes to all these elements. Please remember, you don't have to follow how I am styling these elements. But if you want to, the code is in the GitHub repository, and a link to that is in the description. All right, once we have rendered the ingredients, the next part is to render the cooking steps. So right after ingredients, curly braces again, object.recipe.steps, and if that exists, we render an element with an h3 that says steps and an ordered list where we map over the steps. So object.recipe.steps.map. We specify a callback function, and for each step with an index, we render a list item with key is equal to index and a span tag that renders index plus 1 followed by the step. And we are quickly going to style this section as well. All right, we are now rendering our structured data. The next step is to add a loading state. The useObject hook provides an isLoading flag. Let's destructure it and use it to disable the button while loading. So disabled is equal to isLoading. We can also disable the button if there is no dish name. We can update the button text to show progress. So if we are loading, the text is going to be generating. Otherwise, it's going to be generate. Next, let's add error handling. Destructure error from useObject, and in the JSX, right inside the container div, if there is an error, render a div with error.message with some Tailwind classes applied. Text red 500, margin bottom 4, and padding in the X direction 4. Finally, we can destructure the stop function from the hook to allow users to stop the streaming response if they want to. So destructure stop, and in the form, you can add a separate stop button, or you can also conditionally render either of these two buttons. In which case, this doesn't matter as much. So if isLoading, I'm going to paste the JSX for a stop button, and if it is not loading, we render our existing button. And this can be just generate. For the stop button, we have onClick is equal to stop. All right, there was a lot of code, but now it's time to see this in action. In the browser, navigate to /UI/structured data and try entering Margarita Pizza. Press enter. And you can see the AI generates the recipe with each part appearing as soon as it is ready. The dish name shows up first, Margarita Pizza, then ingredients, and then the steps as an ordered list. It's all properly structured data and not just text that we need to parse. Let's try another one, maybe chocolate chip cookies. Press enter. And see how the structure is always consistent. We always get the dish name and then ingredients with names and amounts, and then the numbered steps. Now I have used recipes as an example, but think about what else you could do with structured data. You could build product catalogs with prices, descriptions, and categories, analysis reports with data points and conclusions, task lists with priorities and due dates, quiz questions with multiple choice questions, and the possibilities are endless. The schema can be as simple or complex as you need. You can have nested objects, arrays of objects, optional fields, enums for fixed choices, numbers, dates, pretty much any data type you need. All right, that was a lot to learn, so let me quickly recap what we've built. First, we created a Zod schema to define exactly what structure we want from the AI. Then we used the stream object function in the route handler and used the schema property to let AI know of the structure we want. In the UI, we used the useObject hook to consume that structured data as it streams in. We use the submit function to make the API call, object to get the structured data, isLoading to show a loading state, and error to show an error message. Throughout the JSX, we make use of optional chaining to check if the data exists before rendering it. The key point here is that we're not asking the AI to format text in a certain way and hoping for the best. We're defining a contract, a schema, and the AI has to fulfill it. This makes our application much more reliable and code much cleaner. Now that we know how to generate objects from AI, let's explore two more patterns: generating arrays and working with enums. For arrays, we'll build a Pokemon generator. You type in a Pokemon type like fire or water, and the AI generates a list of Pokemon for you. For enums, we'll create a sentiment classifier. It analyzes text and tells us if it's positive, negative, or neutral sentiment. Pretty useful for analyzing user feedback. Since the code is very similar to what we did with structured objects, I already have both examples ready. Let me walk you through how they work. Let's start with arrays. In the API folder, I've created a structured array folder. Let me show you the schema first. Here's what's happening. First, we define what a single Pokemon looks like. It is an object with name and abilities. Name is a string, and abilities is an array of strings. But the key difference from our previous example is the UI schema. We directly wrap the Pokemon schema in z.array, and this tells useObjectHook we're expecting an array of Pokemon. But first, let's look at the route handler. You can see we're still using streamObject, but there's something new here. We're setting output property to array. When we generated objects in the previous example, we didn't specify any output type because object is the default value. But when you want arrays, you need to tell the AI SDK by setting output to array. Also, we pass the single Pokemon schema, not the array schema. The output type tells streamObject to generate multiple instances of our schema. The Pokemon type itself comes directly from the request body, which we include as part of the prompt. Generate a list of 5 fire, water, or electric type Pokemon. We stream the response to the UI using result.toTextStreamResponse. The UI is defined in the UI folder, structured array folder, page.tsx file. The pattern here is similar to objects. We use the same useObjectHook, but pointing to our new route /API/structured array. The schema also points to Pokemon UI schema. The difference is that we get back an array instead of a single object. So in the JSX, we map over object, we get hold of each Pokemon, render the name and the abilities. Since abilities is an array as well, we map over that too. Let me show you this in action. In the browser, navigate to /UI/structured array. Enter fire as the Pokemon type and hit submit. You get 5 fire type Pokemon with their abilities. Charmander with blaze and solar power, Vulpix with flash fire, and 3 more. Try water or electric, and each time you get a properly structured array which we can map over to display the Pokemon and their abilities. Alright, now let's take a look at enums. And this works a bit differently. So in the API folder, I've created a structured enum folder with a route.ts file. First, you can notice that we are using generateObject and not streamObject. Enums is only available with generateObject. We set output to enum and provide the possible values directly using the enum property: positive, negative, or neutral. No need for a separate schema. The next important difference to note here is that I'm using GPT 4.1 Mini instead of Nano. For enum outputs, the more capable models tend to be more consistent in generating the correct enum value. I've found Nano having problems trying to stick to the enum values, so make sure you remember to use the more capable model. Finally, notice we're using to JSON response and not to text stream response. Enums return a single value and there is no need for streaming. The UI is defined in UI folder, structured enum folder, page.tsx. The UI component is also quite different. Since we are not streaming, we don't use the useObject hook. Instead, we use a regular fetch request and useState hook. We manage the input text, sentiment, which is the response from our AI, a loading flag, and error message. Analyze sentiment makes a fetch request to /API/structured-enum, method post, content type, application JSON, body, we send the input text, and once we get hold of the data, we set the sentiment as data to render in the UI. In the JSX, we display the error. If it's loading, we say analyzing sentiment, and if the sentiment exists, we render the sentiment as positive, negative, or neutral. We have the same form, layout, and structure. On submit, we call analyze sentiment. We have our div, our input, enter text to analyze, and a button to analyze that is disabled when loading. You can try this at /UI/structured-enum, and you can enter the text amazing product. Press enter, and you get positive. Now try, this is terrible. This gives you negative, and finally, it's okay. This returns neutral. We're able to classify the sentiment in the text using OpenAI. All right, let me quickly summarize the key patterns here. Array schemas get wrapped in a Zod array and exported as a UI schema. Enums don't require a separate schema. Arrays use stream object with output type arrays and require a schema. Enums use generate object with a list of possible values instead of a schema. Arrays give you back an array of objects from useObject. With enums, you manage it manually and don't require useObject. All right, we've expanded our structured data toolkit. Arrays for multiple items and enums for classification. Combined with object generation from before, you can get any data structure you need from AI. I recommend playing with these examples. Try different Pokemon types, different text for sentiment analysis. See how the AI handles edge cases. It's a great way to get comfortable with Zod and see what these patterns can do. The code is on GitHub if you want to experiment. Up until now, we've been working exclusively with text-based interactions. We've generated responses, built chat conversations, and even created structured data. But modern AI models can handle much more than that. Today, we'll explore multimodal capabilities. Multimodal means the AI can understand and process different types of content. In addition to text, we can work with images, PDFs, audio files, and more. In this lesson, we'll focus on image analysis. Then in the next lesson, we'll move on to PDF processing. Let's jump into VS Code and see how to analyze images with the AI SDK. Let's start by creating the route handler. So navigate to the API folder and create a new folder called Multimodal Chat. Now here's something interesting. Remember the chat route handler we built earlier? We can actually reuse this exact same code for image analysis. The AI SDK handles both text and images, so we don't need to write any special logic. Let's copy this route.ts file from the chat folder and paste it into our new multimodal chat folder. I will, however, simplify the messages property. And for the sake of simplicity, let's also remove the token usage code. We define an async post request handler. We extract messages from the request. We call stream text, passing in model and messages. And we return result.toUI message stream response. This is all the code we need for the backend. The same code that processes chat messages will automatically handle images when we send them. Now let's build the UI component. In the UI folder, create a new folder called Multimodal Chat with a page.tsx file inside. We will use the chat UI component as our starting point since most of the functionality is similar. So copy the code from UI/chat/page.tsx and paste it into multimodal chat page.tsx. First, let's update the component name from chat page to multimodal chat page. By default, useChat makes a request to /API/chat. Our API, however, lives in multimodal chat. So let's correct the API endpoint. For that, we rely on the default chat transport class from the core AI package. So import it at the top. Import default chat transport from AI. As an argument to the useChat hook, we pass a transport object with the API endpoint. So transport is the key. The value is new default chat transport. And to this, we specify API/multimodal chat. This will send the messages to the new route handler. All right, now comes the interesting part. We need to enable file uploads in this form. To handle files properly, we will need to track two things: which files are selected and a reference to the file input. At the top, let's import useRef along with useState. Inside the component, let's set up our state. First, we'll track the selected files. So useState, the state variable is files, the setter function is setFiles, and the initial value is undefined. This is going to be of type file list or undefined. File list is the browser's type for file selections. Next, we need a reference to the file input element. So const file input ref is equal to useRef with an initial value of null, and the type is HTML input element. This will allow us to programmatically clear the file input after submission. Now let's modify the form to support file uploads. Currently, our form has one input and button side by side. We need to add a file attachment option, so let's restructure the layout to stack elements vertically. Inside the form element, wrap the form children in a new container. So div class name is equal to flex column cap 3. This creates a vertical layout with spacing between our existing input plus button and the new file attachment UI we'll add in a second. And while we're at it, let's also adjust the main container padding. So find the padding y24 class and change it to padding top 12 and padding bottom 36. This gives us more room at the bottom of our expanded form. All right, now for the file attachment feature. Above the existing input and button div container, but inside our new flex column container, let's add an attachment button. Div tag with a label inside, and the attachment icon and text will go here. On the label, we will set HTML4 is equal to file upload. We'll then add some Tailwind CSS to make this pretty. So on the div, class name, flex, item center, cap 2. And on the label, we specify more classes. We're using a label element styled as a button. The HTML4 attribute will connect it to our file input. Within the label, let's add a paperclip icon inside. I'm going to paste an SVG icon, but feel free to just type the text attach. After the icon, let's add text that changes based on whether files are selected. So curly braces, if files exist and files are selected, we render $curly braces, files.length, file or files based on the number attached. Otherwise, we render attach files. So this shows attach files by default, or the number of files if any are selected. Now we need the actual file input. So after the label, still inside our div flex container, we add a new input element. We specify ID is equal to file upload. So this matches our label HTML4 attribute. Type is equal to file. Class name is equal to hidden. So this is a Tailwind CSS class which will hide the input element. On change, event, and if event.target.files exist, set files event.target.files. We will also set the multiple attribute, and then ref is equal to file input ref. Quite a few attributes, so let me explain one more time. The ID, file upload, matches our label's HTML4, So clicking the label opens the file picker. We hide the input with class name is equal to hidden because we're using the styled label instead. The onChange handler updates our state when files are selected. The multiple attribute allows selecting several files at once. And we attach our ref so we can clear the input programmatically later. Now that we have our file input, the next step, we need to update the form submission to include the selected files. Let's look at the current handle submit function. You can see currently it only sends text, but the send message function can accept both text and files. Let's update it. Text :input and files set to our state variable files. With ES6 shorthand syntax, we can specify just files. We are now passing files along with the text to our API endpoint. But we should also clear the file selection after sending. So set files to undefined, and then the file input element itself needs to be cleared too. If file input ref dot current dot value is equal to empty string. So if the ref exists, clear its value. All right, now the form properly handles both text and file submissions, clearing everything after each message. The last step is updating our messages display to show images. Now you should know that files are part of message parts with a type equal to file. In the route handler, if you inspect the UI message type, you will see that it has a parts property, and that is an array of type UI message part. And UI message part is a union of several types. We already had a look at the text UI part earlier. Type is set to text, and text is the text content. Now let's inspect the file UI part. You can see this has type set to file, and media type is the MIME type of the file, for example, image/JPEG. File name refers to the actual file name, and URL is the URL of the file. It can be both a local file or a remote URL. But now that you understand this file part structure, let's look at the message rendering code, which seemed like an overkill when dealing with text. We have message.parts.map, and we have a switch statement that processes different part types. Currently, it only handles text. Because we did this verbose implementation earlier, supporting files is now straightforward. After the text case, add case file return null. But we want to display images, not return null. So let's check if the file is an image. File parts include a media type property as we just saw. So if part.mediatype exists, we check if it starts with image/. This covers all image formats like image/JPEG, image/PNG, etc. So if it's an image, we render it using Next.js image component. Make sure to import image from next/image. We set key is equal to $curly braces, message.id, followed by index to make sure this is unique. We set source is equal to part.url, since each file part provides a URL for the source. And optionally, we will set file name for accessibility. So part.filename. And if that doesn't exist, attachment followed by index. We will set width to 500 and height to 500, but you can adjust these values. Make sure to return the image component. All right, our page component is now ready to handle images. Let's test this out. In the browser, navigate to /UI/multimodal chat. And now you should see the same UI as the chat page, but with a file attachment button. Click Attach Files and select an image. I have attached one of my YouTube thumbnails, and you can see the text updates to one file attached. Type something like, "What's in this image?" and hit enter. You'll see your image appear in the chat. This is followed by AI's analysis. For my question, "What's in this image?" the AI responds with, "This image appears to be a graphic or presentation slide related to Next.js, a popular React framework. It has a black background with white text. The text stream text is in the top left corner, and Next.js is prominently displayed in large font in the center, with some sparkles or star icons next to it. There's a photo of a smiling man on the right-hand side of the image, outlined in white with dark hair and a goatee, wearing a black shirt. The overall design looks modern and tech-oriented. As you can see, the model can see and understand the image content, allowing for natural conversations about what it sees. You can try follow-up questions, ask about specific details or colors on the image. The AI maintains context and can discuss the image throughout the conversation. All right, let me quickly recap what we've implemented. We started with a route handler that was pretty much a copy of our existing route handler from the chat route. The AI SDK's design means our existing chat handler supports images as well. For the UI, we improved the chat interface with file upload capabilities. We used useState to track selected files and useRef to manage the file input element. We created a file attachment button that shows the upload status. The form submission now handles both text and files, passing them together to the send message function. We made sure to clean up properly by clearing both the state and the input element. Finally, we extended the message rendering to display images. By checking the part type and media type, we can show images in line with the conversation. For our next topic, let's learn how to process PDFs with the AI SDK. In the previous lesson, we built a multimodal chat that can analyze images. Now, let's add PDF support. If our AI can read and understand PDF documents, users can ask questions, get summaries, or extract specific information without reading through dozens of pages. Super useful feature and super easy to implement with the AI SDK. Let's start with the route handler. Remember, when we added image support, we didn't have to write any additional code. Same story for PDFs. Our multimodal chat route handler already handles PDFs because the AI SDK automatically takes care of processing them. All we need to do is update our UI to display PDFs in the chat. So let's do that. Open the multimodal chat page.tsx file and find the switch statement where we handle message parts. We've got cases for text and file types. For the file case, right now we are checking if it's an image, and if it is, we render it using the image component. If it's not an image, we return null. But we want to handle PDFs too. So right after the image if block, let's add another check for PDFs. Part.mediatype.starts with application/PDF. PDFs have a media type that starts with application/PDF, so we check for that just like we did for images. Inside this if block, we need to render the PDF. Now for PDFs, we will use an iframe. Browsers have built-in PDF viewers, so an iframe works perfectly for displaying PDFs. Now let's add the attributes. First, the key for React. So key is equal to $curly braces, message.id, followed by the index. So $curly braces index. Then the source URL. So source is equal to part URL. And this is the URL where the PDF is hosted. Same pattern as images. Then let's set the dimensions. Width is equal to 500 and height is equal to 600. Feel free to style the iframe as you see fit. Finally, add a title for accessibility. So title, if part.filename exists, render that. Otherwise, attachment followed by index. That's it. The file case now handles both images and PDFs. Let's test this. In the browser, navigate to /UI/multimodal chat and click Attach Files. But this time, select a PDF file. Could be anything, a report, documentation, flight tickets, whatever PDF you have. I have attached the landing page for AI SDK docs as my attachment. The text now reads one file attached. In the input, type something like, what's this document about? Or summarize the main points and hit enter. I had to reset the zoom to accommodate this iframe, But you can see the PDF is rendered in your chat, our prompt, what's this document about? And we get the AI response. This document provides an overview of the AI SDK by Vercel, a TypeScript toolkit designed to help developers build AI-powered applications across various frameworks and providers. You can try asking specific questions. What does page 2 talk about? The AI reads through the PDF and gives you the appropriate answers. You can see the AI respond to page 2 discusses the supported AI model providers integrated with the AI SDK. With PDF support, you can build all sorts of document analysis tools, contract review systems where users upload agreements and ask about specific clauses, research assistants that help parse through academic papers, documentation Q&A bots for technical manuals, and more. The same file attachment flow works for both images and PDFs. Users can even attach multiple files, mix images and PDFs in one message if they want to. The AI processes everything and each file renders correctly in the chat. So now we have a multimodal chat that handles text, images, and PDFs. We've seen how AI can analyze images and PDFs, but AI can do something even more impressive. It can create images from scratch based on text descriptions. For this next lesson, we'll build an image generator with the AI SDK. There are quite a few image generation models available, but for this course, we will use DALL-E 3 from OpenAI. It's not the best model available, but it is one of the cheapest. Once you understand how image generation works, you can always upgrade to more sophisticated models based on your needs and budget. Like all other lessons, we'll tackle this image generator in 2 parts. First, we'll create a route handler to communicate with DALL-E. Then, we'll build a UI where users can enter prompts and see the generated images. Back in VS Code, in the API folder, create a new folder called Generate Image. Inside, create a route.ts file. Start with the post handler that accepts a request parameter. So export async function, post, request of type request, and then add the imports we need. Import OpenAI from AI SDK/OpenAI and the generate image function. Experimental generate image from AI. It is marked as experimental, but by the time you're following this tutorial, it might be stable, so check the documentation. We will, however, import it as an alias, as generate image. Within the post handler, get the prompt from the request. So destructure prompt by awaiting request.json. Now we will call generate image with the configuration. So await generate image. We pass in an object, and first we specify the image model we want to use. Property is model, and we call OpenAI.imageModel, and we specify DALL-E 3. Then we pass the prompt from the request. So prompt, key, and value both are the same. Now for image generation, we can also specify the dimensions of the image using the size property. Let's set it to 1024 by 1024. Finally, we pass any optional provider options. So provider options. And in this case, we'll use the OpenAI provider and set the style to vivid and quality to HD. Style, vivid, quality, HD. The generate image function returns an object with the generated image, which we can destructure and return as JSON. So const image destructured by awaiting generate image and return response.json image.base64. We're returning the base64 encoded image data, which the browser can display directly. Finally, let's wrap everything in proper error handling. So try, close it after response, catch block, get access to error, console.error, error generating image, log the error, and return new response, failed to generate image. Status 500. The route handler is ready. Now for the UI. In the UI folder, create a new folder called generate image, and inside, create a page.tsx file. Let's start with the basic component structure. We will use the exact same layout as our other pages, so I'm going to paste the code to save us some time. We have the useClient directive at the top since this is a client component. The component name is generateImagePage. We'll start with a container div that centers the content and adds some padding. We'll leave space for the image to be displayed. So image will go here. At the bottom goes the form. We add a flex container with an input and a send button side by side. All elements are styled with Tailwind CSS to look nice, and you can copy these styles from any of the previous pages. The code, of course, is also available on my GitHub repository, and the link is in the description. You can see this UI in the browser by navigating to localhost 3000/UI/generate-image. You can see the form at the bottom and space at the top to render our image. The next step is to make our form interactive. So at the top, import useState from React. Within the component, create a new prompt state variable. Prompt, set a function, setPrompt, and the initial value is an empty string. Bind this to the input field. Type is equal to text, value is equal to prompt, and on change, we get hold of the event and we call setPrompt, passing in event.target.value. Let's also make the placeholder describe the image to suit the component. Value is not a string, but the state variable. Next, let's add the functionality to call our API. We'll need more state variables and a submit handler. So use state. First, we need image source and set image source to store the generated image source. The initial value is null and the type is string or null. Next, we need isLoading and set isLoading with an initial value of false. So the type is Boolean, and this is for loading states. The third state variable is error. The setter function is setError, and the initial value is null. The type is string or null, and this is for error handling. Next, we define our submit handler. So const handle submit is equal to an async function. The function receives an event that is of type react.formEvent, HTML form element, and within the function body, first we prevent the default submission. So event.preventDefault. Next, we set the loading state, so set isLoading to true. Clear any previous image, so set image source to null, and reset the input, set prompt to an empty string. We will also clear any errors if they've been previously set. Then in a try block, make a fetch request to our API with the prompt. So const response is equal to await fetch. The endpoint is /API/generateImage, which is the route handler we just created. Specify an options object. The method is post. Headers, we set content type to application JSON, and then body is the prompt. JSON.stringify an object with key and value set to prompt. Await the response and then the data. So await response.json, and we assign this to a constant called data. If the response is not OK, throw an error with the error message or a generic error message. So if not response.OK, throw a new error, data.error, or something went wrong. If the request was successful, convert the base64 response you get back from the API into a data URL that the browser can display. Set image source, backticks, data, :image/png, :base64, $curly braces, data. And then we add a catch block for error handling. So error, console.error, error generating image, followed by the error, and set error, error instance of error. And we do this for TypeScript error.message. Otherwise, something went wrong. Please try again. Finally, we clean up the loading state. Set isLoading to false. Now, our handle submit is complete. So let's connect this to our form on submit is equal to handle submit, and then update the JSX to render content based on the state variables. For the button, we'll add disabled, and this is going to be equal to isLoading. I will also update the classes to account for disabled state. And while we're at it, let's change the button text to say generate instead of send. Next, at the top, we render the error message. So within the outer div container, error, and if that exists, we render the error. We'll also add tailwind classes. Text red 500, margin bottom 4. If there is no error, we render the image. Curly braces again. First, we need to handle the loading state. So if it is loading, we're going to add a div tag that reflects a loading state with animate pulse class. And if it is not loading, we check if the image source exists, and if it does, we render the image component. Image, which we are going to import from next/image, so make sure to import it at the top. We set alt to generated image. We're going to add some tailwind classes for styling. Source is equal to image source, width 1024, which we specified in our route handler, and the same for height. And we will wrap this content in a div tag. We will add some tailwind classes to make sure the loading state is displayed. When loading, we show a pulsing gray box, and when not loading, we show the image if it exists. All right, our UI is now complete. Navigate to /UI/generate. We should see the placeholder, describe the image, and the generate button. Describe the image, a realistic corgi dog. When you press enter, you should see the loading state. Please note that image generation takes at least 5 to 10 seconds. And there you go. We have an image that is AI generated based on our prompt. Remember, DALL-E 3 is not the best model. While we did get a corgi dog, the realistic part is a bit questionable. The more recent and advanced models can generate very realistic images. And the more descriptive your prompt, the better the results. You can include details about style, lighting, colors, and even composition. Please remember that image generation can be way more expensive than text generation. So keep an eye on your usage dashboard during development. If you have the budget, I highly recommend swapping DALL-E 3 from OpenAI for one of the better models. Trust me, the results will be night and day. But to summarize what we've learned, we created a route handler that communicates with DALL-E 3 image model using the OpenAI.imageModel method. We specify dimensions and provider options like style and quality. We return the base64 encoded image data as response. In the UI, we make a post request to the route handler and handle the response. We display the image using the image component from Next.js. We also handle loading and error states. We are able to generate images using AI. Now, what's really cool is that AI can transcribe audio with incredible accuracy. It handles different accents, background noise, even multiple languages all automatically. And with the AI SDK, adding this capability is just as straightforward as the other features we've been working with. For this lesson, we'll build an audio transcription feature that can take any audio file and convert it to text. We will follow our usual approach. First, create a route handler to process audio files using AI SDK. Then, build a UI for uploading audio and displaying transcripts. Let's start with the API route. Back in VS Code, in the app folder, in the API folder, create a new folder called Transcribe Audio. Inside, create a route.ts file. Start with the post handler that accepts a request parameter. Export, async function, post, request of type request. Now let's add the imports we need. Import OpenAI from AI SDK/OpenAI and the transcribe function. You can see it's marked as experimental, but it works great for our needs. By the time you're watching this, it might be stable, so check the documentation. We will, however, import it as transcribe. Now, audio transcription is different from our previous endpoints. Instead of receiving JSON with text, we'll receive a file upload. Let's handle that. We parse the request as form data, which is how browsers send file uploads. So const form data is equal to await request.formData. Then we extract the audio file. Const audio file is equal to formData.get audio as file. The field name audio is what we will use in the front-end form. Next, let's add validation to make sure we have actually received a file. So if there is no audio file, return new response, no audio file provided, the status of 400. Next, we have an important step. The transcribe function needs the audio as a uint8 array and not a file object. So we need to convert it. First, we convert the file to an array buffer. So const array buffer is equal to await audio file dot array buffer. And then we create a uint8 array from that buffer. So const unsigned int array is equal to new uint8 array, and we pass in the array buffer. This gives us the raw audio data in the format the AI needs. Now we can transcribe the audio. Await transcribe. We pass in an object. We set the model to OpenAI dot transcription Whisper1. Whisper is OpenAI's speech recognition model, and it's good at transcription. Next, pass in the audio data we just prepared. So audio set to uint8 array. Capture the result in a constant called transcript and return it as JSON. Return response.json transcript. Let's make sure to wrap everything in proper error handling. So try block, catch the error, console.error, error transcribing audio, and log the error, and then return new response, failed to transcribe audio. Status 500. Our route handler is now ready. It accepts audio files, converts them to the right format, transcribes them using Whisper, and then returns a result. Now for the UI. In the UI folder, create a new folder called transcribe audio, and inside, create page.tsx. We'll start with the basic component structure. We're using the same layout as our other pages, so I've pasted the code. Use client directive, since this is a client component. The component name is transcribe audio page. We have a div container. The transcript will go at the top, and then the form is fixed to the bottom. For audio transcription, we need to handle file uploads differently than text input. So let's set up the necessary state and refs. First, import useState and useRef from React. Within the component, we will define all the state variables. First, we have isLoading and setIsLoading, initial value of false for the loading state. Next, we have error, setError of type string or null, initial value null. This is for error messages. Next, we have transcript, setTranscript with an initial value of null. This is for transcription results. The type is transcript result or null, and we'll define this type in just a bit. Next, we have selected file and set selected file, initial value null, and the type is the browser file type or null. This is to store the actual file object that is selected. Finally, we define file input ref is equal to useRef of type HTML input element, and the initial value is null. This is to access the file input element. We do have a TypeScript error for transcript result, so let's define the TypeScript interface. Interface transcript result, and this includes the full text so text of type string, and based on the model, it can also include optional segments. So segments, question mark, since it is optional. And this is going to be an array of start of type number, end of type number, and text of type string. It can also include the detected language, which is a string, and the duration in seconds, which is of type number. Now that we have all the necessary state and refs, let's create the file input. Inside the forms flex container, input ref is equal to file input ref, type is equal to file, accept is equal to audio files only, class name is equal to hidden, and ID is equal to audio upload. We hide this actual input because we will create a better looking label. The accept attribute limits the selection to audio files only. Now let's add a styled label that acts as our upload button. So right below the input, label, and based on whether a file is selected, we'll display either change file or select audio file as the text. This label is for the input with ID is equal to audio upload. We'll then add a bunch of tailwind classes to make this look pretty. You can style the label as you see fit, but this code right here is on my GitHub repo. All right, next to the label, we will add the transcribe button. So button, the text is transcribe, type is equal to submit, and this button is disabled when loading. So if is loading is true, or when no file is selected. So no selected file. I will also add some tailwind classes to make this button look pretty. We will wrap the input, label, and button with another div tag. And on this div, we'll add flex gap2 to make sure the input and button are placed side by side. Now let's implement the form submission. Const handle submit is equal to an async function. We get access to event, which is of type react.form event, HTML form element. And within the function body, we prevent the default submission. So event.prevent default. Check that a file is selected. So if not selected file, set error. Please select an audio file, early return. And then if it is selected, we set up the loading state. Set is loading to true, and we clear out any error that was previously set. Next, we make the API call. Within a try block, const form data is equal to new form data. Form data dot append audio is the string. Selected file is the value. With this form data, we make the fetch request. So const response is equal to await fetch. The API endpoint is /API/transcribe audio, which we just created. Options, we set method to post, and then body to form data. We don't set content type headers as the browser handles that automatically for form data. If the response is not okay, we throw a new error. Failed to transcribe audio. If the request was successful, so const data is equal to await response.json, we update the state with transcript and we clear the selected file and reset the input. So set transcript to data, set selected file to null, and if file input ref dot current, we reset it. Current dot value is equal to empty string. We then add a catch block where we log the error to the console and set the error message. If error instance of error, we call set error with error.message. Otherwise, something went wrong, please try again. Finally, we can reset isLoading to false. Now let's connect this handler to the form. Form on submit is equal to handle submit. Right, now that we are able to make the request, let's display the results that we get back. In the JSX, above the form element, add the UI for showing transcripts. So if the transcript state variable exists, and isLoading is false, which means to say the fetch request has completed successfully, we render a div tag with an h3 that says transcript, then a paragraph tag that renders transcript.text. We will also add tailoring classes to make this look pretty. Now you can optionally add JSX to show the language if it exists, and also the duration if it's available. Transcript.duration in seconds. Next, add loading and error states above the transcript display. If the error exists, render a div tag with the error, and if isLoading is set to true, render a div tag with the text transcribing audio. And finally, for a nice touch, let's share the selected file name and allow clearing it. Above the file input controls in the form, curly braces, if selected file exists, render a div tag with a span tag that says selected followed by selected file.name and a button that says remove. Button type is equal to button. On click is equal to a function called resetForm, which we will define in a bit, and we will add styles to the div tag as well as the button. Let's implement the reset function. ResetForm is equal to set selected file to null, set transcript to null, set error to null as well, and if file input ref exists, we clear that too. .current.value is equal to an empty string. This clears all state and resets the file input. All right, the final part, which I forgot to implement earlier, is to handle the onChange event on the input. So onChange is equal to handle file change, and let's define this function as well. Const handle file change is an arrow function. We get access to event, which is of type react.changeEvent. This is HTML input element, and within the function body, const file is equal to event.target.files of 0, and we access it only if it exists. And if a file exists, set selected file to this file, set transcript to null, so we reset the UI, and we also set error to null. All right, that was a lot of code, but our UI is now ready. Let's test it out. In the browser, navigate to localhost 3000/UI/transcribe audio. We should be able to see our form at the bottom. We have a select audio file label and a transcribe button, which is currently disabled. Go ahead, click select audio file, and choose an audio file from your computer. You can use any audio file. I've selected an MP3 file with the name sample audio, and this is displayed right above the form. We also have remove button, which removes the selected file. All right, I have reselected the file, and this audio file is basically a small segment from one of my other videos. Click transcribe. We see the loading state transcribing audio. And when the speech to text process is complete, you will see the full transcript, and if the model supports, the detected language and audio duration. Whisper doesn't support that, so we just see the full transcript text. I can confidently say this transcription is pretty accurate, but let me know in the comment section how close was your transcription for the audio file you attached. Audio transcription opens up many possibilities: meeting transcription services, podcast search engines, voice note-to-text converters, video subtitle generation, interview transcription tools, and a lot more. Keep in mind that audio files can be large, so you might want to add file size limits in production. Also, longer audio files take more time to process and cost more in API usage. While testing, please make sure to include short clips that are only a few seconds long. All right, let's quickly recap what we built. We created a route handler that accepts audio file uploads through form data. We convert the file to a uint8 array format that the AI can process. Using OpenAI's Whisper model, we transcribe the audio and return the results. For the UI, we built a file upload interface with proper state management. We show the selected file, handle the upload process, and display the transcript with metadata like language and duration. The AI SDK makes audio transcription surprisingly simple. Just a few lines of code to add powerful speech-to-text capabilities to your app. For our next lesson, let's go in the other direction and learn how to generate speech from text. We just built a feature that converts speech to text. Now, let's flip it around and do the opposite. Convert text to speech, or TTS for short. The AI SDK supports speech generation just like everything else we worked with. We will use OpenAI's text-to-speech model, which produces great natural-sounding voices. We will follow a familiar pattern. First, create a route handler that converts text to audio using AI SDK. Second, build a UI where users can type text and hear it spoken. Back in VS Code, start by creating the API route. In the API folder, create a new folder called Generate Speech, and inside, create a route.ts file. Begin with the post handler that accepts a request parameter. So export async function, post, request of type request, curly braces. Next, let's add the imports we need. Import OpenAI from AI SDK/OpenAI and the generate speech function from the core AI package. This is experimental, so experimental generate speech as generate speech. It is marked as experimental, but don't worry, it works perfectly fine. Now for this endpoint, we will receive text that needs to be converted to speech. So extract the text from the request body. Await request.json. Nice and simple. Now let's generate the speech. We use the generate speech function with OpenAI's text-to-speech model. So property model, we set it to OpenAI.speech and specify TTS-1. We then pass in the text we want to convert to speech. So text, key and value being the same. The function returns an audio object. Await generate speech, and from the result, destructure the audio object. Send this audio back to the client. Return new response, audio.uint8 array, and then we set headers, content type, audio.media type, or the string audio/mpeg. We set the content type header to tell the browser this is audio data, and the audio object includes the media type, but we fall back to audio/mpeg just in case. Let's wrap everything in error handling. Try block, catch the error, console.error, error generating speech, and return new response, failed to generate speech, with a status of 500. And that's it for our route handler. It takes text, generates speech, and returns that audio data. Now for the UI, we'll build it in 2 stages. First, we'll create a basic version that plays the audio once. Then we will improve it with replay functionality. In the UI folder, create a new folder called Generate Speech, and inside, create a page.tsx file. Start with the component structure. Very similar layout pattern to our previous pages. We start with use client directive since this is a client component. The component name is generate speech page. We have a div container. The audio UI will appear at the top, and then the form is fixed at the bottom. Now let's set up the state we need. First, import useState from React, and within the component, we're going to define 3 state variables, text and setText with initial value empty string, and this is for the input. Next, isLoading and setIsLoading, initial value false. This is for our loading state. Finally, error, setError, and the initial value is null. The type is string or null. This is for our error messages. Now that we have the state, let's add the text input inside the form. So HTML input, I'm going to copy paste Tailwind classes to make this look pretty. The placeholder is going to be enter text to convert to speech. Type is equal to text. value is equal to the state variable text. On change, we get hold of the event and call setText, passing in event.target.value, and we disable it when isLoading is true. So a standard controlled input that updates our text state. We disable it while loading. Next, add the generate button next to the input. So button, the text is generate, type is equal to submit, disabled is equal to if isLoading is true, or if there's no text in the input field. I will also paste Tailwind classes to make this look pretty. Now that we have the form, let's implement the form submission. The function is handleSubmit, so const handleSubmit. And this is an async function that takes an event of type react.formEvent HTML form element. In the function body, we prevent default submission, so event.preventDefault, set loading state, so set isLoading to true, clear any previously set errors, so set error to null, and clear the input as well. So set text, empty string. After clearing the input, let's make our API call. Try block, const response is equal to await fetch. The URL is /API/generate speech, which is the endpoint we've just created. And for options, method, set to post, headers, content type, application, JSON, and body, JSON.stringify, we pass in an object with key and value set to text. If the response is not OK, we throw a new error, failed to generate audio, and we will handle the error. So catch error block console.error generating audio, followed by the error, and then we call set error. If error instance of error, we set error.message. Otherwise, something went wrong, please try again. And this is an uppercase E. And now for the important part. Let's handle the audio response. So inside the try block, after checking the response is OK, we get the audio data as a blob. The const blob is equal to await response.blob. Then we create a URL for it. So const audio URL is equal to URL.create object URL, passing in the blob. And then we create an audio element. So const audio is equal to new audio, passing in audio URL. Once we have the audio, we play it immediately. So audio.play. Finally, we clean up the URL when the audio finishes playing. So audio.add event listener. The event is ended, and we execute a function where we call URL.revoke object URL, audio URL. Very important to avoid memory leaks. Next, connect the submit handler to the form. So onSubmit is equal to handleSubmit. Next, add loading and error states above the form. If there is an error, render a div tag with that error. And if isLoading is true, render a div tag that says generating audio. Perfect. Our component is now ready. Time to test it out. In the browser, navigate to /UI/generate speech, and you should see the form. Enter text to convert to speech and the generate button. Type some text like, hello, this is a test of AI speech generation, and press generate. Looks like something's wrong, so let's go back to our code. And the problem is I've misspelled our API endpoint. This should be generate speech. And I also noticed the loading flag was never reset. Let's add a finally block, set isLoading to false. All right, let's go back to the browser, refresh, enter the text, hello, this is a test of speech generation. Press enter, and our AI will convert the text to speech.
Hello, this is a test of speech generation.
You can see that the audio will play once, and then the memory is released when it's done. We have completed the first version of our component. We're able to convert text to speech. Now let's improve it to allow replaying audio. This requires more careful resource management since we need to keep the audio around. First, we need to import useRef and useEffect from React. Add refs to store our audio resources and a state for tracking if we have audio. So state has audio, set has audio, and initially the value is false. Then for the refs, const audio URL ref is equal to useRef. The type is string or null, and the initial value is null. And then const audio ref, useRef. The initial value is null, and this is of type HTML audio element or null. Next, we need to update our handle submit function to properly manage these resources. So before we call our API, if audio URL ref dot current exists, URL dot revoke object URL audio URL ref dot current, and then audio URL ref dot current is equal to null. Along similar lines, if audio ref dot current exists, audio ref dot current dot pause, audio ref dot current dot source is equal to an empty string, and audio ref dot current is equal to null. So if an audio is currently being played when you enter a new prompt, we pause that audio, clear it, and we get ready with a new fetch request. And here in our try block, blob is equal to await response.blob. Instead of audio URL, this is going to be audio URL ref dot current is equal to URL dot create object URL. And then instead of const audio, audio ref dot current is equal to new audio. And we pass in audio URL ref dot current. Audio dot play becomes audio ref dot current dot play. We'll also set has audio to true, and in the catch block, we'll set it to false. We will comment out the ended event listener because we're not cleaning up immediately anymore. The audio stays available for replay. Now add the replay functionality. So const replay audio is equal to a function if audio ref dot current exists, audio ref dot current time is equal to 0, and audio ref dot current dot play. This resets the audio to the beginning and plays it again. Add a replay button to the UI. So above the form, we make use of the has audio state variable. And if you are currently not loading, so if is not loading, we render a button. Text is replay audio. On click, we call replay audio, which is the function we just defined. And I'm going to paste the Tailwind classes. The button only appears when we have audio and we are not loading. Finally, and this is crucial, we need to clean up when the component unmounts. So useEffect, we pass in a function and we return the cleanup function. Here, if audio URL ref dot current exists, URL dot revoke object URL, audio URL ref dot current, and then if audio ref dot current exists, audio ref dot current dot pause, and audio ref dot current dot source is equal to an empty string. We specify empty dependency array as we want this to run only when the component unmounts. Now let me explain why this cleanup is so important. When we create an object URL with url.createObjectURL, the browser allocates memory for that blob. If we don't call revoke object URL, that memory stays allocated even after we are done with the audio. Similarly, audio elements can keep playing even after the component unmounts if we don't explicitly pause them. That is why we clean up old audio before creating new video, clean up everything when the component unmounts, and properly pause and clear audio sources. This might seem like overkill for a simple demo, but in a real app with many users generating audio, proper cleanup prevents memory leaks and performance issues. All right, let's test this complete implementation. Back in the browser, type some text. Hey, how are you? Press generate and listen.
Hey, how are you?
The AI converts your text to natural sounding speech and plays it automatically. But after generation, you'll see this replay audio button. Click it
Hey, how are you?
to hear the speech again without AI regenerating. And while we're using the default voice here, OpenAI's text-to-speech model actually supports multiple voices. You can refer to the docs for more information. And as opposed to this simple UI, in your own app, you could also add features like a download button to save the audio file, speed controls to make speech faster or slower, a voice selection dropdown, and any other feature as per your requirements. All right, let's recap what we've built. We created a route handler that accepts text and uses OpenAI's text-to-speech model to generate speech. The audio data is returned as a binary response with the appropriate content type. For the UI, we built it in 2 stages. First, a basic version that plays audio once with automatic cleanup. Then an enhanced version with replay functionality. We learned about proper audio resource management using refs for audio elements, cleaning up object URLs, and ensuring resources are released when components unmount. The combination of speech to text and text to speech opens up possibilities for voice-driven interfaces. You could build apps where users speak commands, the AI processes them as text, then responds with synthesized speech, which is a complete voice interaction loop. What used to require complex audio processing libraries is now just a few function calls away with the AI SDK. All right, that wraps up our first half of the course on the fundamentals of building AI applications with Next.js and the AI SDK. In the next half, we'll dive into some of the more advanced topics. You've probably used ChatGPT or Claude for all sorts of things, explaining concepts, writing code, or generating text. And it works great for most things. But when you ask something like, what's the weather like in Tokyo right now? Or what's the current stock price of Apple? The AI will apologize because it can't give you the answer. LLMs have been trained on a dataset with a cutoff point and don't have access to the outside world. This is where tools come in. Tools are actions that the AI can invoke. Technically, they are special functions you give to the AI to perform specific tasks that go beyond their training data. When the AI recognizes it needs information it doesn't have, it can call these tools. But here's the key. The LLM itself doesn't execute the function. Instead, it identifies which tools to use, figures out what parameters to pass, and returns this information in a structured format. Your application then runs the actual function and gives the result back to the AI to be considered in the next step of the response. The beauty is that users can interact with complex systems using natural language while the AI handles all the orchestration. You ask in plain English, the AI figures out which tool to use, calls it with the right parameters, gets the result, and gives you a natural response. Now this seems more complex than it is, so let's dive into an example. Let's give our AI chatbot a weather tool to use. We will use hard-coded weather data so we can focus on understanding the syntax and mechanics, but we will cover tool calling with external APIs and external systems in an upcoming lesson. Let's start by setting up our files based on the chat implementation from earlier in the course. So in the source folder, in the API folder, create a new folder called tools. Copy the route handler from the chat folder and paste it into the new tools folder. We can remove the system prompt and the token usage code to keep it simple. Similarly, in the UI folder, create a new folder called tools with a page.tsx file. Copy the code from UI/chat page.tsx and paste it here. Update the component name to tools chat page and the API endpoint. So use chat, we pass in an object, we define our transport, which is new default chat transport. That has to be imported from the AI package. And we specify API, path is /API/tools. This is the route we've just defined. Perfect. We should now have a working chat interface. Let's test it out. In the browser, Navigate to localhost 3000/UI/tools. Try asking, what is React? Works great. The AI explains React perfectly. Now refresh and try asking, what's the weather like in Tokyo right now? You'll see the AI can't answer because it doesn't have access to the outside world. The AI is smart enough to understand what you're asking, but can't actually get that information. So let's learn how to add a weather tool to our chat so the AI can actually answer this question. First, we will extend the route handler to support tool calling. We need to bring in additional dependencies from the AI SDK. So import from AI the tool helper function. This lets us define tools that the AI can use. We will also need Zod for schema validation. So import Z from Zod. Zod helps us define what inputs our tool expects in a type-safe way. Now let's define our weather tool. Outside the post handler, create a constant called tools. So const tools is equal to an object. Each property in the tools object becomes a tool that the AI can use. Let's call this one getWeather. And we assign it a tool definition using the tool function we imported from the AI SDK. So tool is a function, and we pass in an object. The definition is an object with 3 properties. First, we have the description property. This is a short description of the tool, including details on how and when it can be used by the model. In this case, we will describe the tool as a function that gets the weather for a given location. So get the weather for a location. Next, we have the input schema property. This is a Zod schema that defines the input parameters for the tool. The AI model will use this to generate the input for the tool. In this case, we will specify a city input that is a string. The Zod object, city, and this is a string, and we describe it as the city to get the weather for. Finally, we have the execute property. This is an async function that will be called with the arguments specified in the input schema. So async function, and the argument will be an object with city. For our weather tool, we'll return a string that describes the weather for the given city. We will keep it extremely simple for now and return a hard-coded string for Gotham City and Metropolis. So if city is equal to Gotham City, we're going to return a string 70 degrees and cloudy. Else if city is equal to Metropolis, we return 80 degrees and sunny. And if it's neither, you simply return unknown. Our weather tool is now ready. Let's give the AI access to this tool. Now the stream text function takes a tools property, and we can pass in the tools object we just created. So tools is the key, and tools is the value. We're using ES6 shorthand notation as the key and value are the same. All right, the AI now knows about our weather tool and can call it when needed. Before we jump to the browser to verify if this works, let's improve the type safety of our messages array. We need a couple more imports from the AI SDK. So in addition to UI message, we will also need infer UI tools and UI data types. And after the tool definition, export type chat tools is equal to infer UI tools. We specify type of our tools object. And in the next line, export type chat message is UI message, no metadata, the standard UI data types, and also our chat tools. We replace the UI message with chat message in the post request handler. So messages is now an array of chat message. This ensures our messages array is properly typed and supports our tool calls. TypeScript will understand exactly what tools we have and what their parameters are. Now let's jump to the browser. Enter the prompt, what's the weather in Gotham City, and hit enter. We don't see the response in the AI. This happens because of how tool calling works behind the scenes. You see, when the AI decides to use a tool, that is considered one step in the process. When you ask for weather in Gotham City, the AI calls the tool and gets the result, but then it needs another step to process that result and generate a natural language response. However, stream text only allows one step by default, which means the AI can call the tool but can't do anything with the result. To fix this, we need to import another helper function called stepCountIs from the AI SDK. So stepCountIs. This helper lets us control how many steps the AI can take. Now we will update the stream text call. We specify a property called stopWhen and set it to stepCountIs2. This allows two steps. Step 1 for calling our weather tool, and step 2 for processing the result and generating a response back to the user. The model is completely up to you. Let's actually try GPT-5 Mini and see how it works. All right, let's go back to the browser and test this out. Refresh, enter the prompt, what's the weather in Gotham City, both uppercase, and hit enter. This time, the AI actually tells you the weather. Current weather in Gotham City, 70 Fahrenheit and cloudy. This is the value we hard-coded in our getWeather tool. Here's what's happening behind the scenes. The AI recognized the question needed weather information. It called our getWeather tool with Gotham City as the parameter. The tool returned the weather data for Gotham City. The AI used that data to form a natural response. You can see here, current weather in Gotham City, 70 Fahrenheit and cloudy. Try asking, what's the weather in Metropolis? Press enter, and the AI will tell you the weather in Metropolis is 80 Fahrenheit and sunny. Our value right here. The really cool part is that AI is smart enough to know when a tool is relevant and when it's not. You don't have to explicitly tell it. If you ask, what is React? The AI responds normally without using the tool. All right, let me quickly summarize what we have learned. Tools are special functions we give to the AI model to address the limitations of its training data. With the AI SDK, the process is pretty straightforward. We used the tool helper function to define a tool. We provided a description and an execute function. We passed the tool's object to the stream text function. We set stopWhen step count is 2 or greater to allow the AI to call the tool and then process the result before generating a response. We also updated the type safety of our messages array. All right, if you're ready to see what else we can do with tools, let's jump into the next lesson. Previously, we implemented tool calling in our API route handler. When someone asks about the weather, the AI recognizes it needs a tool, calls it with the right parameters, gets the result, and forms a natural response. It all works perfectly, but there's something missing from the user experience. Right now, tool calls happen completely behind the scenes. The user asks about the weather and gets an answer, but they have no idea that the AI is actually calling a function to get that information. It might seem like the AI just knows the weather, when in reality, it's actively fetching it. In this lesson, we'll make tool calls visible in the UI. This transparency helps users understand what's happening and builds trust. They will see when the AI is calling tools, what parameters it's using, and what results it gets back. Let's dive in. Before we update the UI, let's first understand how tool calls appear in messages. In route.ts, command-click the UI message type to view the type definition. Scroll down to the parts array, which is an array of UI message part. When the AI calls a tool, it creates special message parts of type tool UI part. A tool UI part is an object that has a type that starts with tool hyphen followed by the name of the tool. In our case, tool hyphen getWeather. Each tool also has a tool call ID, but more importantly, it has a state property that tells us what stage the tool call is in. There are 4 possible states we need to handle. Input streaming, which is when the tool call is being streamed in and we are receiving the parameters gradually. Input available, which is when the complete tool call with all parameters is ready. output available, which is when the tool has executed and returned a result. And finally, output error, which is when something went wrong during tool execution. In the UI, we just need to handle this part type in the switch statement, taking into account the different states. So open page.tsx file. The first step is to import the chat message type from our route handler to get proper TypeScript support for our tool parts. So at the top of the file, import type chat message from app/api/tools/route. This gives us full type safety for our tools. Update the use chat hook to use this type. So use chat, and we specify chat message. TypeScript now knows exactly what tool parts can appear in our messages. Let's update the message rendering to handle tool parts. So find the switch statement where we render message parts, and you can see currently it only handles text parts. If part.type is equal to text, we render part.text, which is the content itself. Now, after the text case, let's handle a case for our weather tool. So case, if you remember, it is tool followed by the tool name. And you can see TypeScript IntelliSense working. Tool-getWeather. We'll add default return null. We start simple, just catching the tool part. But returning null means we won't see anything, so let's check which state the tool is in. And for that, we need another switch statement. So within the case tool-getWeather, switch statement, and this is on part.state. Remember, the state can be one of 4 different values. Now, as a default case, we're going to return null. And now, let's handle the 4 states one by one. The first state is input streaming. So case input-streaming. This happens when the tool call is being streamed in piece by piece. Let's add the case. We add a return statement with a div tag. We set key prop message.id followed by the tool name, which is getWeather, followed by index. We will add a nested div tag receiving weather request. Let's add some Tailwind styling to make it stand out. So on the outer div, as well as the inner div, we're basically showing a subtle message that we are receiving the request. Actually, during streaming, we can even show the partial parameters as they come in. So let's add that just for development purposes. A div tag, json.stringify part.input null, 2. We use a pre-tag to show the raw input parameters as they come in. This handles our case for input streaming. Next is input available. So case input available. The state means we have the complete tool call with all parameters. To save some time, I'm going to paste the JSX. So we have a return statement, a div tag with a key prop and Tailwind classes, an inner div that says getting weather for hard.input.city. We can now access city because the parameters are complete. If we go back to our tool call, you can see city is an input parameter. So part.input.city. We show exactly which city we are checking the weather for. The third state is output available. So case output available. This state indicates the tool has executed and returned a result. Once again, I'm going to paste the JSX. So for case output available, we have a div tag with a key prop and Tailwind classes, and then a div tag that now renders the text weather, followed by another div tag that renders part.output. We display the weather data that came back from our tool. Output is how you access the result. Finally, let's handle the error state. So case output error, and this is for scenarios where the tool call fails. So we should surface that to the user very clearly. We're going to have a return statement with a div tag, key prop, class name for styling, and we use red text to indicate an error and show the error message. It is accessible at part.errorText. This helps with debugging and lets users know when something goes wrong. And I can remove this unwanted return null. As you can see, each state has its own visual representation, and users can now see the entire flow of a tool call. Let's test this out. Back in the browser, refresh, and ask, what's the weather in Metropolis? You might briefly see receiving weather request as the tool call streams in, and then you will see getting weather for Metropolis when the parameters are ready. Next, the weather data appears showing the output, and finally, the AI's natural language response appears below the tool call UI. Since we render the tool call state UI in a switch statement, we only see one of the states at a time. And given how fast the tool call is, it's hard to see all the different states. So just for our learning, I'm going to tweak the code a bit to show all the states at once. I'm going to replace the entire messages rendering. In the browser, you should now see the complete journey. The AI decides to call a tool. It prepares the parameters. The tool executes with the input, so Metropolis. The tool executes and returns data, and the AI uses the data to respond. This transparency is powerful. Users understand that the AI isn't making things up. It's actually checking a weather service, even though ours is hard-coded for now. Now, to test the error state, you could modify the execute function in your route handler to throw an error for a specific city. So if city is equal to error city, throw a new error, weather service unavailable. Back in the browser, ask the AI, what's the weather in error city? And you will see the error state rendered in red. State output error, weather service unavailable. You can even see the AI's response. I tried to fetch the weather for error city, but the weather service returned weather service unavailable. Would you like me to try again, check a different city, etc.? We have basically transformed our tool calling implementation from an invisible background process to a transparent visual experience. By handling all 4 states of tool execution, we give users complete visibility into what the AI is doing. To summarize, we started by importing the proper chat message type to get TypeScript support for our tool parts. Then we added cases to handle each state of tool execution: streaming input, complete input, successful output, and errors. The pattern we have established here works for any tool. Whether you're calling weather APIs, querying databases, or sending emails, you can use the same approach to make tool calls visible and understandable. We have successfully implemented tool calling where the AI can check the weather for any city. But what if the user's question requires more than one tool to answer? Think about this scenario. Someone asks, what's the weather like for Bruce Wayne? To answer this question, the AI needs to do 2 things. First, figure out where Bruce Wayne lives. Then, get the weather for that location. This requires calling multiple tools in sequence, with the output of one tool becoming the input for another. This is called multi-step tool calling, and it is incredibly powerful. The AI can chain tools together to solve complex problems. Here is a visualization of multi-step tool calling. When the user asks, what's the weather for Bruce Wayne, the AI first extracts the name Bruce Wayne from the user's question. Then it calls the getLocation tool to find where Bruce Wayne lives. The tool returns Gotham City, and the AI passes that to the getWeather tool to get the weather for Gotham City. The tool returns 60 degrees and cloudy, and the AI uses this information to respond to the user's question in a natural way. If this is clear, let's see how to implement this in code. We will duplicate the code written for tools and make the necessary changes to support multi-step tool calling. In the API folder, create a new folder called Multiple Tools. Copy the route handler from the Tools folder and paste it into this new Multiple Tools folder. Similarly, in the app/UI folder, create a new folder called Multiple Tools. Copy the page.tsx file from the Tools folder and paste it into this new Multiple Tools folder. Rename the component to Multiple Tools Chat Page and update the API endpoint to /API/multiple tools. Perfect. Now, if you open the route handler, you will see we already have our weather tool, which accepts a city name and returns the weather for that city. Let's add a second tool that can find where someone lives. So in the tools object, before the getWeather tool, let's define a new tool. We'll call this one getLocation. Let's define it step by step. First, add the description. Get the location of a user. This tells the AI that the tool can find where someone lives. Next, define the input schema. This is Zod object. This tool needs a name parameter, and this is of type string. So z.string.describe the name of the user. The AI will pass the person's name to find their location. Finally, add the execute function. This is an async function. The argument, object with name, and the function returns the city where the username lives. Once again, we will use hard-coded data to keep things simple. But in a real app, you might query a database or a user's directory. If name is equal to Bruce Wayne, we return a string Gotham City. Else if name is equal to Clark Kent, return Metropolis. Else, we return unknown. So now our tools object has two tools, getLocation and getWeather. The order doesn't matter functionally, but it reads better this way since we'll call location first and then weather. Now here's the crucial part. Remember how we set step count to 2 to allow the AI to call one tool and respond? Well, now we need more steps. Step 1, call getLocation to find where Bruce Wayne lives. Step 2, call getWeather with that location. Step 3, generate the final response to the user's question. We need 3 steps in total. So let's update the stream text call, stop when step count is 3. This allows the AI to chain multiple tool calls together. The number really depends on how many tools you have and how many steps the AI needs to take to answer the user's question. For our example, 3 steps is sufficient. All right, our route handler is now ready. Head over to page.tsx to update the UI to show both tools. In the message parts rendering, we already handle tool getWeather parts. Now we need to handle tool getLocation parts too. So before tool getWeather, let's add a new case. Case tool getLocation. We see a TypeScript error because our chat message import is still from the tools folder. Update this to multiple tools, and the TypeScript error should be fixed. For tool getLocation, we will add a new switch statement to handle the part state. The default case, we will return null. For the first case, we will start with input streaming. I will paste the code since we've already gone through this for getWeather tool. So case, input streaming, we have a div tag with a key prop, tailwind classes. We have a nested div with the text receiving location request. And for development purpose, we render part.input. This is the streaming parameter. The second case is input available. Once again, return a div with the key prop and class name. We now have access to the name input parameter. So the text reads getting location for part.input.name, and the name here can be Bruce Wayne or Clark Kent. We're basically showing whose location we are looking up. The next case is output available. So return a div tag with key and class name, the inner div, location found, and then we output part.output. In our case, it will be Gotham City for Bruce Wayne and Metropolis for Clark Kent. Finally, handle errors. So case output error, we return a div with a key prop and class name, and the inner div in red color, we render the error message. As I mentioned previously, the pattern for rendering the UI states for a tool call will remain the same. All right, it's time for the exciting part, testing. Navigate to localhost 3000/UI/multiple tools and ask the question, what's the weather for Bruce Wayne? You should see the UI reflecting multiple tool calls. The first one is the location tool, and the second one is the weather tool. Finally, the AI responds to the user's question in a natural way. I found Bruce Wayne's location as Gotham City. Current conditions there, 70 Fahrenheit and cloudy. Try another one. What's the weather for Clark Kent? It's the same process. The AI calls getLocation with Clark Kent, gets back Metropolis, then calls getWeather with Metropolis. We see the final response from AI. Clark Kent's location is Metropolis, current conditions 80 and sunny. And here's something interesting. If I refresh and ask, what's the weather in Gotham City directly, the AI only calls the weather tool. It's smart enough to know it doesn't need the location tool when you already provide the city. The AI only uses tools it needs, even when multiple tools are available. The powerful thing about multi-step tool calling is that we don't explicitly program the sequences. We don't write code that says, if the user asks about weather for a person, first call getLocation, then call getWeather. Instead, we just define the tools and their capabilities. The AI figures out which tools to use, what order to call them in, how to pass data between tools, and how to combine the results. This is called tool orchestration, and it's one of the most powerful features of modern AI systems. The AI becomes like a conductor coordinating multiple tools to achieve a goal. We have successfully implemented multi-step tool calling. Starting with our single weather tool, we added a location tool that can find where people live. By increasing the step count to 3, we enable the AI to chain these tools together. The UI shows the complete flow of multiple tools, giving users visibility into the AI's problem-solving process. They can see how the AI breaks down the complex questions into smaller steps, uses different tools for each step, and combines the results. This pattern scales to any number of tools, whether you're building a customer service bot that needs to check orders, inventory, and shipping, or a research assistant that searches multiple databases, the same principles apply. Define your tools, give the AI enough steps, and let it orchestrate the solution. So far, we've been using hard-coded data in our tools. When someone asks about the weather in Gotham City, we return a fixed response. This works great for understanding how tools work, but it's not very useful in the real world. Users want actual weather data. In this lesson, we will connect our weather tool to a real weather API. We will fetch live weather data and return it to the user. But here's where it gets really interesting. Since tool outputs can be structured data, we can do more than just display text. We can create rich visual interfaces based on the tool results. Let's dive in and see how. First, we need a weather API. For this lesson, we will use weatherapi.com. It's free for development and provides comprehensive weather data. So go to weatherapi.com and sign up for a free account to get an API key. Once you have your API key, add it to your .env.local file. The key will be weather_API_key, and the value you can find in your Weather API account. Make sure to restart your development server after adding the environment variable. All right, time to create a new implementation that uses the real API. So in the API folder, create a new folder called API tool. Copy the route handler from the tools folder as a starting point. So route.ts from tools, copy and paste inside API tool. Now let's update the execute function to call the actual weather API. So replace the hard-coded data with a fetch call. Const response is equal to await fetch, and I'm going to paste the URL. It's http api.weatherapi.com/v1/current.json. Key is equal to process.env.weatherapi key, and the query parameter is our city, which is the input. Once we have the response, convert it to JSON. So const data is equal to await response.json and return data. This works, but the weather API returns a lot of data we don't need. For our example, let's extract just the essential information. Some elements from location, some elements from the current temperature, as well as the condition. So we create a weather data object, const weather data, with just the fields we care about. That would be location, which is an object, name, data.location.name, country, data.location.country, and local time, data.location.local time. Similarly, we need the current temperature in Celsius, so data.current.temperature in Celsius, and the condition. This is going to be text, and there's a code associated with it. This condition code will be useful later for styling. We return weather data instead of the complete data. Perfect. Our route handler is ready. Next, in the UI folder, create a new folder called API tool with a page.tsx file. Copy the code from UI/tools page.tsx as a starting point. Update the component name and the API endpoint. So this is going to be API tools chat page. The endpoint is API-tools. And don't forget to update the import for the chat message type, API-tool/route. For the output available state, we need to update our JSX. We're going to render part.output.location.name along with temperature in Celsius. So part.output.current.temperature. And finally, the text, current.condition.text. Our UI updates are ready. Very minimal changes, as you can see. I just noticed the API endpoint should be API-tool. All right, let's test this. In the browser, navigate to localhost 3000/UI/API tool. You should see the chat interface. Ask a question, what's the weather in London? And you should see the real weather data, the temperature, conditions, and even the local time in London. You can try different cities like Tokyo, New York, or Paris. Each returns actual current weather data. But here is where the tool calling becomes really powerful. Instead of just showing text or JSON, we can create beautiful visual components based on this tool output. So let's build a weather card that displays the data in an attractive, easy-to-read format. Back in VS Code, in the API tool UI folder, create a new file, weathercard.tsx. Since this is a straightforward React component, I will paste the component code, then walk through what it does. You can define your own component with your own styles to display the tool output, but let me walk you through what this component does. First, we define TypeScript interfaces. Weather data matches the structure of what our tool returns. This weather data right here. Then we have weather card props, which defines the component's props. Weather style interface defines the color scheme for different weather conditions. Within the weather card component, we have a getWeatherStyle function, which is an interesting bit. It takes the weather condition code and returns appropriate Tailwind classes. Sunny weather gets warm amber colors. Cloudy weather gets slate gray. Rain gets blue tones. Snowy gets sky blue. So each weather type has its own color palette that creates the right mood. The format time function takes the local time string and formats it nicely, showing just the hour and minutes with AM or PM. In the component's return statement, we create a compact weather card. It's a horizontal rectangle with the city name and local time on the left, temperature and conditions on the right. The background color changes based on the weather condition, creating a visual representation of the weather that you can understand at a glance. As I already mentioned, you don't have to copy this exact same component. It's a straightforward React component, so define your own JSX and style it the way you want to. Once you have the component ready, let's use it in our page.tsx. Import the weather card at the top, so import weather card from /weather card. Find the case for handling tool getWeather, output available, and currently it simply displays text values for location name, the current temperature, and the condition text. Replace this with the weather card component. So div, the key prop remains, but a simpler class name for some margin. And then we render the weather card component with weather data props set to part.output. This matches our interface structure. The weather card component will handle all the visual representation. All right, let's test it out. Let's save this and head to the browser. In the browser, you should already see the weather card component being rendered. We have this weather card with a purple or violet background, which is the default style. You can see background color, BG violet. The temperature is prominently displayed. The local time shows you AM or PM. And we also have the condition code text, cloudy. The code we have only checks for snow, rain, partly cloudy or sunny. So cloudy falls back to the default styles. Let's refresh and ask, what's the weather in Paris right now? We can see it's 5:07 p.m., 24 degrees Celsius, and partly cloudy. And the gray background reflects partly cloudy. What's the weather in New York? And we see it's 10:57 a.m., 24 degrees, and sunny. The warm amber background reflects that. The visual design changes to match the weather. This is why structured tool output is so powerful. We're not just getting text back from our tools. We're getting data we can transform into rich user interfaces. It's the perfect combination of AI intelligence and traditional UI development. All right, we have successfully connected our tool to a real API and created a beautiful visual interface for the results. Let me summarize what we have done. We started by integrating with weatherapi.com, replacing our hard-coded data with live weather information. The tool now fetches real temperatures, conditions, and local times for any city in the world. But we didn't just stop at displaying the data. We built a weather card component that transforms the structured tool output into an attractive color-coded weather display. The card adapts its colors based on weather conditions, making the information instantly understandable. We render the component in page.tsx for the case output available. Of course, you're not limited to just weather. Any API you can call, any data you can fetch can become a tool. And any tool output can become a rich interactive interface. This is how you build AI applications that don't just talk about the world, but actually interact with it. We've given our AI the ability to make API calls, but there's still a major limitation. When you ask about recent events, current news, or anything that happened after the AI's training cutoff, it can't help. This is where web search tools come in. Web search allows the AI to search the internet in real time, find current information, and incorporate it into responses. It's basically like giving the AI access to Google right from within your chat interface. Now, web search is a bit different from the tools we've built so far because the tool is built into the AI provider's platform rather than something we code ourselves. In this lesson, I'll show you how to use OpenAI's web search capabilities. I will also show you how to use Anthropic's web search capabilities because there is a slight difference in the implementation. One important thing to note is that web search has different pricing than regular chat completions. Each search costs extra, so keep an eye on your usage when developing. All right, let's head back to VS Code and get started. For this lesson, we will use our existing tools implementation as the starting point. In the API folder, create a new folder called Web Search Tool. Copy the route handler from the tools folder into this new folder. Similarly, in the UI folder, create a new folder called web-search-tool. Copy the page.tsx file from the tools folder into this new folder. Update the component name to web search tool page and the API endpoint to /API/web search tool. Make sure to also update the path for chat message, API/web search tool. Perfect. We should now have a working chat interface. Let's test it out. In the browser, navigate to localhost 3000/UI/web search tool. Enter the prompt. What's the latest version of Next.js as of August 26th, 2025? And what are the main changes? Submit the prompt, and you will see the AI can't answer because it doesn't have access to that. I don't have live web access from here, so I can't look up the exact Next.js release published on August 26, 2025. And then it gives me some instructions on how to figure out myself. So the AI is smart enough to understand what you're asking, but can't actually get you the information. Let's go back to VS Code and add a tool so the AI can search the web on the fly and answer your questions. In the route handler, first remove the existing weather tool. You can also remove the tool helper function, as well as the Zod import. We'll have an empty tools object. Now, I mentioned web search tool is typically provided by the AI provider, so we access it differently. For OpenAI, add web_search_preview. This is going to be OpenAI.tools.webSearchPreview. This is a built-in tool from OpenAI. We will pass in an empty object as configuration options. But that is pretty much it. The web search tool is now available to the UI through this tools property. OpenAI handles all the complexity of searching the web, parsing results, and returning relevant information. Now, one other change is we need to update the stream text model to OpenAI.responses with the model GPT-5 Mini. Both OpenAI and AI SDK docs recommend using the responses model for OpenAI web search, but I found that web search works fine without having to specify that. To be on the safer side, I'll stick to the docs, so make sure to update OpenAI.responses. I'm using Mini, but please feel free to use Nano as it is more cost efficient. If you feel the results aren't what you expect, then you can upgrade to Mini. All right, our route handler is now ready. Let's update the UI. In the page component, we need to handle the web search tool parts. In the message rendering switch, update the getWeather tool call to web_search_preview. The 4 cases remain the same: input streaming, input available, output available, and output error. However, we don't get access to input and output, so I'm going to quickly modify just the JSX. First, for case input streaming, we're going to return the text preparing to search. Next, for input available, we're going to render the text searching the web. For output available, we're going to render the text web search complete. And finally, for output error, we're going to render web search failed, and also the error text. Very minimal changes, and our UI component is also ready. Let's test this. Back in the browser, enter the same prompt. What's the latest version of Next.js as of August 26th, 2025? And what are the main changes? Press enter, and you will see preparing to search, which is our web search tool call. Now, OpenAI does multiple searches to gather all the necessary information. And this UI is very specific to OpenAI, as you will see in just a moment when we implement for Anthropic. All right, after about 10 web search tool calls, we can see the short answer. As of 26th August, the newest stable release is Next.js 15.5, released around August 20th, 2025. And we'll also get to see what's new. Don't worry too much about the response formatting right now, but you can see the content is all there. What's the latest version of Next.js, and what are the changes? The AI is providing information based on current search results. Our web search tool is working, and the AI is no longer limited to its training data. Now, let me show you Anthropic's version. You don't have to follow along if you don't have an Anthropic key, but I will show you how to do it. In the route handler, first import Anthropic at the top. So import Anthropic from AI SDK/Anthropic. Comment out the OpenAI tool and add Anthropic's web search tool. Web_search. This is going to be Anthropic.tools.websearch 2025-0305. This has a version date in the name, which ensures stability as they update the tool. But we can also specify the max uses parameter, which limits how many searches can happen in one request. I'll set it to 1. Very useful for controlling costs. Next, in the stream text function, update the model to use Claude. So I'm going to comment out the existing line and change it to Anthropic Claude Sonnet for 2025-05-14. Next, in the page component, we need to update the case for Anthropic's tool name, web_search. So in page.tsx, comment this out and add a new case, tool web_search. The rest of the content is identical to the OpenAI version. So no more changes. Save the file, head back to the browser, and test with the same prompt. What's the latest version of Next.js as of August 26th, 2025? And what are the main changes? Press enter, and you should see the tool call, searching the web search complete, and we get back our response. Based on the search results, as of August 26th, 2025, the latest version is Next.js 15.5, which was released on August 18th, 2025. You can see Anthropic's version of web search is much cleaner from a UI perspective. We don't see multiple tool calls like we did with OpenAI. We just see one. This configuration from Anthropic is super useful. And if you scroll down, we also see the main changes in Next.js 15.5. We have successfully added web search capabilities to our AI chat. We first integrated OpenAI's web search tool and handled the tool call UI. Then we switched to Anthropic's implementation by updating the tool as well as the model. The UI is the same for both providers. Web search changes your AI from a static knowledge base into a dynamic assistant that can stay current with world events. When our AI searches the web, it's pulling information from various websites and articles. But users might wonder, where is this information coming from? Can I verify it? Is it from reliable sources? This is where source citations come in. When the AI performs a web search, it can return not just the information, but also the URLs of the sources it used. This transparency is important for building trust and allowing users to verify facts, read more details, or judge the credibility of sources themselves. The AI SDK makes it incredibly easy to include sources in web search results. Let's dive in and add this feature. In the web search tool route handler, we already have web search working with Anthropic's model. To include sources in the response, we just need one small change. In the return statement, when calling toUI message stream response, we will add the send sources option. So object, send sources, and set it to true. When send sources is true, the AI SDK sends source parts to the client. Now, before we update the UI, let's understand what these source parts are, which is what the UI will be receiving. In the AI SDK, a UI message can have various parts. We've already seen text parts, file parts, and tool parts. Now we are getting a new type called source parts, or source URL UI part to be more accurate. Each source part has a few properties. Type set to source-URL, so we can identify it in page.tsx. Source ID, which is a unique identifier. URL pointing to the source website. An optional title, which is the page title. And finally, optional provider metadata, which is the additional information from the provider. These parts are included alongside the text and tool parts when the AI uses web search. Let's see how we can extract and display these sources in the UI. Inside the messages.map function, before we render anything, let's filter out the sources. So let's change the parentheses into curly braces and add a return statement. This now allows us to add our new code. Const sources is equal to message.parts.filter. We pass in a callback function which receives the part, and we filter out by part type. So part.type is equal to source-URL. We are filtering the message parts to find only those with type source-URL. This gives us an array of all sources used for this particular message. Now we can display these sources immediately after the web search complete tool call UI. So expand the div, find, output available, and wrap the current UI in a fragment so we can add the sources right after it. So wrap the div in React fragment. After this div tag, we will render our list of sources. We'll start with curly braces. We will only show sources for assistant messages since users don't have sources. So message.role is equal to assistant. And we will also check if we have sources to show. And sources.length is greater than 0. If these are true, we will render the list. We'll render a div tag with some bottom margin. And now we can add a nice container with a blue background and a border. So div with some Tailwind classes, which I'm going to paste to save us some time. Within this container div, add a header showing how many sources we have. So another div, a span tag that renders the count of sources. So sources, parentheses, and within the parentheses, we will render sources.length. Let me add some styling to the div tag, as well as the span tag. Next, let's render each source as a clickable link. So another div tag with some vertical spacing between each link, so space y2, curly braces, to render the sources. So sources.map, we specify a callback function. We get access to the source part and the index. And within the function body, if part.type is equal to source URL, just to be on the safer side, we return an anchor tag. The text is going to be part.title, if that exists. Otherwise, we fall back to part.url. On the anchor tag, we specify the key prop. So key is going to be message.id, followed by the index. href is equal to part.url. Target is equal to blank. rel is equal to no opener and no referrer. We'll add some Tailwind classes for styling. And finally, title is equal to part.url. So each source becomes a link that opens in a new tab, has security attributes, shows the full URL on hover, and truncates long URLs to fit the container. If a source has a title, we use that instead of the URL. That is pretty much it. In output available, we render our web search complete tool called UI, followed by the list of sources. One thing I realize is the key prop should be present on the React fragment. So let's change this to React fragment with the key. Import React at the top. All right, let's save the file and test this out. In the browser, navigate to /UI/websearch tool and enter the same prompt as before. What's the latest version of Next.js as of August 26th, 2025? And what are the main changes? Press enter and watch what happens. The AI searches the web, so searching the web. The web search completes, and we now see a blue box of sources appear below the tool called UI. We see the sources that were used to answer the question. Click on any source to verify the information. You can see exactly where the AI got its facts. We have successfully added source citations to our web search tool. Let me quickly summarize what we did. First, we enabled sources in the route handler response. Send sources set to true for to UI message stream response. We filtered message parts to extract source URL parts. For the web search tool, for case output available, we added a React fragment, wrapped the tool called UI, and then added a dedicated UI section for sources. We made sources clickable for verification. Now that I think about it, this might render multiple times for an OpenAI web search, so please feel free to move this section around based on your UI requirements. Instead of blindly trusting the AI, users can now verify information, explore topics deeper, and judge source credibility. If you've followed along, you've learned how to build a multimodal chat interface that can respond with text, analyze images, and PDFs. You've also learned how to use AI to generate images from text descriptions. They are both powerful features by themselves, but what if we could combine them? With tools, we can do just that. In this lesson, we'll extend our multimodal chat to support image generation through tools. The user can still upload images for analysis, ask questions, and have conversations. But now, when appropriate, the AI can also create images as part of the response. Let's dive in. We will use our multimodal chat implementation as a starting point. It already handles text, file uploads, and image display perfectly. In the API folder, create a new folder, Generate Image Tool. Copy the route handler from multimodal chat into this new folder. Similarly, in the UI folder, create a new folder called Generate Image Tool. Copy the page.tsx file from multimodal chat into this new folder. Update the component name and API endpoint. We will call this Generate Image Tool page, and the API endpoint /API/generate-image-tool. In the browser, you can navigate to /UI/generate-image-tool, and you will see we have a working multimodal chat interface. You can upload images, ask questions about them, and have conversations. But it can't generate images yet. Let's add that capability. Open the route handler, and currently it is a standard chat handler. Let's extend it with tool support. First, we need additional imports, so update the import statement. Add tool for defining tools, and step count is for controlling the number of steps. We also need the image generation function, so experimental generate image as generate image. If you can recollect, this function generates images using AI models. We will also import Zod for schema validation. So import Z from Zod. Now let's define our image generation tool. Outside the post function, const tools is equal to an object. The tool name will be generate image, and we invoke the tool helper function with an object with the description property set to generate an image from a prompt input schema, which is a Zod object with one property, prompt, which is going to be z.string.describe the prompt to generate an image for. And now for the execute function. This is an async function which receives the input prompt, and within the function body, we call generate image with $3. So await generate image. The model is OpenAI .image model $3. We pass in the prompt. We set size to 1024 by 1024 and provider options for OpenAI, style, vivid, quality HD. From the resulting object, we will destructure the image. Finally, from the function, we return the base64 encoded image data. So return image.base64. Now, as it stands, this tool will generate an image and return this base64 encoded image data back to our AI for processing. But this encoded image is so large that it will exceed the context window of our model. To prevent this, we will send a simpler response to the AI using the toOutputModel method. So right after execute, we'll add toModelOutput. This is a function which receives the result from execute as its argument. However, we don't need to use it, so I'm going to leave it out. We will just return a simple text response that conforms to the model message format. So we return an object where type is set to content and value is an array of objects, and we specify type is text and the text content generated image in base64. To be clear, we are still generating the image and we can access that as tool call output in the UI. But we are not sending that image data back to the AI. Instead, we are sending this object, which is sufficient for the AI to understand how to respond in the chat interface. I will, of course, show you how to upload the image to a storage and use the URL in the next lesson. But for now, this toModel output method is a simple way to prevent the image data from exceeding our context window. But now that our tool is ready, let's include it in the post handler stream text call. Tools, key and value are the same, so use the shorthand notation. And then remember, we need to allow multiple steps. The AI will need to understand your request, call the image generation tool, process that result, and respond back in natural language. So set stop when. Step count is 2. Next, we need to update our TypeScript types. So update the imports. We need UI data types and infer UI tools. After the tools definition and just before the post handler, export type chat tools is equal to infer UI tools type of tools. And in the next line, export type chat message is equal to UI message. There's no metadata, the standard UI data types, and then our chat tools. Update the post function to use the typed messages. So this is going to be an array of chat message type. Our route handler is complete. Now let's update the UI to show image generation. In the page.tsx file, first import the chat message type. So import type chat message from generate image tool. Update the use chat hook to use the type. Use chat, and we specify chat message. Next, we will handle the tool generate image parts in our message rendering. So find the switch statement in the message parts rendering, and after the file case, we're going to add a case for tool generate image. To render the different tool calling states, we need a nested switch statement. So switch hard.state, and I'm going to quickly add a default return null. And now we can handle the 4 different states. Since we've been through this already, I'm going to paste the code and then walk you through it. First case is input streaming. We're going to render the text receiving image generation request and a JSON stringified version of part input. We're basically showing we are receiving the request with the prompt. The next case is case input available. We display the actual prompt being used for generation. This helps users understand what the AI is creating. Now for output available. Here we show the generated image. So the text generated image and the image component from Next.js rendering our tool output. Remember, the tool returns base64 image data, so we create a data URL and assign it to the image component source. Finally, handle errors with case output error. We render the text error generating image with the error text. And we can remove this return null statement. Our UI is now complete. Let's test this feature. Navigate to /UI/generate-image tool and start with a simple request. Generate a single image of a baseball cap. Press send and watch what happens. You see generating image for a realistic baseball cap. And after a few seconds, since image generation takes time, we can see the generated image. The AI might also add a text response describing what it generated. The image appears right in the chat flow, just like any other message. So our interface now supports both image analysis and generation. Now some models tend to be rogue and create multiple images for a request. So I'm trying to tame it by specifying I want a single image. But please feel free to experiment with different prompts and see how it goes. Our image generation tool is working as expected. Let me quickly summarize what we have done. First, we started with our multimodal chat interface that could analyze images and PDFs. Then we added the ability to generate images through tool calling. We added a tool to the route handler that can generate images from text descriptions. We used the toModel output method to prevent the context window exceeded error. We then updated the UI to handle the tool generate image parts in our message rendering. This pattern we have established here could be extended to other creative tools as well. You could add tools for generating audio, editing images, creating charts, or any other visual content. The combination of natural language understanding and creative generation opens up endless possibilities for AI-powered applications. So far, all our tools have been executing on the server. But what if applications need AI to interact directly with the user's environment? Think about scenarios where AI needs to access browser APIs, manipulate the DOM, interact with local storage, update your app state, require user confirmation before taking an action, or simply run some code automatically. That's where client-side tools come in. Client-side tools let the AI execute functions directly in the user's environment, which is the browser in our case. Instead of the server handling everything, the client takes over when appropriate. In this lesson, we'll build a practical example showcasing image transformations. We will use AI to remove the background as well as change the background to a new scene. The transformations will happen client-side, giving us instant results while maintaining the conversational AI experience. Let's start by duplicating our image generation tool implementation from the previous lesson. In the API folder, create a new folder called client-side tools and copy the route handler from generate image tool into this new folder. Copy route.ts, paste it in client-side tools. Similarly, in the UI folder, create a new folder called client-side tools and copy the page.tsx file from generate image tool into this new folder. Update the component name to client side tools page and update the API endpoint in the use chat hook /API/client side tools. Make sure to also update the chat message import /API/client side tools/route. Now, before we continue, we need to set up our image storage and transformation service. That brings us to ImageKit, our sponsor for this lesson. It is completely free to follow along, so go ahead and create an account using the link in the description. Once you have an account, you can get your credentials. In the dashboard, navigate to Developer Options, and here we will find the public key, the private key, and the URL endpoint. We will add these to the .env.local file. First, copy the URL endpoint and add it to the env file. Next, _public _imagekit URL endpoint and paste the copied value. Next, copy the public key and add it to the env file. So next, _public _imagekit public key and paste your value. Finally, copy the private key and add it to the env local file. To access the private key, we need to set a password. Let me quickly set up mine behind the scenes. And now I can enter that password and access the private key. Copy it and paste it in the .env.local file as imagekit _private _key. Make sure to not prefix with next _public as you should not be exposing this. Now that we have the credentials, let's install the ImageKit packages. In the terminal, run the command npm install imagekit and @imagekit/next. We need two packages, imagekit for the file upload in the route handler and imagekit/next for the optimized image component in the UI. Once the packages are installed, update your next.config.ts file to allow imagekit images. So scroll down and find next.config.ts and add a new configuration. Images, remote patterns is an array of objects. Protocol we set to HTTPS and host name imagekit. So ik.imagekit.io. This tells Next.js to trust images from ImageKit's domain. Now let's modify our route handler to upload generated images to ImageKit. So open the route handler and first import ImageKit at the top. Import ImageKit from ImageKit. Now let's create an upload function. So before the tools definition, const upload image, and this is going to be equal to an async function. This function will receive the base64 encoded format of the image. So image of type string. inside the function, first create an ImageKit client. So const ImageKit is equal to new ImageKit. We pass in an object where we set URL endpoint to process.env.next public ImageKit URL endpoint, our environment variable. We need to cast it to string. Next, we set public key to our public key environment variable. So process.env.next_public_ImageKit_public key as string. And finally, we set private key to process.env.ImageKit_private key as string. We are basically initializing ImageKit with our credentials from the environment variables. Now that we have the client, we can upload the image. So const response is equal to await ImageKit.upload. The upload method takes the base64 image and a file name. It will return the URL where the image is stored. So specify an object where file is equal to the image parameter, and file name, we can set it to generated_image.jpg. The upload image function will return the URL where the image is stored, so return response.url. Our function to upload image is ready, so let's update the generate image tool. Find the execute function, and here, instead of returning base64, let's upload to ImageKit. So const image URL is equal to await upload image, passing in image.base64, and we will return the image URL. This allows us to delete the two model output method we added previously. And what you see here is the right way to do this. Upload your image and return the image URL back to the AI to form a natural language response. For the next step, in the page component, we need to use ImageKit's image component. So at the top, replace import image from next/image to import image as a named export from at ImageKit/next. In the tool generate image output available case, where we render the image, update it to use the ImageKit component with the new image URL. The ImageKit image component needs the URL endpoint prop. So URL endpoint, and you set it to the environment variable process.env.next public ImageKit URL endpoint. The source is now a URL path rather than base64 data, so we can specify part.output. All right, let's save the file and test this. In the browser, navigate to localhost 3000/UI/client-side tools. We should see the chat interface. Let's enter a prompt. Let's try generate an image of an e-commerce product, a single image of a baseball cap. We have AI creating the prompt for us, and the image generates and displays. But now, if you check your ImageKit dashboard by clicking on Media Library, you will see the image is stored permanently. Now, ImageKit is a real-time media processing product that helps optimize, stream, and transform images and videos for the web. It comes with integrated storage and can also work with your own cloud storage, such as S3, GCP, etc. ImageKit can automatically compress and convert images and videos to a suitable format for every device. It offers more than 50 plus URL-based transformations for your images and videos, from simple resize and crop to more advanced features like AI-based crop and watermarking. They also offer SDKs for popular frameworks and languages. In this lesson, we are using their Node and Next.js package on their forever free plan. Now, what makes ImageKit particularly powerful is its image transformation capabilities. You can transform images simply by adding query parameters to the URL. Since transformations work through URL parameters, they happen instantly on the client side. And since we want these transformations using natural language, this is a perfect fit for client-side tools. Let's go back to our code and add client-side tools for background removal as well as changing the background. In the route handler, let's start with the transformation tools. So after generate image tool, add a change background tool. Let's call this change background. We use the tool helper function with an object we specify the description as replace image background with AI generated scenes based on text prompt. Now add the input schema. So input schema, z.object. And here we need the image URL and a description of the new background. So image URL is going to be z.string.describe URL of the uploaded image, and then a background prompt property, which is z.string again, and we describe it as description of the new background. We'll also specify some examples. We will use backticks as we need to use double quotes. Let's go with modern office, maybe a tropical beach sunset, or a mountain landscape. Perfect. Next, we will add the output schema, which is something new. This dictates the type of data that the tool will return. We will return a string, which is the URL of the transformed image. So z.string.describe the transformed image URL. Now you might have noticed something important here. We don't have an execute function. That is because this tool executes on the client side. Along similar lines, let's add a background removal tool as well. So remove background is a tool. We'll specify a description, remove the background of an image. We'll specify the input schema, so z.object. We require just the image URL, which is the URL of the uploaded image. And finally, output schema, z.string.describe the transformed image URL. Again, no execute function. The server just defines what the tool does. Now for the magic. Open the page component, and we will handle these tools on the client side. First, we will update the import from AI. Along with default chat transport, we need last assistant message is complete with tool calls. This helper determines when to automatically continue after tool calls. We'll use it in just a moment, but first, before the component, create a helper function. So function build transformation URL, and as the name indicates, this function will build our transformation URLs. Remember, all our transformations are simple URL based thanks to ImageKit. The function accepts base URL as a string and the transformation as a string. It will return a string value. Within the function body, we check if the URL already has query parameters. So base URL dot includes question mark, and if it does, we need the ampersand symbol. Otherwise, we append the question mark. And this is our separator. We then return a string, which is the base URL, followed by the separator, followed by ImageKit's transformation. The query parameter is tr is equal to, and we append the transformation. Very simple. Now update the use chat hook. First, destructure a function called add_tool_result. Again, as the name indicates, this will allow us to add tool results manually on the client side. Next, add the configuration for automatic sending. So send automatically when, and we set it to last assistant message is complete with tool calls. This tells the hook to automatically continue when tool calls complete. Next, add the onToolCall handler. So async on tool call. This function runs when the AI calls a tool, so we can run the execute function logic client side. The function is called with the tool call object, so tool call, which contains the tool name, input, and tool call ID. Inside the function, we'll first check if the tool call is dynamic and simply return if it is. So if toolcall.dynamic return. Dynamic tools are tools where the input and output types are not known at compile time. They're primarily useful when integrating with MCP tools. For us, we just need this check to narrow down the types for change background and remove background tools we've defined. Next, let's handle our tools with a switch statement. So switch tool call dot tool name, and we will use this tool name to determine which logic to execute. For case, change background from tool call dot input, we will destructure image URL and background prompt. Now, if you don't do this dynamic check, you will get type errors when you try access the input properties. Something to keep in mind. But once you have the image URL and background prompt, we can build the transformation URL. So const transformation is equal to, and this is an ImageKit transformation. It's simply e-change bg hyphen prompt followed by the actual prompt. So hyphen dollar curly braces background prompt. And the transformed URL is going to be build transformation URL, passing in the base image URL as well as the transformation. Finally, add the tool result to the messages array using the add tool result function. Add tool result, pass in an object. The tool is change background. Tool call ID is going to be tool call dot tool call ID, and output is going to be the transformed URL. In case you were wondering, add tool call result was destructured from the use chat hub. Let's actually put this in a block, as we will use similar variables for remove background as well. So for case remove background, we will have a similar pattern but with a simpler transformation. Once again, we'll have curly braces for block scoping. We'll extract image URL from tool call dot input. We'll define the transformation, which is simply e-remove bg. Remember, these are ImageKit transformations. And then const transformed URL is equal to build transformation URL. We pass in the base image URL with the transformation. Finally, call add tool result, passing in an object with tool set to remove background, tool call ID set to tool call dot tool call ID, and output set to transformed URL. Our client-side tools are ready. Let's add UI to show these transformations. In the message rendering switch, after tool generate image, let's add cases for change background and remove background. First, case tool hyphen change background. We need a switch statement for part.state, and I will paste the code for case input available. We're simply displaying changing background to, followed by the background prompt. We're showing the user what's happening when the tool is called. And I will also paste the output available case. So case output available. We render the text background changed, and we use the ImageKit component for Next.js to render the transformed image. And since the code is very similar for remove background, let me paste the code. Case tool hyphen remove background, switch statement on part.state. For input available, we're going to render the text removing background, and for case output available, we're going to render the text background image along with the transformed image. Once again, we're using ImageKit's image component for Next.js. All the code is available on my GitHub repo, and a link is in the description, so please pause the video if you want to go and grab the code. But our UI component is now complete. Time to see this magic in action. Navigate to localhost 3000/UI/client-side tools and generate a prompt. First, I'll enter the prompt, a single image of a saucepan with lid. Press enter, and the AI will take a few seconds to generate the image. The image is generated along with some text. We also get the full ImageKit URL for reference. But now, we can simply type, change the background to a dining table for the saucepan, and press enter. Now watch what happens. The AI calls the change background tool, the client builds the transformation URL, and the transformed image appears instantly. No server round trip for the transformation. our change background transformation is working perfectly. Now let's try remove background. And I realized this should be e-pg remove. Back in the browser, we can enter the prompt, a single image of a saucepan on a dining table. Press enter, and we see the AI enhancing our prompt. This prompt will be sent to DALL-E 3, and the image generation is in progress. Give it a few seconds, and our image is generated. Now we can simply prompt, can you remove the saucepan background? Press enter, and we should see our image without any background. All the transformations are happening client-side through ImageKit's parameters transformation. Very simple, as you can see. Now, if you want to, you can chain remove background and change background, but make sure to update the step count to 3 or higher. So as an exercise, go ahead and generate a new image using DALL-E 3, and then change the background using ImageKit's change background tool, and then remove the background using ImageKit's background removal tool. Now, ImageKit supports a lot of transformations. You have change background, edit image, generative fill, AI drop shadow, retouch, upscale, and a lot more. Very useful when working with media-heavy apps like an e-commerce site. But the key insights for this lesson are that server-side tools define capabilities without execution, client-side handlers process tool calls instantly in the browser, and natural language maintains the conversational experience. You will reach out to client-side tools for medium to large applications, and hopefully this gives you a clear picture of how to use them. So far, we've been building all our tools from scratch. Weather tools, location tools, search tools. We code them, we maintain them, we deploy them. But what if you could connect to tools that someone else has already built and deployed? Tools for accessing databases, sending emails, managing calendars, or controlling smart home devices. That's where Model Context Protocol comes in. MCP, or Model Context Protocol, is an open standard that lets AI applications connect to external tools and data sources. Think of it like an app store for AI tools. Instead of building everything yourself, you can connect to MCP servers that provide ready-made tools. These servers can be running anywhere, on your local machine, in your company's infrastructure, or in the cloud. The AI SDK makes it incredibly easy to connect to these MCP servers and use their tools just like the ones we've built ourselves. Now, MCP is a pretty vast topic that deserves its own course. There is so much you can do with it. But for this lesson, we will focus on the essentials, connecting to MCP servers and accessing their tools using the AI SDK. We'll see how MCP tools work seamlessly alongside the tools we've already built. Let's dive in and add MCP tools to our chat interface. For this lesson, we will build on top of our existing tools implementation. In the API folder, create a new folder called MCP-tools. Copy the route handler from the tools folder and paste it into this new folder. Similarly, in the UI folder, create a new folder called MCP-tools and copy the page.tsx file from the tools folder into this new folder. Update the component name to MCP tools chat page. Update the API endpoint to /API/MCP-tools. And don't forget to update the chat message import /API/MCP-tools/route. Perfect. Let's test this out at localhost 3000/UI/MCP-tools. Ask the question, what's the weather in Gotham City? And it works with our existing weather tool. We've defined that in route.ts. Now let's add MCP tools to the mix. For this lesson, we will use mockmcp.com, which is an easy way to create an MCP server that we can test against. So head over to mockmcp.com and create a free account. It just takes a minute. Once you're logged in, you can create your first server. So let's click on Create Your First Server button. And let's fill in the necessary details. For the server name, Demo MCP Server. With a description, Testing MCP Tools with AI SDK. Next, we will add a tool to our server. For this demo, let's create a stock price tool. The tool name is going to be Get Stock Price. The description, get current stock price for a company. The input parameter, we'll call this symbol, type string, and the description, stock ticker symbol, and we can provide examples. So example, Apple or Google. For the output configuration, we will keep it simple with hard-coded data. The response is going to be a JSON with two values, price, $142.5, and change plus 2.3%. I'm hard-coding a static response to demo that we can call an MCP tool. In a real MCP server, this would fetch actual stock data. Once you've filled in all the details, go ahead and click Create Server. And there you go. You now have an MCP server with a Get Stock Price tool up and running. Now, mock MCP will give you two important things, a server URL and an auth token. Copy both these values because we will need them in our route handler. So for our next step, let's update our route handler to connect to the MCP server. First, we need to install the MCP SDK. In your terminal, run the command npm install at model context protocol /SDK. Next, we make some imports. From the AI package, we will import experimental create MCP client as create MCP client. And then we will import streamable HTTP client transport from model context protocol /SDK /client streamable HTTP.js. MCP support in the AI SDK is still experimental, but it works great. Once you've made the imports, inside the post function, before we call stream text, let's connect to our MCP server. So const HTTP transport is equal to new streamable HTTP client transport. The first argument is the URL, which you can copy from mock MCP server, paste it. And the second argument is our options. We have request init, headers, authorization, and we specify the bearer token. Copy and paste it. Make sure to specify bearer. Please make sure both these values are from your mock MCP server. For the next step, create the MCP client. So const MCP client is equal to await create MCP client. We pass in an object where we specify transport, and that is set to HTTP transport we have just defined above. And now we can get all the tools from the MCP server. So const MCP tools is equal to await client dot tools. This fetches all available tools from the MCP server. In our case, it's just the get stock price tool, but an MCP server could have dozens of tools. Next, we need to combine our MCP tools with our existing weather tool. So update the stream text call. Tools is going to be set to an object where we destructure MCP tools and then our own tools. We're using the spread operator to merge our local tools with the MCP tools. The AI now has access to both. But wait, there's one more important thing. We need to close the MCP client when we are done. In the stream text argument, after stop when, we specify on finish. This is a callback, and we await MCP client dot close. We will also add the on error callback, which is an async function. Get access to the error. You await MCP client dot close here as well, and also log the error to the console. Error during streaming, and we log the error. This code right here ensures we properly close the connection to the MCP server when the stream finishes or if there is an error. It is super important to clean up resources. Our route handler is ready. For our next step, let's update the UI to handle our new stock price tool. So in the page.tsx file, in the switch statement, where we handle message parts, we already have tool get weather. But here's the thing. MCP tools come through with dynamic names and are not strongly typed. So after the weather tool case, we will add a case for dynamic tool. Case, dynamic tool And you can see TypeScript helping us out. For case dynamic tool, we will pretty much repeat the switch statement for handling the different states in the UI. Since we've been through this multiple times already, I will paste the snippet and walk you through the code. You can see we are handling the 4 states of the tool call. Input streaming, where we render preparing stock price request. Input available, where we render fetching stock price. Output available, stock price retrieved. And output error, failed to fetch stock price. The JSX here specifically corresponds to the get stock price tool, but if your MCP server has different tools, you will want to be more generic. All right, time to see this in action. Save the file, navigate to /UI/MCP tools, and first let's make sure our existing tool still works. Ask the question, what's the weather in Gotham City? Submit, and perfect, the weather tool still works, 70 Fahrenheit and cloudy. Now for the exciting part. Ask, what's the stock price of Apple? Submit, and you'll see the MCP tool call UI and the response. Stock price retrieved. Apple is trading at $142.5, change plus 2.3%. This will be the same result for any stock price symbol you ask for because we are hard coding the tool response, but hopefully you can see the pattern here. We're able to connect to an MCP server and make a dynamic tool call. The beauty is that your code doesn't change. You just connect to different MCP servers, even multiple, and suddenly your AI has all these new capabilities. We have successfully integrated MCP tools into our chat application. Let me quickly summarize what we've learned. MCP, or Model Context Protocol, is an open standard that lets you connect to external tool servers. Instead of building every tool yourself, you can connect to MCP servers that provide ready-made tools for various tasks. We started with our existing tools implementation and added MCP support. Using mockmcp.com, we created a simple server with a stock price tool, and in the route handler, we connected to the MCP server using the streamable HTTP client transport, fetched its tools, and merged them with our existing tools. In the UI, we added a switch case for dynamic tools that can display any tool that comes from an MCP server. The AI can seamlessly use both our local tools and MCP tools to answer questions. When you ask an AI to solve a complex problem or a tricky algorithm, it gives you an answer. Sometimes it's right, sometimes it's wrong. But wouldn't it be nice to see how the AI is thinking through the problem? That way, you could understand its approach, learn from its logic, or figure out where things went wrong. The good news is that the latest AI models have something called reasoning capabilities, which will allow them to think before they answer. They work through the problems step by step, consider different approaches, and sometimes even backtrack when they realize they've made a mistake. It's like watching someone work out a math problem on paper. Now, how does this work? Well, the AI models generate something called reasoning tokens. Basically, the AIs scratch paper where it works through the problem. It might use hundreds or thousands of these reasoning tokens to think through your question. But here's the thing. Normally, these are hidden. You get the final answer, but never see the work. In this lesson, we're going to change that and make the AI's thinking process visible. Let's dive into code and see how reasoning works. We'll start by setting up our files based on the chat implementation from earlier in the course. In the API folder, create a new folder called Reasoning. Copy the route handler from the chat folder and paste it into this new Reasoning folder. We can remove the system prompt and the token usage code to keep it simple. The model is GPT-5 Nano. Next, in the UI folder, create a new folder called Reasoning and copy the page.tsx file from the chat folder into this new folder. Update the component name to Reasoning Chat Page and the API endpoint using the default chat transport class. So import default chat transport from AI, and to use chat, specify transport. The value is new default chat transport. We pass in an object, with API set to /API/reasoning. We should now have a working chat interface. Let's test it out. In the browser, navigate to /UI/reasoning and try asking, what's the best JavaScript framework? The AI will take a while and we see the answer, but we don't see the thinking process. Let's fix that. To enable reasoning features with the AI SDK, we need to add provider options. So after the messages property, we specify provider options. We're working with OpenAI. So we specify OpenAI and we set reasoning summary to auto and reasoning effort to low. Now the reasoning summary tells the model to include a summary of its reasoning process. This is a human readable version of what the AI was thinking. The value auto typically refers to a detailed summary for most recent models, but you can also set this to concise if you want a shorter summary. Next, we can also set the reasoning effort for the model. This parameter tells the model how much to think. You can set it to low, medium, or high, medium being the default. For our demo, low is perfectly fine. Finally, we need to tell the response to actually send these reasoning parts to the client. So update the return statement. To UI message stream response, we pass in an object and we set send reasoning to true. This ensures that reasoning parts are included in the stream sent to the client. Now, before we update the UI, let's understand what we're dealing with. In the AI SDK, when reasoning is enabled, the UI message can include reasoning parts alongside text parts. Here's the type definition for a reasoning part. A reasoning part has a type of reasoning, so we can identify it. The text, which contains the reasoning summary, an optional state that tells us if it's still streaming or complete, and an optional provider metadata with additional info from the provider. These reasoning parts appear before the text parts in the message, showing you what the AI thought before giving its answer. Let's see how we can extract and display these reasoning parts in the UI. In page.tsx, in the switch statement, where we handle message parts, we only have a case for text part. Let's add a case for reasoning parts. Now we can add this before or after the case text, case reasoning. And since reasoning is special because it is the AI's thought process, we will give it a different visual treatment. We'll return a div tag with key set to message.id, followed by index, and class name text small, text blue 500. We'll also render part.text. Now don't worry too much about the UI at this point. We will learn how to leverage UI components built specifically for chat interfaces later in the course. But we are now handling reasoning UI parts. Let's test this out. Navigate to /UI/reasoning and enter the same prompt as before. What's the best JavaScript framework for building web applications? Press send, and look at that. You see a blue reasoning box appear with the AI's thought process. I need to respond to the user's question about frameworks, which is quite subjective. I'll provide a range of options like React, Vue, Svelte, Solid, and you can read the rest. But you can see it is explaining how it's breaking down the question and thinking through the approach. Then below that, you get the final answer. We have successfully added reasoning capabilities to our AI chat. Let me summarize what we have learned. Reasoning models like GPT-5 use reasoning tokens to think through problems before answering. These tokens are like the AI's scratch paper, normally hidden, but incredibly valuable for understanding how the AI works. We started with our basic chat implementation and then updated the code to enable reasoning. In the route handler, we added provider options for reasoning effort and summaries. We also enabled send reasoning in the response. In the UI, we handled the new reasoning parts by creating a special visual treatment that makes it clear when the AI is showing its thought process versus its final answer. This thinking transparency is powerful. Users can now see not just what the AI thinks, but how it thinks. They can verify the logic, learn from the problem-solving approach, and have much more confidence in the answers they receive. When you're building a chat application, sometimes you need to track more than just the conversation itself. For example, when was each message sent, or how many tokens did it use? Right now, our messages are just text. They don't carry any of this contextual information that could be really useful for debugging, analytics, or just giving users more transparency. Message metadata lets you attach custom information to each message. It's not part of the actual message content, but it's information about the message that can be incredibly valuable. The AI SDK makes it super easy to add metadata to messages as they're being streamed in. In this lesson, we will learn how to add timestamps and token counts to our messages. Let's start by setting up our files based on the chat implementation from earlier in the course. In the API folder, create a new folder called message metadata. So message metadata. Copy the route handler from the chat folder and paste it into this new folder. We can remove the system prompt and the token usage console log to keep it simple. In the UI folder, create a new folder called message metadata and copy the page.tsx file from the chat folder into this new folder. Update the component name to metadata chat page and the API endpoint using the default chat transport class. Import default chat transport from AI and use chat hook. Pass in an object where we specify transport. This is new default chat transport. We pass in an object again, set API to /API/message metadata. Perfect. We should now have a working chat interface. Let's test it out. In the browser, navigate to localhost 3000/UI/message-metadata. Type the prompt, what is TypeScript? We can see the loading spinner, and the chat interface is working. But there is no metadata yet. Let's add that. First, we need to define what metadata we want to attach to our messages. Since TypeScript doesn't know what custom metadata we're using, we need to create types for it. In the API folder, in the message metadata folder, create a new file, types.ts. We'll define our metadata schema here. First, we import UI message from AI and Zod for schema validation. So import Z from Zod. Now let's define what metadata we want. Export const message metadata. This is going to be z.object. We will define two pieces of metadata. Created at, for when the message was created, as a timestamp, so z.number.optional, and total tokens for how many tokens the message used, z.number.optional. Both these are optional as we might not always have all metadata. Now let's create TypeScript types from our schema. Export type message metadata, and we use Zod's inference to create a type from our schema. So z.infer type of message metadata. Let's call this message metadata schema and pass in the same. Finally, let's create a typed version of UI message that includes our metadata. So export type my UI message. This is going to be equal to UI message, and we pass in message metadata. So this creates our own typed UI message that knows about our metadata structure. This gives us full TypeScript support for our custom metadata. Let's update our route handler to actually attach metadata to messages. First, import the custom type. So import type my UI message from /types and update the post function to use our typed message. Instead of UI message, my UI message. And we can remove the UI message import from AI package. All right, now here's where the magic happens. When we return the response, we can specify a message metadata function that gets called as the message streams. So an object, message metadata, is a function, and this function receives a part parameter that tells us what's happening in the stream. So destructure it, and within the function body, let's handle different parts of the streaming process. First, when the message starts, we capture the current timestamp. So if part.type is equal to start, we return an object where we set created at to date.now. And then we capture the token usage when the message finishes. So if part.type is equal to finish, we return an object where we set total tokens to part.totalUsage.total tokens. Total usage contains all the token information, and we extract the total tokens and add it to our metadata. And let's also add a console log statement to understand the token count better when we send a prompt. So just before the return statement, console log part.totalUsage. Now let's make this metadata visible in the UI. So in page.tsx, first we need to import our custom type. Import myUIMessage from message metadata /types and update the useChat hook to use our typed messages. UseChat myUIMessage. Now TypeScript knows our messages have metadata. Let's display it. After the message parts rendering, but before the closing div tag for each message, we're going to add a div container. I'm going to add a few tailoring classes for styling. Within the div, let's conditionally show the token count. So curly braces, message.metadata. If that exists and total tokens exist, we're going to render a div tag message.metadata.total tokens followed by the word tokens. Similarly, let's also render the timestamp. Curly braces, message.metadata, and if that exists and created at exists, we render a div tag, the at symbol, followed by, within curly braces, new date, message.metadata.createdAt to locale time string. And we can make the time format more readable. So as the second argument, we set R to 2-digit, minute to 2-digit, and R12 to true. Now we get a clean time format like at 2:30 p.m. The metadata appears as subtle gray text below each message. Time to see this in action. Navigate to /UI/message metadata and ask the same question. What is TypeScript? Now, when the AI responds, you see both the timestamp and the token count, 256 tokens at 11:32 a.m. Now, there is an important point I want to point out. Right now, we're using GPT 4.1 Nano, and in the terminal, you can see input tokens 12, output tokens 244, total tokens 256. Reasoning tokens is 0. But if you were to use GPT 5 Nano, refresh the browser and ask the same question, what is TypeScript? You can see the token count is way higher, 1,344 tokens. This is because of reasoning tokens we learned in the previous lesson. If you look at the console, you will see the token count breakdown. Input tokens 11, output tokens 1,333, of which reasoning tokens are 1,024. Very important to keep this in mind. All right, we have successfully added metadata to our chat messages. Let me summarize what we have learned. Message metadata allows you to attach contextual information to messages. It's different from message content because it's information about the message itself. We started by creating a typed schema for our metadata using Zod, then created a custom UI message type that includes our metadata structure. In the route handler, we used the message metadata function to capture timestamps when messages start and token counts when they finish. In the UI, we displayed the metadata as subtle gray text below each message giving users visibility into when messages were sent and how many tokens were used. You could add model versions, response times, or any other metadata your application needs. The metadata travels with the messages throughout your application, making it perfect for analytics, debugging, and creating more informative user interfaces. Right now, when we use AI models in our code, we are hard coding them everywhere. We write OpenAI GPT-5 Nano in one file, and then Anthropic Claude Sonnet 4 in another. But what happens when you want to switch models, or test different providers, or update to a new model version? You would have to change model names everywhere, which can be a maintenance headache. Plus, what if you want to use the same model with different settings in different parts of your app? Maybe you want high reasoning effort for complex tasks, but low effort for simple ones. Or maybe you want to give your models friendly aliases like fast or smart instead of remembering version numbers like Claude Sonnet 4 2025 0514. Right now, you would have to configure these settings every single time you use a model. The AI SDK solves this with custom providers and a provider registry. With custom providers, you can pre-configure model settings, provide model name aliases, and limit the available models. The provider registry lets you mix multiple providers and access them through simple string IDs. It's like having a control panel for all your AI models in one place. Let's dive in and see how this works. Let's start fresh with a new implementation. In the API folder, create a new folder called Provider Management. Inside, create a route.ts file with our basic chat setup. I'm going to paste the code to save us some time. We make the necessary imports at the top. We have a post request handler. From the request body, we extract messages. We call stream text with model OpenAI GPT-5 Nano, and we convert UI messages to model messages. We return result.UI message stream response, a standard route handler we have seen before. Similarly, in the UI folder, create a provider management folder with a page.tsx file. Copy the basic chat UI from before. So chat page.tsx, paste it, and update the component name as well as the endpoint. So provider management page, import default chat transport from AI, and when invoking use chat hook, pass in an object with transport set to new default chat transport, pass in an object with API set to /API/provider-management. You can test this out at localhost 3000 /UI/provider-management. If you ask the question, what is React? You can see it works perfectly. But if we look at our route handler, it is clear we're still hard coding our model. Let's fix that. The first thing we'll do is create model aliases. Instead of remembering exact model names and versions, we will use friendly names like fast and smart. So in the API provider management folder, create a new file called models.ts. First, we import the original OpenAI provider. So OpenAI as original OpenAI from AI SDK /OpenAI. Next, we will import the custom provider function from the AI SDK. So import custom provider from AI. Now let's create our custom provider with aliases. So export const OpenAI is equal to custom provider. We pass in an object where we specify language models. This is an object. We have fast set to original OpenAI GPT-5 Nano, and then smart original OpenAI GPT-5 Mini. And we will also set fallback provider to original OpenAI. So what's happening here is that we are creating a custom provider that maps fast to GPT-5 Nano and smart to GPT-5 Mini. The fallback provider means if someone uses a model name we haven't aliased, it will pass through to the original OpenAI provider. Next, update the route handler to use this custom provider. So at the top, import OpenAI from /models. And when specifying the model in stream text, OpenAI, we specify OpenAI.language model, and we pass in our alias, fast. Save the file, head back to the browser, and enter the prompt, what is React? You can see our chat interface still works, but now we're using our alias. You can change it to OpenAI language model smart, and you'll be using the more powerful model. The beauty with this approach is if OpenAI releases a new version, you just update it in one place, the models.ts file, and your entire app uses that new version. Now let's say we want a reasoning model that always uses high reasoning effort. We don't want to specify this every time we use it, so let's add that to our custom provider. In models.ts, we need a couple more imports. Import default settings middleware, as well as wrap language model from AI, which I realized could be just one import statement. And now we can add a reasoning model with pre-configured settings. So after smart, let's create an alias called reasoning, where we wrap language model, pass in an object, and the model we are wrapping is original OpenAI, GPT-5 Nano, and we specify middleware, default settings middleware. We specify an object again, and we update the settings to provider options, OpenAI, which is an object, and we set reasoning effort high. We're basically wrapping the model with middleware that sets default settings. Now, whenever someone uses OpenAI reasoning, it automatically uses high reasoning effort. So back in the route handler, we can specify OpenAI.language model reasoning. Back in the browser, you can test this with a complex question like explain recursion with an example. The model will use high reasoning effort automatically. Now, what if you want to use multiple providers? For that, we can use the create provider registry function to create a registry that can handle both OpenAI and Anthropic models. So first, install the Anthropic provider if you haven't already, or simply follow along with me if you don't have an Anthropic key. Next, update models.ts with some more imports. Import Anthropic from AI SDK/Anthropic, and from the AI package, create provider registry. Now we can create custom providers for both OpenAI and Anthropic. So this will be just const custom OpenAI with our existing custom provider of different aliases, fast, smart, and reasoning. And we can create a similar one for Anthropic. So const custom Anthropic, custom provider. We specify an object, language models, which is an object again. We set fast to Anthropic Claude 3.5 Haiku 2024-10-22. And we can set smart to Anthropic Claude Sonnet 4. Now that we have both custom OpenAI and custom Anthropic, we can create a registry that combines both. So export const registry is equal to create provider registry, pass in an object where we set OpenAI to custom OpenAI and Anthropic to custom Anthropic. The registry uses a colon as the separator by default. So you can access models like OpenAI :fast or Anthropic :smart. Let's go back to the route handler, update the import to import registry from /models, and update stream text to model registry .language model OpenAI :fast. The language model method on the registry finds the right provider and the model based on the string ID. Back in the chat, you can ask, "Who are you?" And you will see ChatGPT. But now you can easily switch providers. So change it to Anthropic :smart and ask the same question. Who are you? You can see the AI respond with Claude. There's no need to change imports or anything else. All you have to do is just update the string. We have successfully implemented provider and model management with the AI SDK. Let me summarize what we've learned. Provider management solves the problem of hard coding models throughout your code base. Instead of scattered model references, you have a central place to manage all your AI providers and models. We started by creating model aliases with custom providers, giving friendly names like fast and smart to specific model versions. Then we added pre-configured settings, so models like our reasoning model always uses high reasoning effort without having to specify it each time. Finally, we created a provider registry that combines multiple providers, letting us access model from any provider with a simple string ID like OpenAI Fast or Anthropic Smart. In a large app, you could have different models for different tasks. A fast model for simple queries, a smart model for complex ones, a reasoning model for problem solving, and specialized models for specific domains. All managed in one place, all easily switchable, all with their own pre-configured settings. We built some great AI-powered chat interfaces together. The models know about programming languages, historical events, scientific concepts, and millions of other topics to respond to user questions. Let's say you want to create an AI chat interface as an internal tool where anyone can ask questions about your company. For example, developers need to know about architecture decisions. Designers want to look up brand guidelines and user research findings. Product managers need roadmap information and customer feedback. Support teams need to quickly find solutions to customer issues and product documentation. The AI model has no information about any of this. It doesn't know your tech stack, your design system, your product strategy, or your customer history. And even for public information, there's always a cutoff date. The model doesn't know about yesterday's product launch or this morning's incident resolution. Now you might think, well, I'll just store all my data in a database and search when needed. Let me tell you, traditional search has a huge problem. Imagine you're on Netflix trying to find something to watch. You remember watching this great movie about AI taking over the world, but you can't remember the title. So you search for AI apocalypse or robots destroying humanity. If the movie's title and description don't have those exact words, you get nothing. Zero results. Maybe the movie description says machines gain consciousness and threaten mankind. Totally different words, but similar meaning. Traditional keyword search just doesn't work here. This is exactly what Netflix, Spotify, YouTube, basically every content platform has to deal with. How do you help users find content based on meaning, not just matching keywords? This is where embeddings come in. Embeddings are a way to turn text into numbers that capture what the text actually means. When you give text to an embedding model, it gives you back a list of numbers. We call this a vector. These numbers represent what your text means in mathematical terms. And here's the cool part. Similar meanings end up close together in this mathematical space, even if they use completely different words. So AI apocalypse and machines gain consciousness would be really close in this embedding space, even though they don't share a single word. And this is how Netflix can show you the matrix when you search for reality simulation, even though the movie description might never use those words. Now let's talk about what these vectors actually are. A vector is just a list of decimal numbers. For OpenAI's text embedding 3 small model, you get 1,536 numbers. We call that 1,536 dimensions. Even the simplest text, like the matrix, will give you an array of 1,536 dimensions. Of course, we can't visualize thousands of dimensions. Our brains max out at 3D. But the idea is the same. Imagine a simple 2D graph where we plot movies. On the x-axis, maybe we measure action versus drama. And on the y-axis, realistic versus sci-fi. The matrix would be high on sci-fi and high on action. The Godfather would be high on drama and high on realistic. With 1,500 plus dimensions, the model can capture super detailed aspects of meaning, which means similar content naturally groups together. All sci-fi movies about AI would be in one area. Romantic comedies would be grouped in another area. Historical documentaries would be somewhere else entirely. But it is smarter than just genre. The Matrix, Inception, and Blade Runner, for example, would be super close together because they're all philosophical sci-fi that explores reality. Meanwhile, Star Wars would be further away because it's sci-fi but more adventure than philosophy. When Netflix wants to recommend movies, they find the movies closest to what you just watched in this embedding space. When you search, they convert your search into an embedding and find the closest content. No keyword matching is needed. But how do we measure closeness in this space? The most common way is called cosine similarity. Without getting too deep into the math, cosine similarity measures the angle between two vectors. It gives us a score from -1 to 1, where 1 means identical meaning, 0 means unrelated, and -1 means opposite meaning. So for example, The Matrix versus Inception could be 0.92, very similar. The Matrix versus Godfather could be 0.31, pretty different. And Matrix versus The Matrix Reloaded could be 0.98, almost identical. Of course, these numbers are hypothetical and will depend on the model you use. Embeddings and similarity search actually have many use cases. In customer support, when a customer says, "My internet is slow," you can find similar resolved tickets even if they said connection lagging, pages loading forever, or bandwidth issues. In content moderation, you can detect harmful content even when people use creative spelling or code words to avoid keyword filters. In duplicate detection, you can find similar bug reports or support tickets even when people describe the same problem differently. In retrieval augmented generation, or RAG for short, which is what we are building toward, you can store your documents as embeddings, find the most relevant ones for a user's question, and give them to the AI as context to generate an accurate answer. All right, now that we understand the theory, let's see how to actually implement this in code. In the next lesson, we will use OpenAI's embedding models to convert text into vectors. Now that we understand what embeddings are and how they can help us find content by meaning, let's learn how to generate them with OpenAI's embedding models using the AI SDK. We'll learn two key functions today: the embed function for embedding a single value, and embed many for processing multiple values at once. Let's jump into VS Code and start building. First, let's create our API endpoint. In the app folder, in the API folder, create a new folder called Embeddings. Inside, create route.ts file. We'll start with our basic post handler structure: export, async, function post. And now let's import what we need from the AI SDK. We import the embed function from the AI package and the OpenAI provider. So import OpenAI from AI SDK/OpenAI. The embed function is what turns text into vectors. Let's start simple. We will hardcode some text just to see how this works. So await, embed. We pass in an object where we specify model as OpenAI.textEmbeddingModel, and we pass in text embedding 3 small. This is their efficient embedding model that produces 1,536 dimensional vectors. We also specify value, and this is the text we want to convert to a vector. Let's type in a movie about hackers discovering reality in a simulation. The embed function returns an object from which we can destructure the embedding. We can return this embedding in the response. So return response.json, an object with the embedding. Our route handler is ready. Let's test this with the Thunder Client VS Code extension. Click on New Request. This is going to be a post request. to http localhost 3000/API/embeddings. With your dev server running, click send. You can see our request succeeds with status 200 OK, and we get back an array of 1,536 numbers. These are our embeddings, the numerical representations of our text. Each number captures some aspect of the meaning, though we can't tell exactly what each one represents. But returning just this embedding isn't very useful. Let's see what else the embed function gives us. Instead of destructuring immediately, let's return the entire result object to see what we get. So const result is equal to await embed and response.json result. Test again with Thunder Client, and you can see we get more than just the embedding. We have a value property showing our original text, the embedding array, and a usage object that tells us how many tokens this operation consumed. This is important for tracking costs. We also have some additional information about the response. Now let's make our route handler dynamic so users can send their own text. We specify request of type request. We destructure text from request.json. From the result, we will destructure value, embedding, as well as usage. The model remains the same, but the value is now text from the request, and we return response.json, an object with the value, the embedding, usage, and then dimensions. This is going to be embedding.length. Save the file and test this in Thunder Client. We will add a JSON body. So curly braces, double quotes, text is going to be a story about space exploration and first contact with aliens. Click send, and we get back our response. We get our original text, embedding, usage info, and dimension count. Now you might be wondering, why aren't we building a UI for this like we did for our chat and completion features? Well, embeddings are different. They're more of a behind-the-scenes operation. You generate embeddings when you're processing your data, like when Netflix adds a new movie to their catalog. It's not something users interact with directly. They interact with the search or recommendations that use these embeddings, but not the embedding generation itself. So for learning and testing, Thunder Client is actually perfect. Now, what if you need to embed multiple pieces of text? Maybe you have 100 movie descriptions to process. You don't want to call the API 100 times separately. That would be slow and inefficient. So let's update our route handler to support batch processing. We will import the embed many function from the AI package. Now let's add a new condition to handle arrays of text. So from request.json, we don't destructure, but instead we get the body of the request. And then we add a condition. If array.isArray body.texts, which we will pass in a request. If this exists, we will copy our embed function code and make the changes. The function is now called embed many. The model remains the same, but value is now called values. And to this, we assign body.text, which is an array. And embed many returns values and embeddings, both plural. Once we embed multiple values, we can return response.json values, embeddings, usage, count, which is embeddings.length, and then dimensions, which is embeddings of 0.length. We will have multiple embeddings, and dimensions are per embedding. So we access the first element in the array and calculate the length. The code for a single embedding, this is going to be body.text. So basically, if we receive a texts array in the request, we use embed many. If we don't, we will pass in text and we use the embed function to embed a single value. Let's test this with Thunder Client. Send a post request with an updated JSON body. We have curly braces, property is texts, plural, which is an array of 3 movies. A movie about time travel, a documentary about ocean life, a comedy about mistaken identity. Click send, and you can see our request succeeds. We get back 3 embeddings, 1 for each text. The usage object shows the total tokens for all 3. The count indicates the number of embeddings, and dimensions is the dimensions for each embedding. And it's important to note that the embeddings come back in the exact same order as the texts you send. So the first embedding corresponds to the time travel movie, second to the ocean documentary, and third to the comedy. This ordering is very important when you're processing your database. Speaking of processing, when you're processing lots of texts, Embed Many has a useful option called max parallel calls. By default, it processes texts one by one, but we can speed things up by processing multiple texts at the same time. You can set it to 5, for example. This tells the SDK to process up to 5 embeddings at the same time, just like having 5 workers instead of 1. This makes batch processing much faster, but be careful. Too many parallel calls might hit API rate limits. Of course, you won't see a difference with just 3 texts in an array, but imagine processing thousands. The time savings add up. And another point to mention is that we are using text embedding 3 small, which gives us 1536 dimensions. OpenAI also offers text embedding 3 large with 3072 dimensions, double the size. More dimensions mean the model can capture more nuanced meanings. It's like the difference between describing a movie with 10 words versus 20 words. More words let you be more precise. But there is a trade-off. More dimensions mean higher costs, more storage, and slower processing. For most applications, especially for learning purposes, the small model with 1536 dimensions works great. All right, to quickly recap what we have built, we learned how to use the embed function to convert a single piece of text into a vector of numbers. We saw how to track token usage for cost monitoring. Then we explored Embed Many for batch processing multiple texts at once. We saw how the order is preserved, which is super important when you're processing your database. We also learned about max parallel calls to speed up batch processing and briefly looked at the difference between small and large embedding models. These embeddings are the foundation of semantic search. In our next lesson, we will learn how to actually use these vectors, how to calculate similarity between them to find related content. We can now turn any text into a vector of numbers, but that's only half the story. The real power comes from finding which vectors are similar, which pieces of content are related by meaning. This is how Netflix knows that if you liked The Matrix, you might enjoy Inception. Not because they have similar titles or share keywords, but because their meaning vectors are close together in that high-dimensional space we talked about. In this lesson, we'll build this ourselves. Let's build a semantic movie search. In the API folder, create a new folder called Semantic Search with a route.ts file. We import embed and embed many from before, plus a new function called cosine similarity. This calculates how similar two vectors are. We will also import OpenAI from AI SDK/OpenAI. Now let's create a movie database. In a real app, this would come from your actual database, but for learning, we will hardcode some movies. I've picked a list of 8 movies from different genres: sci-fi, romance, crime, and action. This will help us see how well semantic search works across different types of content. Now, the first step is to embed all these movie descriptions. In a production app, you would do this once when adding movies to your database and store the embeddings. But for this demo, we will embed them on each request. So export async function, post, get hold of the request, and you extract the user's query from the request. So await request.json, and we destructure query. Next, we call embed many to embed our movie descriptions. So pass in an object. Model is going to be OpenAI.text embedding model, text embedding 3 small, and we specify values which is an array. We map over our movies array, extracting only the description. So for each movie, return movie.description. The embeddings come back in the same order as our movies. So we await the call to embed many, and we destructure from the result object embeddings, and we will alias this to movie embeddings. We will return response.json, a message embeddings generated. Now that we have the embeddings for our movie descriptions, the next step is to embed the search query, and using that embedding, find similar movies. To embed the query, we call the embed function. Model is going to be OpenAI.text embedding model, text embedding 3 small. We also specify value, which is singular, and we assign the user's query. From the resulting object, we destructure embedding as query embedding. Now that we have the movies embeddings as well as the query embedding, we can calculate similarity between query and each movie using the cosine similarity function. So const movies with scores, which is going to be an array of similarity scores. We map over the list of movies. We pass in a callback function. For each movie and index, we calculate the similarity. So const similarity is equal to cosine similarity. We pass in the query embedding and the movie embeddings of index. Once we have the similarity, we return an object where we destructure the movie and also include its similarity. Make sure to await embed to fix the error. Now, once we have movies with scores, let's return response.json results movies with scores. Let's save the file and test this out. In Thunder Client, update the URL to localhost 3000/API/semantic-search. The request body, we're going to specify query a sci-fi movie about space. Send the request, and you can see our results array. We have each movie object, so ID1, title, the matrix, the description, and the similarity, 0.33. If we look at Inception, it's 0.18. The Notebook, 0.24. Interstellar, which is pretty close to our query, has 0.45, which should be the highest in our list of movies. Blade Runner comes in a close second. Our similarity calculation is working as expected. But returning all movies isn't very helpful. So let's sort them by similarity and return only the most relevant ones. Back in the route handler, we're going to sort movies with score. So call the sort method, pass in a callback function for a comma b, b.similarity minus a.similarity. And then we can return only the top results. So const top results is equal to movies with scores dot slice 0, 3. And for our response, we can now return the query as it is, and results is going to be top results. Let's go back to Thunder Client and test this. Click send. And now look at the results. Interstellar has the highest similarity score, 0.45. Blade Runner is second, 0.41. And then the Terminator comes in third at 0.34. You can see that we never mentioned Interstellar in our search, but it still found the right movie. And the scores here are a reflection of our embeddings, which are only from simple one-liners right here. But Netflix would have a huge description of the movie as well as other metadata, which are embedded to make the score more relevant. But hopefully you get the idea. Now what you can also do is filter only the relevant results. So you can add a threshold filter. Before slicing, we can set const threshold is equal to 0.4. And then const relevant results is equal to movies with scores dot filter a movie such that movie dot similarity is greater than threshold. And we can now return relevant results.slice 0, 3. When you click send, we can see we have one and just two movies recommended, Interstellar and Blade Runner. If you search cooking, competition, reality show, and press send, you will get 0 results, and that is actually good. It's better to say no results found than show irrelevant content. In a real application, you would embed each movie description once when it's added to your database. You will store the embedding alongside the movie data, and when searching, only embed the query. You can compare the query embedding against your stored embeddings. The similarity calculation itself is fast. It's just math on arrays. But for millions of movies, even fast math adds up. That's where vector databases come in. They optimize the storage and search of embeddings using techniques like indexing to find similar vectors without checking every single one. We will learn about vector databases soon, but I hope you've understood the concept of semantic search. AI is amazing, but it knows nothing about your data. ChatGPT can write poetry, explain quantum physics, and code entire applications. But ask about your company policies, your research papers, or your personal notes, and it has no clue. Today, we're solving this problem by building a RAG chatbot that turns any PDF into instant AI knowledge. But before we start coding, let's first understand what RAG actually is and why it's important. Imagine you're building a chatbot for your company, maybe an internal tool where employees can ask questions about company policies, benefits, or procedures. Now, the problem is that AI models have never seen your company's data. They don't know your vacation policy, your expense reimbursement process, or any of your internal information. So with a traditional chatbot, when someone asks, what's our vacation policy, or how many sick days do I get, the AI can't answer because it simply doesn't have that information. That's where RAG comes in. RAG stands for Retrieval Augmented Generation. Retrieval means we search for and retrieve relevant information from your own data sources. Augmented means we enhance the AI's capabilities by providing this retrieved information. Generation means the AI generates a response based on both its training and the information we provided. Instead of the AI trying to remember everything, we give it access to your company's knowledge base. When someone asks a question, we quickly find the relevant documents, hand them to the AI, and then the AI uses those documents to generate an accurate answer. The really cool part is that this works instantly with any updates. If you changed the vacation policy last week, or if you added a new benefits package, it is immediately available. The AI becomes a knowledge assistant that has access to all your current documentation. So that is what we're building today, a RAG chatbot. By the end of this tutorial, you'll have built a RAG application with real-time streaming chat interface, PDF upload and processing, vector embeddings for semantic search, beautiful UI with Shatsian and AI elements, user authentication and role-based access control with Clerk, and production-ready database with Neon. Whether you're building an internal tool for your team, a customer support chatbot, or just learning to build AI applications, this tutorial will give you a solid foundation in modern RAG architecture. And to understand the project to its fullest, please make sure to watch the Next.js AI SDK playlist on the channel. Let's start building. First, create a new Next.js project. In the terminal, run the command npx create next app at latest, and we want to create the project in the current directory. When prompted, select yes for TypeScript, biome as your linter, Tailwind CSS, yes to source directory, yes to app router, turbopack, and no to import alias. When the command completes, you will have a new Next.js app ready to go. Run the app with npm run dev, and in the browser, open localhost 3000. You should see the Next.js welcome page. Now that we have our Next.js app set up, let's build a standard AI chatbot. The user will enter a prompt, we will send it to a route handler that interfaces with OpenAI and stream the response back to the UI. Back in VS Code, let's install the AI SDK packages we need. npm install AI at AI SDK/OpenAI at AI SDK/React and Zod. AI is the core AI SDK package. AI SDK/OpenAI connects us to OpenAI's models. AI SDK/React contains React hooks for building chat interfaces. And Zod helps us create type-safe schemas. Next, let's set up the UI components. We'll use Shadcn UI and AI elements. In the terminal, run the command npx shadcn at latest space init. Select neutral, and then run the command npx shadcn at latest space add. We'll keep this simple and select all the components. Press A to select all and press enter. Next, we'll add AI elements. The command is npx AI-elements at latest. This gives us pre-built components specifically for AI applications. If we expand the source folder, components folder, we can see Shadcn components in the UI folder and our AI-specific components in the AI elements folder. Now, before we write any code, we need to add our OpenAI API key. In the project root, create a .env.local file. Add a new variable called OpenAI _API _key and add your actual OpenAI API key. I'm going to do this behind the scenes. Now let's create the chat route handler. In the app folder, create a new folder called API. Within this folder, create a new folder called chat with a route.ts file. Start with a basic post handler. Export async function post receives request of type request and empty curly braces. Next, let's add our imports at the top of the file. Import the stream text function from the core AI package and the OpenAI provider from AI SDK/OpenAI package. These work together to stream text using OpenAI's models. We will also import the UI message type and convert to model messages helper function from the AI package. Within the post function, let's get the messages from the request. Await request.json. This returns an object from which we destructure messages. The type of messages is UI message array. Next, let's call stream text to generate the response. Const result is equal to stream text. We pass in an object with model set to OpenAI, GPT 4.1 mini, and messages set to convert to model messages, passing in messages. We use the helper function to convert the messages from the UI to the format expected by the model. Now, I'm using GPT 4.1 mini for this tutorial, but if you want to use GPT 5 mini, there is an extra step you need to take if your organization has zero data retention policy. But I'll keep it simple and use GPT 4.1 mini, so I recommend you do the same to follow along. Once we have the result, let's return the streaming response. So return result.toUI message stream response. Let's also add error handling with the try-catch block. So try, closing curly braces, catch. You get hold of the error, console.error, error, streaming chat completion, and log the error. And we return a new response, failed to stream, chat completion, status 500. Perfect, our route handler is complete. Now let's build the UI. In the app folder, create a new folder called chat with the page.tsx file. Here, define a basic React component. Export default function, rag chatbot, and we return a div tag. This component will be a client component since we'll need interactivity. So add the useClient directive at the top of the file. Now the AI elements package gives us beautiful components for chat interfaces. Let's import a couple of them. To save us some time, I'm going to paste the imports here. You can copy these from the GitHub repo linked in the description, but also feel free to style the UI to your liking. You can take a look at the AI Elements docs for detailed information on each component. But the first set here is related to prompt input and submission. The second set here related to rendering the conversation. And loader is basically a loading indicator. Now that we have the components imported, let's start building the JSX structure. First, we'll create a container that centers everything and takes the full height. So div class name is equal to max width 4XL, MX auto, padding 6, relative, size full, and the height for now is going to be the 100% of viewport height. So calculate 100 VH. Within this div tag, we're going to nest another div tag. This one with class name is equal to flex column to vertically place our items, and full height. Now let's add the conversation component. So conversation class name is equal to full height. And within the conversation component, we're going to nest conversation content. And this is where our messages will go. And then a conversation scroll button component. The conversation component handles the scrollable area, and the conversation scroll button adds a nice button to scroll to the bottom. Below the conversation, we will add the prompt input. So prompt input will add some top margin, and we will nest a couple of components. First, prompt input body. This will contain the prompt input text area, and below the text area, prompt input toolbar with the submit button. Optionally, you can also include prompt input tools for elements like a model selector, the web search icon, extended thinking, and so on. We will not implement this for our chatbot, but I will leave a placeholder here for you to understand where the additional functionality can go. There is a type error on prompt input, but we will fix this in a bit. But we now have the structure in place. Of course, nothing works because we haven't connected it to any logic. So let's add state for the input field. Import useState from React. And we will also import the fragment component, which we will need for rendering messages in a bit. Within the component, let's add the state. So useState, the variable is called input, the setter function set input, and the initial value is an empty string. We will bind this to prompt input text area. So value is equal to input, and onChange is equal to an arrow function which receives the event, and we call set input event.target.value. Next, for managing the chat state, we will use the useChat hook from AI SDK/React package. Import it at the top. Invoke the hook within the component. Use chat. This hook gives us an object from which we can destructure messages, which is the conversation history, send message, which is a function to send new messages to the API route, and status to know status of the chat. By default, this hook automatically connects to /API/chat, which is exactly what we have created. So please make sure to follow the same route structure. Now let's render the messages. Inside conversation content, curly braces, messages.map, pass in a callback function. For each message, render a div tag with key is equal to message.id, and each message has parts, allowing the messages array to contain different types of content. Let's map through the parts. Curly braces, message.parts.map. We pass in a callback function. We get access to the individual part as well as the index. And within the function body, we will use a switch statement to handle the text part type, which is the only part type we'll have for this implementation. So switch statement on part.type, curly braces, and for case text, we return React fragment with key set to $curly braces, message.id, followed by the index to make sure this is unique. We will then invoke the message component with from set to message.role. And this prop tells the message component whether this is from the user or assistant. The text will get styled appropriately. Within the message, we render message content with the response component rendering heart.text. The response component handles the markdown rendering. We'll also add a default case where we return null. Next, let's use the status enum and add a loading indicator that shows while we're waiting for a response. So right before ending conversation content, curly braces, if status is equal to submitted or status is equal to streaming, render the loader. Finally, we'll add a handler that calls sendMessage for when the user submits a message. Const handle submit is a function, receives message of type prompt input message, and within the function body, if there is no text, so if there's no message.text, we don't send anything, we simply return. Otherwise, we send the message, passing in an object with text set to message.text, and clear the input. So set input, empty string. This message, by the way, is automatically passed as an argument to handle submit when we assign it to the onSubmit prompt of the prompt input component. So on prompt input, onSubmit is equal to handle submit. Our TypeScript error is also fixed. Perfect. Our UI is now complete. Time to test our standard AI chatbot. Navigate to localhost 3000/chat, and you should see the clean chat interface. Enter the prompt, what is React, and submit. The AI will stream back a response. Try a follow-up like, can you give me a code example? And the chat maintains context and provides a relevant example. But now, watch what happens when you ask, what is our company's vacation policy? The AI can't help because it doesn't have access to that information. But before you give AI access to internal information, you would want to control who has access. For this next section, let's add authentication with Clerk, our sponsor for this video. Clerk gives us a complete authentication solution with pre-built UI components and user management. Click on the link in the description to follow along. First, sign up to create an account if you haven't already. I'm going to enter my email and password. Verify your email, and now, once you're logged in, create a new application. Enter the name of the application as RAG Chatbot. Select sign-in options that you want to support, and you can see a preview of the UI on the right. With the default options, we will have email, password, and Google authentication. I will also add GitHub. You can see the same updated in the preview. When you're happy, click on the Create Application button. This brings us to the instructions page. Choose Next.js as a framework if it's not already selected. Now, let's follow the steps together to add Clerk to our project. Step 1. Install the Clerk package. Copy the command from the Setup Instructions page and run it in your terminal. Step 2. Set up your Clerk API keys. Copy the publishable key and secret key from the Setup Instructions page and add them to your .env.local file. I just completed that step behind the scenes, but make sure to use your own keys instead of mine. Step 3. Create a middleware.ts file in the source folder. So within the source folder, new file, middleware.ts. Copy the code from the Setup Instructions page and paste it in the file. This will help us access auth data and configure protected routes later. Step 4. Wrap your entire application with the Clerk provider component, which is a React component that provides Clerk's context to your application. We will do this a little differently to what the setup instructions show. In the root layout file, so layout.tsx, import clerk provider component at the top from @clerk/Next.js and wrap the JSX with it. So return clerk provider. All right, now that we have clerk set up, let's add sign-in and sign-out functionality to our application. Inside the components folder, create a new file called navigation.tsx. We will define and export a React component called navigation. So export const navigation is equal to an arrow function. Now, the great thing about Clerk is that it provides pre-built components that handle all the authentication flows for us. We will import the sign-in button, the sign-out button, the sign-up button, the signed-in component, and the signed-out component from Clerk. We will also import the button component from Chatbot UI. For the JSX, we will start with the nav element with a border and a flex container nested inside it. Within the container, we'll add a logo of sorts, so a div tag. Let's call this rag chatbot with class name TextXL, font semi-bold. We will also add a div for the sign-in and sign-out buttons, a flex class to place the buttons side by side, and gap2 for some spacing. Now within the div, let's use the clerk components. The signed out component renders the children when the user is not signed in. In that case, we will render the sign in button and sign up button components using the Chatbot button component. So sign in button with Chatbot button. The text is sign in. Variant is equal to ghost. And we will also add mode is equal to modal to open a modal dialog instead of redirecting to a separate page. Right next to the sign-in button, we will add the sign-up button. Mode is equal to modal. We will use Chatbot button component once again, and the text is sign up. Along similar lines, we invoke the signed-in component, which renders the children when the user is signed in. So in that case, we will render the sign out button component using the Chatbot button element. Sign out button, the Chatbot button component with the text sign out, and variant is equal to outline. Our navigation is ready. Include this in your layout.tsx file. Within the body tag, import and invoke the navigation component. Import it at the top from components/navigation. To accommodate for the navigation, in page.tsx, we're going to remove some height from the page. Check the browser, and we see the navbar with the logo top left and the sign in and sign out buttons top right. Let's test if the auth flow works as expected. Click on the sign up button and create an account with your email and password. Verify your email. And once signed up, you should be redirected back to the home page. We now see the sign out button instead of sign in or sign up. Click on the sign out button and you're logged out. Redirected to the home page. Click sign in, enter your email and password, and you should be redirected back to the home page. Perfect. Our auth setup works as expected. For the next step, let's protect our chat route so only authenticated users can access it. Right now, anyone can go to /chat, which is not great for internal information. So let's add this protection logic in the middleware.ts file. First, we'll import a function called createRouteMatcher from clerk, which helps us define which routes are public. So const isPublicRoute is equal to createRouteMatcher. We pass in an array, the root route, along with sign in and sign up. We're saying that the home page and auth pages are public. Everything else needs authentication. Next, we'll pass a function to clerk middleware. This is an async function, which receives the auth object and the request object as arguments. In the function, we check if the request does not match any of the public routes. So if not is public route, passing in request, and if that is the case, we call the protect method on the auth object. So await auth.protect. This method will redirect the user to the sign-in page automatically if they're not signed in. You can see how easy it is to implement route protection. Let's test if it works as expected. Sign out and navigate to localhost 3000/chat. You should be redirected to the sign-in page. Sign in with your email and password. And once signed in, you should be automatically redirected back to the chat page. Our soon-to-be internal RAG chatbot is now protected and only authenticated users can access it. For the next step, let's add the ability to upload knowledge documents that our chatbot can use to answer questions. This feature involves 3 separate parts that all work together. First, we need a UI where users can upload documents. We will keep it simple and stick to PDF documents for this project. Second, we need a server action that processes these PDFs. The server action will extract the text from the uploaded PDF, chunk it into smaller pieces, and then convert those chunks into vector embeddings using OpenAI's embedding model. Chunking helps improve the accuracy and efficiency of semantic search and is a crucial step in RAG. Third, we need to store the vector embeddings in a vector database. This becomes our knowledge base that we will search against when users ask questions in the chat. Let's start with the database setup first, as we need a place to store the embeddings before we can process any PDFs. For our vector database, we will use Neon. Neon is a serverless Postgres database that supports vector operations, perfect for storing our embeddings. Head over to neon.com and create an account. Once you're logged in, let's create a new project. Name it RAG Chatbot. For the Postgres version, select 17, choose AWS as the provider, and pick a region close to you. Then click Create Project. Once the project is created, you will see a Connect to your database card. Click Connect and click the Copy Snippet button to copy the connection string. Now let's add this to our .env.local file. neon_database_URL and paste the string without the PSQL prefix. All right, that's all we need from the Neon console. Everything else we'll do with code. So let's install the packages we need. In the terminal, run the command npm install at neondatabase/serverless, drizzle-kit and .env. Neon database/serverless is Neon's database driver for TypeScript. Drizzle ORM is a type-safe ORM that lets us write TypeScript instead of SQL to work with our database. DrizzleKit is the CLI tool we'll use for handling database migrations or changes. And .env helps us load environment variables. All right, now let's set up our database connection. Inside the lib folder, create a new file db-config.ts. First, we'll import the functions we need. Import drizzle from drizzle orm/neon http, which creates our database instance, and also import neon from neon database/serverless to create the connection. We'll also import config from .env to load our environment variables. Now let's make use of the imports. First, call config, passing in an object with path set to .env.local. We're basically loading the environment variables from our .env.local file. Next, create a SQL client with our connection string. So const SQL is equal to neon process.env.neon database URL. And we use the exclamation to let TypeScript know we know what we are doing. Finally, wrap SQL with drizzle. So export const db is equal to drizzle SQL. Our database connection is now ready. Next, let's define our database schema. In the same lib folder, create a new file called dbschema.ts. First, import the types we need from Drizzle: pgtable, serial, text, and vector. Now let's define our documents table. Export const documents is equal to pgtable. We'll call it documents. We'll have ID of type serial ID, and this is primary key. We'll have our content, which is text, and this cannot be null. Finally, we'll have our embedding. This is of type vector, and we specify dimensions 1536. So the ID is an auto-incrementing primary key. The content field stores the actual text chunk from your PDF document. And embedding is a vector field with 1536 dimensions, which is the size of OpenAI's text embedding 3 small model output. But searching through vectors can be slow if you don't have an index. So let's add one. Import index. And as a third argument to pgtable, specify a function which returns an array. The function gets access to table, and we call index. Let's name this embedding index dot using hnsw table dot embedding dot op vector cosine ops. If this is confusing, don't worry too much about it. It's just syntax you have to follow. This basically creates an HNSW index, which stands for Hierarchical Navigable Small World, and it's an algorithm that makes similarity searches really fast. Now let's also export types for TypeScript. So export type insert document is equal to type of documents dot $infer insert. And similarly, export type select document type of documents dot $infer select. Our schema is ready. The next step is to configure Drizzle. In the root of your project, create a drizzle.config.ts file. Here, import config from .env and define config from drizzlekit. Next, load the environment variables. So config path.env.local, and then export default define config, pass in an object. We set schema to /source lib dbschema.ts out to /migrations dialect Postgres and db credentials URL process.env neon database URL with exclamation. So this tells Drizzle where our schema is, where to put migrations, and how to connect to the database. Now here is an important step. Neon's Postgres needs the PG vector extension to work with vectors. So first, let's create a custom migration to enable it. In the terminal, run the command npx drizzlekit generate -- custom. This creates a new migration file in the migrations folder. Open that file and add create extension if not exists vector. Now run the migration to enable the extension npx drizzle-kit space migrate. Our command completes, and now let's verify if it worked. Go to your Neon console, open the SQL editor, and run select extension name, extension version from pg_extension, where extension name is equal to vector. You should see the vector extension listed with the version number. Now we can generate the migration for our documents table. Run the command npx drizzlekit generate. This will create a new migration file in the migrations folder. We can see the SQL, create table documents, ID content embedding, and an index. Now you can run npx drizzlekit migrate. Our command completes, and to verify everything worked, back in Neon console, click on Tables, and you should see the Documents table. We have ID, Content, and Embedding, which is vector of 1536 dimensions. Perfect. Our vector database is now ready. We have a place to store our document chunks and their corresponding embeddings, and we have set the HNSW index to support fast similarity search. The next step is to create our server action for uploading documents. But before we build that server action, we need a couple of utility functions it will use. First, we need utility functions for generating embeddings. When we process a PDF, we'll need to generate embeddings for multiple chunks of text. And later, when a user searches, we'll need to generate an embedding for their search query. Let's create both. Back in VS Code, create a new file in the lib folder called embeddings.ts. Begin by importing the embed function from the AI SDK and the OpenAI provider. Now, let's start with the single embedding function, which we will use for search queries. Export async function, generate embedding. This takes a string and returns an array of numbers, which is the embedding vector. Inside the function, we'll clean up the text, so const input is equal to text.replace new line character with an empty space, and then we'll generate the embedding. Await embed, we pass in an object. Model is set to OpenAI.textEmbeddingModel, and we use textEmbedding3 small, which produces 1536 dimensional vectors, exactly what we configured in our database schema. We will also pass input as the value. This returns an object from which we can destructure the embedding. We return that embedding. Now, for processing PDFs, we'll have multiple chunks to embed. We could call generate embedding for each chunk, but that means multiple API calls, which is slow and expensive. Instead, let's create a batch function. Import embed many from AI SDK and create the batch function. Export async function, generate embeddings, plural. This gets texts, which is an array of string. And within the function body, const inputs is equal to texts.map. And for each text, we replace new line with a blank space. And then we call embed many with the same model. So OpenAI text embedding model, and values, plural, is going to be inputs, plural. This returns an array of embeddings, which we can destructure. Finally, return embeddings from the function. Perfect. We now have utilities for generating embeddings, singular for search queries and batch for document processing. Next, let's create the chunking utility. Remember, we need to break PDFs into smaller pieces so we can retrieve just the relevant sections when users ask questions. We'll use a package called LangChain that has utilities specifically for text splitting. Back in VS Code, run the command npm install @langchain/textsplitters. Now, create a new file in the lib folder called chunking.ts. Chunking.ts. First, import a function called recursive character text splitter from @langchain/textsplitters. Then invoke the function. Export const text splitter is equal to new recursive character text splitter. We pass in an object, chunk size set to 150, and chunk overlap set to 20. Chunk size 150 means each chunk of text will be roughly 150 characters. That is pretty small, but for this demo, it works well. In production, you might use 500 or 1000 characters. Chunk overlap 20 means consecutive chunks will share 20 characters at their boundaries. This helps us maintain context across chunks and is very important. And let's add one more parameter to make the splitting cleaner. Separators is an array, and we specify just one, which is a single space. This prevents words from being cut in half. Now let's create the function that uses this splitter. So export async function, chunk content, receives content of type string, which will be the PDF content in our case. And we call the split text method text splitter dot split text and pass in the content. We'll trim the content to remove any leading or trailing white space. So content dot trim. The function will return an array of strings, and each string is a chunk. So return await text splitter dot split text. That's it. Our chunking utility is now ready. It takes a long piece of text and breaks it into smaller overlapping chunks that are perfect for embedding and searching. We have both the utilities our server action needs: embedding generation and text chunking. Now let's build the server action that brings everything together. We'll extract text from PDFs, chunk it, and generate embeddings and store everything in our database. First, we need a package to extract text from PDFs. So in the terminal, run the command npm install pdf-parse. We need to treat pdf parse as external in the server build. So update next.config.ts to include it. The configuration is server external packages, and we specify pdf parse. Next, create a new folder in the app directory called upload, and inside create a file actions.ts. Add the use server directive at the top of the file. This tells Next.js this is a server action, which is code that runs on the server but can be called directly from client components. Now let's import what we need. We import the PDF parser, so PDF from PDF parse, our database connection, so import db from lib/dbconfig, the documents table schema, and the two utilities we just created: generate embeddings, plural, and chunk content. Now we have an error for PDF parse because we haven't installed the types. So run the command npm install at types/pdf-parse. Perfect. Now let's create the function that processes PDFs. Export async function, process PDF file, and this function receives form data from the upload form. Form data of type form data. Now form data is how browsers send files to servers. Within the function body, let's extract the PDF file. We'll start with a try-catch block for catching any errors. So console.error, PDF, processing error, logging the error, and we return an object with success set to false and error set to failed to process PDF. Within the try block, we get the file from form data. So const file is equal to formdata.get PDF as file. Now to extract text from the PDF, we need to convert the file to a buffer and then pass it to PDF parse. So const bytes is equal to await file.arraybuffer, and then const buffer is equal to buffer.from bytes, and finally const data is equal to await PDF buffer. So first we convert the file to an array buffer, then to a Node.js buffer, then pass it to PDF parse, which extracts the text. Next, let's check if we actually got any text. So if there's no data.text or data.text.trim.length is equal to 0, we return success false and error no text found in PDF. So if the PDF is empty or has only images, we return an error. But if it does contain text, let's use our chunking utility. So const chunks is equal to await chunk content, and we pass in data.text. This breaks the entire PDF text into smaller chunks. Next, generate embeddings for all the chunks. So const embeddings is equal to await generate embeddings, and we pass in chunks. We use our batch function to generate all embeddings in one API call. Now let's prepare the data for our database. So const records is equal to chunks.map. We pass in a callback function. We get access to individual chunk as well as the index, and we return an object where content is set to chunk and embedding is set to embeddings of index. So we create an array of records where each record has the text chunk and its corresponding embedding. The chunks and embeddings are in the same order, so we use the index to match them up. Finally, insert all records into the database. Await db.insert documents, and the values we insert are the records. We then return an object where success is set to true and message is set to created records.length searchable chunks. All right, our server action is complete. It handles the entire flow from receiving a PDF file to storing searchable chunks in a vector database. Now let's build the UI where users can upload PDFs. This will call the server action we just created. In the upload folder we created earlier, add a page.tsx file. Let's define a basic React component. Export default function, PDF upload, and we return a div tag. This is a client component since we'll need to handle file uploads and show loading states. So add the useClient directive at the top. Next, let's import what we need. We need useState for managing component state and our server action. So import process PDF file from /actions. Now let's import the UI components we need. Card and card content, label, input, alerts, and loader. These are ShadCN UI components we'll use for the UI. Next, let's set up the state we need. Inside the component, invoke useState. The variable is isLoading. The setter function setIsLoading, and the initial value is false. We will also track any messages to show the user. So useState, messages, set messages, and the initial value is null. The type, however, is an object where we have type property that is either error or success, and text property a string. It is either this object or null. Now let's build the JSX structure. Start with the container. So a div tag with class min height screen, background gray, 50, some vertical padding and horizontal padding. Next, another div tag with class name max width 4XL and MX auto. Next, add the page title. So H1 PDF upload. We'll also add some Tailwind classes for styling. Text 3XL, font bold, text gray, 900, margin bottom 8, text center. Now add the upload card. So invoke the card component from ShadCN with class name, margin bottom 6. Invoke the card content component inside with class name, padding top 6. And we'll add a div with class space y4. This will add some spacing between the label and the input, which we will define now. So invoke the label component. The label is upload PDF file. We will add HTML4 is equal to PDF hyphen upload. And below the label, the input component, ID is equal to PDF hyphen upload. Type is equal to file. We set accept is equal to .pdf to only allow PDF files. On change is equal to handle file upload, which we will define in a moment. Disabled is equal to is loading and some more top margin. Below the input, add the loading indicator. So curly braces, is loading, and render a div tag with class name, flex, item center, gap2, loader2, with class name is equal to height 5, width 5, animate spin, and span tag that says processing PDF. We will also add some styles. Text muted, foreground. This shows a spinning icon and message while processing. The loading should actually be outside the div tag. Finally, add the message display. So braces, message, and if that exists, we render the alert component. We nest the alert title and the alert description. We have cannot find message. The state variable should be message and not messages. So message and set message. Back in the JSX, for alert, we're going to specify variant is equal to if message.type is equal to error, destructive, otherwise default. For the alert title, if the message type is error, we render the text error, otherwise we render the text success. And for the alert description, we render message.text. So the alert shows success or error messages. The variant changes the styling based on the message type. Now let's create the file upload handler that the input calls on change. Const handle file upload is equal to an async function. It receives event of type react.changeEvent HTML input element, and within the function body, we get the selected file. So const file is equal to e.target.files, and if that exists, the first file. And if there is no file, we simply return. Set isLoading to true and set message to null to clear any previous messages. Now let's call our server action. We'll add a try block with catch, and if there is an error, we set message, passing in an object where we set type to error and text. An error occurred while processing the PDF. We will also add a finally block where we set isLoading to false. In the try block, however, we create form data. So const form data is equal to new form data, and we append the file. So form data dot append the file with the key PDF. This is what our server action expects. So call the server action process PDF file, passing in the form data, and handle the result. Const result. Successful, so result dot success. Make sure to await the server action. So if result dot success, call set message, passing in type success and text set to result dot message. And if that doesn't exist, PDF processed successfully. We will also set e.target.value is equal to an empty string. So we are clearing the file input. If the result is not successful from the server action, we call set message, we set type to error, and text result.error or failed to process PDF. And that is our PDF upload UI. Let's test this. In the browser, navigate to localhost 3000/upload. You should see the upload interface. Try uploading a PDF file. I'm going to upload this Tech Corp Solutions Employee Handbook, which is a PDF file I had generated from AI. It has a few sections like health and wellness benefits, professional development, code of conduct, performance reviews, expense reimbursement policy, and communication guidelines. You can upload any PDF you want to. So upload, and you will see a loading spinner, then a success message telling you how many chunks were created. Success created 28 searchable chunks. If you take a look at Neon and refresh the documents table, you will see the chunks are now stored in your vector database with their embeddings ready to be searched. We have content and the corresponding embedding. And for each chunk, if I were to open the third one, for example, you can see we start with balance while delivering and end with through innovative technology. If I go to the previous one, you can see the overlap, balance while, and the one after, technology. Our PDF upload works as expected. We can now process PDFs, extract their text, chunk them, generate embeddings, and store everything in our vector database. Next, we need to implement semantic search so our chatbot can find relevant chunks when users ask questions. Back in VS Code, we'll create a search function that finds similar documents based on meaning. So create a new file in the lib folder called search.ts. Here, we will import several functions from Drizzle. So import from Drizzle ORM. Cosine distance calculates how similar or dissimilar two vectors are. DESE sorts in descending order. GT means greater than. And SQL lets us write raw SQL expressions when needed. We will also import our database connection. So import DB from dbconfig, our schema, so documents from db schema, and the single embedding function we created earlier. So import generate embedding singular from /embeddings. Next, let's create the search function. Export async function, search documents, and the function takes 3 parameters. Query of type string, which is what the user is searching for, limit of type number with a default value of 5, which controls how many results to return, and threshold of type number with a default value of 0.5, which dictates the minimum similarity score. We will ignore results below 0.5 similarity by default. This should be number. Now within the function body, first we need to convert the search query into an embedding. So const embedding is equal to await generate embedding, and we pass in the query. Next, we need to calculate similarity between this query embedding and all the document embeddings in our database. Drizzle's vector support helps us with this. So const similarity is equal to, we calculate the cosine distance between the query embedding and all the document embeddings in our database. So cosine distance, documents.embedding as the first argument, and query embedding as the second argument. But cosine distance measures the dissimilarity between two vectors. So we will subtract from 1 to get the similarity. We will use SQL number template literal 1 minus $curly braces cosine distance. Now let's build the database query to get the most relevant documents. So const similar documents is equal to await db.select. We will select the document ID. That is going to be documents.id. The content is going to be documents.content. And we will also select the calculated similarity score. And we do this from our documents table. We will then add the threshold filter. So .where we call greater than, passing in similarity and threshold. We only want documents with similarity above 0.5, which is the default threshold. Finally, we will sort by similarity and limit the results. So order by descending of similarity, and we limit to limit, which is 5 by default. We will return similar documents from the function. This function is the heart of our RAG system. It takes a natural language query, converts it to an embedding, searches our vector database for similar chunks, and returns the most relevant ones. The index we created earlier makes this search fast even with thousands of documents. And because we're using cosine similarity, it finds documents based on meaning, not just matching keywords. Now we have all the pieces. We can upload documents, search them, and chat with AI. Let's connect everything together so our chatbot can actually use the knowledge base when answering questions. Currently, our route handler just streams responses without any access to our documents. Let's give the AI a tool it can use to search the knowledge base. In the route handler present in the chat folder, first add tool to the list of imports. From the AI package, import tool. This lets us define tools the AI can use. We will also need Zod for the tool's input schema. So import Z from Zod. We will also import the search function we just created. So import search documents from lib/search. Now let's define a tool for searching the knowledge base. Before the post handler, const tools is equal to an object. The tool name is search knowledge base, and we invoke the tool function we just imported. We pass in an object with description, search the knowledge base for relevant information. We'll define the input schema, which is z.object. It has a query property, which is z.string, and we describe it as the search query to find relevant documents. And then execute is an async function. This gets access to query. So the AI will use the description to know when to use this tool, and the input schema tells it what parameters to provide. Let's implement the execute function. We'll add a try-catch block where we console.error, search error, followed by the error, and we return a string, error, searching the knowledge base. And within the try block, const results is equal to await search documents, passing in the user's query. We limit to 3 relevant documents and 0.5 as the threshold, which is also the default, so you can leave it out. Limiting to 3 results will keep our context focused. Now let's handle the results. If results.length is equal to 0, we'll return no relevant information found in the knowledge base. Otherwise, we're going to format our results. So const formatted results is equal to results.map. We pass in a callback function. For each result with index, we return within square brackets index plus 1, followed by the content. And then we call .join with 2 new lines. We're basically formatting the results nicely with numbered entries separated by blank lines. We will return the formatted results. Next, we need to update our message types to include the tools. So from the AI package, import infer UI tools and UI data types. Create the new types after the tool's definition. So export type chat tools is equal to infer UI tools, type of tools, and export type chat message is equal to UI message, never, since no metadata, UI data types, and chat tools. These types ensure TypeScript knows about our tools throughout the application. So update the post function to use the new message type. So messages of type chat message. Next, pass the tools to stream text. So tools, key and value being the same, so we can use the shorthand notation. And we will add a system prompt to guide the AI on when to use it. I'm going to copy paste our system prompt here. So you are a helpful assistant with access to a knowledge base. When users ask questions, search the knowledge base for relevant information. Always search before answering if the question might relate to uploaded documents. Base your answers on the search results when available. Give concise answers that correctly answer what the user is asking for. Do not flood them with all the information from the search results. That is our system prompt. It tells AI to search the knowledge base when appropriate and base its answers on the results. And one more thing. When the AI uses a tool, that's one step. Then it needs another step to process the results and respond. So we need to allow at least 2 steps. From the AI package, import step count is, and add it to stream text. Stop when step count is 2. All right, our updated route handler is complete. The AI can now search the knowledge base when answering questions. Let's test the full RAG system. First, make sure you've uploaded a PDF through the upload page. Then go to the chat interface and ask a question about the content you uploaded. For example, ask, what is our vacation policy? Press enter. The AI will search the knowledge base, find relevant chunks about vacation policy, and give you an accurate answer based on your actual documents. Our vacation policy provides PTO as follows for employees with 0 to 2 years, 15, 3 to 5, 20, and the vacation request should be submitted at least 2 weeks in advance through the HR portal. We can find that information right here in the PDF. Let's ask about professional development. Are there any professional development benefits? You can see, yes, there are professional development benefits. The company invests in employees' growth by providing an annual education budget of $2,000 per employee. A RAG chatbot is working. The magic here is that the AI doesn't need to know about your documents beforehand. It searches for relevant information on demand and uses it to answer questions accurately. All right, let me now show you how to quickly implement role-based access control so only admins, such as HRs in this case, can upload knowledge documents. Right now, any authenticated user can upload PDFs to your knowledge base. Probably not what you want in a real application. We will use Clerk's metadata feature to assign roles to users and protect this upload route. First, we need to create TypeScript types for our roles. So in the application's root folder, create a new folder called types, and inside, create a file called globals.d.ts. Start by exporting an empty object. This makes the file a module. Now, let's define what roles are available in our application. So export roles is equal to admin or user. Admins can upload documents, and users can only access chat. Now, we need to extend Clerk's session token type so TypeScript knows about our roles. So declare global interface custom JWT session claims metadata role is of type roles. This extends Clerk's session claims globally. Now, when we access the user's role anywhere in our application, TypeScript will provide auto-completion and type safety. Next, let's update the middleware to protect the upload route. So open middleware.ts and at the top, import next response from next/server. We will use it to redirect non-admins. Now, create a matcher for admin-only routes. So const isAdminRoute is equal to create route matcher, and we just have the one upload route. So array with one entry upload. Next, we update the middleware function. From auth, so await auth, we get the session claims. So const session claims and check if the user's role is admin. Const isAdmin is equal to session claims, and if it exists, metadata, and if that exists, check if the role is equal to admin. If someone tries to access an admin route without being an admin, so if isAdminRoute request, and the user is not an admin, we redirect them to the home page. So const URL is equal to new URL, the route, and request.url. Return next response dot redirect to this URL. Otherwise, we continue with the normal authentication check. That's the code side done. But we still need to configure Clerk to include roles in the session token. Go to your Clerk dashboard and under the Configure tab, find the Sessions page. Scroll down and find Customize Session Token. We're going to edit this JSON, add metadata, and set it to double curly braces, user.public_metadata. This tells Clerk to include the user's public metadata in the session token. Click Save to apply the changes. Now let's set our user role as an admin. Navigate to the Users tab and select your user account. It should be the only one in the list. Scroll down to the user metadata section, and next to public, click Edit. We will set role to admin. Click Save, and our user is now an admin. Let's test it out. Back in the browser, navigate to localhost 3000/upload. We should be able to access PDF upload page. In the Clerk dashboard, switch it back to user. Save it, go back to the browser, refresh the page, and navigate to /upload. You can see we are automatically redirected to the home page. Edit, admin again, navigate to /upload, and we have access. And that's it. We've built a complete RAG chatbot from scratch. The user enters a prompt in the chat UI, which gets sent to the route handler. The route handler sends the prompt to a search tool, which does a semantic search of our vector database. It finds the relevant content, formats it, combines it with the user prompt. The AI forms a natural language response, and we stream that response back to the user. We also have authentication and role-based access control. From here, you could extend this in many ways. Support more file types, add document management features, or fine-tune the chunking strategy for better results. It is completely up to you. Thank you for watching. And if you found this video helpful, please like and subscribe for more videos on how to build AI applications.